एक सेकंड में प्रेजेंटेशन
स्टोरी स्टार्ट मत करना अपना।
ये ऑन कर देते ना। हेलो हेलो
यहाँ देख लो सिंबल में जा रहा है ऊपर नीचे।
हेलो
हाँ तो
हेलो।
नहीं।
ये देखो, ये आ रहा है ना, दिख रहा है तुम्हें? हेलो हेलो।
अच्छा ये कहाँ से लिखा?
ये उसका कैप्शन वाला है। क्या कहता है, इसकी आवाज बढ़ा देंगे ना तो समझ में आ जाएगा।
जैक एंड कैप्शन।
ठीक है ना?
ज्यादा एडवांस है क्या?
एक सेकंड।
हेलो
हेलो
हेलो हेलो हेलो हेलो हेलो हेलो हेलो माइक टेस्टिंग। हॉल में क्यों नहीं आ रही है? हेलो, हॉल में क्यों नहीं आ रही है?
आपके फोन से कॉल में कैसे आएगी?
हॉल में
फोन से कैसे आएगी?
नहीं, मैं तो मीटिंग में हूँ ना, मीटिंग में बोल रहा हूँ।
नहीं मीटिंग पीसी में अच्छा स्पीकर है आपके?
वैसा भी ऐसे बोल दीजिए, उधर से कोई बोलेगा नहीं। हेलो हेलो हेलो, ऊपर आ रही है? ऊपर 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 हॉल में। हेलो 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 हेलो। ये रागा की आवाज कम कर रहा तो और बढ़िया सर। हेलो, प्रेजेंटेशन लोड करना था सर। अच्छा ये उनको बोल दीजिए ग्रीन टी शर्ट शर्ट। आते हैं
इसमें भी बीच बीच में आएंगे बैकग्राउंड में दिक्कत लगे।
हेलो हेलो।
ऑडियो भेजना है ना इसमें से।
नहीं वो आती है पर पता नहीं चलता।
हेलो।
आ रही आ रही।
आ रही है।
तुम्हारा तो चालू नहीं था?
ठीक है आप बोल के देखिए एक बार।
हाँ बोलो। आ रही है ना इसमें दिख रहा
ये
है।
वो मीटिंग से एक्चुअली बोल के देखना तो ऑडियो वहाँ क्लियर।
वेरी गुड मॉर्निंग। हेलो हेलो, हॉल में नहीं आ रही फिर भी अभी।
ऑडियो ऑन कर बढ़ा दीजिए थोड़ी सी।
पीछे से
स्पीकर के जो ऑडियो होगा ना 50 के ऊपर डाल देंगे तो।
हम बोलो हेलो हेलो।
हाँ भैया।
ठीक है बढ़िया कंट्रोल ठीक है सब।
और आज कितने आज तकरीबन 4-5 बाकी की आगे नहीं उसकी 29 तो भी ऐसा अच्छा 29।
हेलो
हेलो आयुष, आवाज आ रही? अरे
हेलो।
इससे ना अभी जाएगी।
अब जाएगी सर।
ठीक है, अभी कर देते हैं। We are going to start the session. All are requested to come to auditorium hall. Thank you.
नहीं बोलिए।
हेलो।
Suprabhat,
हेलो। हेलो।
welcome to third day of InPAC 2025. Today's session, all sessions are going to happen in this hall. You are requested, if you are in corridor, you are requested to please come to the main hall. Now I request Dr. Gopal Joshi, who was former head ACND BARC. I request him to chair the session. Gopal Joshi, sir. Thank you.
Thank you. Good morning to all. Today we have a very interesting session and I would say very important constituent of our accelerator program. So I think without any further delay, let us start our first talk. It will be delivered by Sri Mahendra Lad. Let us invite him to this dais. And he's director, Sri Lad is director of Proton Accelerator Group, RRCAT, Indore. Under his leadership, a lot of important activities in this area are taking place, including development of radio frequency quadrupole and complete infrastructure for conducting radio frequency cavities, which includes fabrication, processing, characterization, and testing using cryogenics facilities, high power solid state amplifiers, digital low level RF and high power circulators, normal conducting RF accelerating structures, and DC and pulse power supplies. These are being done under progress is taking place under his leadership. And he has got a number of achievements under he's presently the technical coordinator DAE for the Indian Institute and Fermilab collaboration, where he's also is a sub-project coordinator for 650 megahertz RF developments. He has got very rich set of publications, including 21 in journals and more than 200 in conference. So let us request him to start his talk. Please, sir.
Shubh Prabhat. Thank you, Dr. Gopal Joshi, for my biodata. I will be presenting the talk on proton accelerator activities at RRCAT and overview. And this I am presenting on behalf of the whole team of Proton Accelerator Group. And these are the constituent divisions who have been working. Accelerator Beam Physics Section, RF System Division, Superconducting Development Division, SCCS, Superconducting Cavity Processing and Cryogenic Section. Proton Linear Development Division, UHVTS, Ultra High Vacuum Section, and Cryomodule Development and Cryogenics Application Division. And just to mention that this proton accelerator activities is pursued at all the centers of DAE. So I will present what we are working and what is the infrastructure at RRCAT. Of course, as far as my talk title goes, I will present about the proton accelerator activities, but these, there is no thick boundary in RRCAT. So these divisions like RF system division, accelerator beam, they work for all the activities of even other accelerator, electron accelerators, industrial accelerator and other in designing, development and even maintaining in round the clock mode for all the machines. So I will just start. So this will be the general what is our DE perspective, then I will discuss about all the systems, subsystems and technologies and whatever are the R&D we are pursuing to have the indigenous development in parallel and of course some spin-offs, technology transfer and some societal machines, what we have also explored. Depending on the mandate and the project, we may pursue that. So as we all know, this is known to all the August gathering here. Means RRCAT has the profound infrastructure for the development of superconducting radio frequency systems, which is suitable for these two machines, which are the big mega projects. And as we all know, that today's scenario after the COVID, these are the two major big mega science projects. So hopefully, if any one of this comes, then all the partnering institutes of DAE will contribute to that. So I will just mention that this expertise is developed at RRCAT in the design development infrastructure which is needed for 1 GeV proton accelerator. For some part and for some part we are also working, which involves these all activities like beam dynamics, ion source, low energy normal conducting structure, RF systems development. And of course, this is very, very important as far as RRCAT is concerned, dedicated facility for superconducting RF cavity infrastructure involving all this fabrication, then tuning, processing, bracing. These are all very important facilities, and two test facilities for RF characterization of cavities at superconducting 2K temperature for both bare cavities in VTS and rest cavities in SCS. Of course, there is also some dimension we can have in VTS also. And in addition to this DAE long-term program, under the framework of Indian Institution for MILAB Collaborations, RRCAT has been entrusted with the responsibility of these deliverables, low beta and high beta 650 megahertz superconducting RF cavity, high power RF amplifier 650 megahertz of 40 and 70 kilowatt, and in addition design of various subsystems of high beta 650 cryo module. But for our program, we are working on other activities as such. So this is just our team, which has developed the expertise from the last few decades. Physics design, I told you, for the full, and we are working on the pulsed, as far as this design goes, for the pulsed 1 GeV machine, which is LINAC, and the 1 GeV accumulator ring for spallation neutron application. And other applications are obvious, which we all know. And design development of ion source, normal conducting structures like RFQ DTL for pulsed machine, and for ADS, it will be purely superconducting after the ion source. Then SCRF cavity fabrication, I told you, processing, testing, and all the RF systems and low-level RF, etc. So this is known to all the gentry here. I just want to mention that for the CW machine, which will be at Vizag for ADS, it will be all after RFQ, it will be superconducting. No detail, I believe, means which has been known to me. And then after 1 GeV, we all know spallation will be there for ADS. And for pulse machine, as I told, we are pursuing the activities after RFQ also, the normal conducting structure, which is the DTL, and then the spoke resonator cavity up to some energy, and then low beta and high beta. And this is the 1 GeV accumulator. So these are all the activities which I have already mentioned. So the first part which I will mention, which is a very, very important activity, Dr. Vinit Kumar and his team has worked on the complete design of 1 GeV spallation neutron source design, including LINAC and accumulator ring. And in September 24, there was a press target for the preparation of these design reports for the complete beam dynamics aspects, which is showing all these particle flow till 1 beta LINAC, and after that in injection issues in the accumulator storage and all other issues. So these all have been studied, and I would like to mention this is a very, very important internal report of RRCAT, and this has led to the peer-reviewed journal, a lot of publication, and also to PhD thesis. So this is one of the very important, and also in accumulator ring, beam halo, beam loss, and impact of failure of any magnet or cavity. What are those scenarios that have been discussed? So now I will one by one touch upon or just give the glimpse of whatever the pulsed and other activities we had been. So this is one of the ion source our team has developed for low duty factor application, and this has been tested up to 12 milliampere. This is the standard multicast cold cathode arc based ion source. And we have our ion source team has worked on a lot of option suitable to all the machine, Pulse, CW and others. So as we all know, this source has the limitation of the life, which is due to this cathode. So this our team has very important got the development done of the RF based H minus ion source, which is now tested at the high current and of course for the high duty factor of 10% and 50 hertz. So these are the parameters which we have achieved. This is the 50 kV RF. So there is a 13.56 RF amplifier and also the 2 megahertz for the plasma, and this is for the ignition at low power. So these all development have been done and tested and characterized. So these are all the parts of the RF based ion source, including the ignition system and plasma chamber, and then this is the impedance matching network for H minus. This is the standard RF solid state RF amplifier for 1 or 2 kilowatt, I think. And as we all know, this ECR proton source is mainly for the CW application, but our team has also worked on the pulsed ECR ion source, and this they have tested with the 2.45 gigahertz RF system solid state with the RF system division at 1 kilowatt, and we have got up to this 10% duty factor with 1 to 5 millisecond. And of course, we have got all the species of the extracted charge species of these, and these were identified, and you can see here all these, and this has been characterized also with the current of 10 milliampere. So the activity of then was coupling of the arc based ion source, and also in the next slide I will show the RF to the LEBT. So this is the LEBT line, and this was characterized with all the characterization from the beam diagnostic division, the help from for characterizing the beam spot and also the beam current and some emittance measurement. So these are all the curves. I'm sorry, this is the feeble spot. But all these characterization curve at different currents, and at the end of LEBT, we could achieve this 0.6 milliampere with this. But as we know, this has the limited life, so we are pursuing this as the main our ion source, RF based ion source, and this also we have characterized for high current, and to get this 2 milliampere with all these beam sizes and beam spot and beam emittance normalized in X and Y axis. So this is a very good development which is done, and now we will interface it with RFQ, which I am explaining in the next slide. So the next activity is the radio frequency quadrupole section, which we have total 3 sections for enhancing the energy from 50 keV to I think we need 2.3 MeV, I think. Yeah. So this is the only one section I am showing, and this is the standard wind modulation structure. And this is one of the, as all the mechanical engineer and the proton accelerator people must be knowing, this is a very complicated structure, and we had a lot of issues during the fabrication. But I would mention that one structure has been completely fabricated with all the accuracy of 50 micron with the and then the 100 micron all the on-axis eccentricity. So all these parameters of this, and this has been characterized with the all the higher order modes, etc. With the and this is of course the simulated and characterized also measurement is done. So these are all the whatever machined T and W which were machined, and this I would mention that we have the 5-axis CNC machine with the help of our DMTD division, and they had been operating this machine round the clock sometime, and there had been a lot of hiccups and maintenance in this. So this is a very huge machine, and with this we have got assembled the 2 sections, means 2-section machined and assembled, and one is brazed, which is this which is recently in our brazing furnace. And I would just mention that during the course of fabrication, all the characterization by the teams of different divisions, and of course tuning, we have all the tuning characterization and the tuning setup to have the field flatness and all the optimization of parameters and all the higher order modes which is expected. This is after the brazing. I will mention here that in the brazing furnace during the first trial, since the first structure took a lot of time, so there was, because of the coolant etc., there were a lot of contamination. So it contaminated in turn the furnace also. which puts it down for a long time, and this furnace was cleaned by the people of workshop, DMTD division, and then again it was brazed last December. And in January, February, we have characterized. I will just mention about the. So this is the one characterization which all the RF person knows about the means beam field distribution throughout the length. This is just showing to show slides to show the tuning, how tuning has helped to bring the field within whatever accuracy we want. So after the successful first section brazing, the second was carried out, and it is also very good. This is will be presented in the poster session in this poster. For RFQ, we have also developed the RFQ coupler, and this is the coaxial pulsed 10% coupler. And I would like to mention that our RF team is also have also developed the similar coaxial cable for CW at 100 kilowatt for our Indus machine. So we are quite confident to have this coaxial coupler for all RFQ and DTL application. So these are the pictures and the testing. It was vacuum leak tested and it has qualified all. And of course the coupling etc. was measured with the center frequency of 325 megahertz. I will mention about RFQ. We have gone for the, because of the klystron non-availability, the 4-feed RFQ of course, we have 250 kilowatt ambition. Right now we have achieved 150, but we will achieve 250 in a short time. So this has been tested, 2 in number, and tested in the pulse mode from 1 to 5 millisecond with 50 hertz repetition rate. And this uses 350 kilowatt module with the small module of 1.5 kilowatt pulsed module. I will show just the picture in the coming slides. So these are the characterization, and this is the module you can see. These are 2 modules back to back on a common cold plate, and all the combiner etc. were characterized with this VNA. And we have got tested all the RF amplifier first characterized and then tested in situ at the RFQ location. And right now this is the second unit of this amplifier. We have built 2 amplifier. So the second unit is under assembly and tested. And I think it has been tested. I was informed by Akhilesh. So this has the 50 kilowatt 3 amplifier solid state. This is one of the very good development, and also this has got the peer reviewed publication in 2 journals. So another thing required for RFQ is the digital low-level RF. As we all know, the pulse digital FPGA, we have developed all digital low-level RF for Indus machine at 500 megahertz, 31 megahertz, and also on the similar with the upgraded modules and the all the up-down converter hardware available. Our team has developed a very good FPGA based one setup for the 4-channel of the RFQ. And these are all the pictures of all the up-down converter RF processing unit, and this was tested in the lab with the and characterized with the dummy cavity. I will show you the pictures. This is based on the PXI FPGA. Of course, now we are going for the SoC development with the local vendors for all these. So this has been characterized low-level RF with all the required stability which is needed for RFQ. This is also one of the good development our RF system power supply division team has done. The pulsed water-cooled DC power supply we have developed, which are normally air-cooled and not pulsed off-the-shelf power supplies are available. So Bala Pandaji and his team have developed for 40 kilowatt. This is one of the amplifier, and based on the same scheme, which is parallel 150 ampere module. We have given the order to the vendor in Pune, which is known to INDORE, to all the gentry here. And that we will be getting in a month or so, which is for 40 kilowatt solid state RF amplifier of all the frequencies. And this also got the peer reviewed publication in all these journals by the Bala Pandaji and team. I will just give the glimpse of the next structure, which is the normal conducting DTL, and this Vijen Prasad, Dr. Shri Vijen Prasad and his team has worked on this. We have prototyped in aluminum, and now we are working, I think this is Vijen SS, I think, no? Yeah. And this will be copper plated, I think, from inside. So with all this surface finish, we could achieve this structure fabricated. And these are all the components of the RFQ and drift tubes which were there. And this is the assembly of all the drift tube magnets with these Samarian cobalt magnets. And these have been then set up and characterized with the help of magnet division here. This is one of the very important development and work by our Dr. Vinit Kumar and team to study the multipacting for the high power couplers of DTL, and of course this is pulse, and that they have done the simulation with or without DC biasing of the coupler with 5 kV, and all the test results are published, and also this will be presented in one of the poster session 977 here. Now I will just give the glimpse of the very, very profound structure which is at the RRCAT for 650 megahertz superconducting cavity. So we have all the facilities for the fabrication of superconducting cavity, right from the forming to all the welding and fabrication and testing at different stages and tuning. So these are all the pictures of the cavity, and we have developed many 5-6 RF cavities, 650 megahertz 5 cell, and characterized and tested all of them in VTS and few in HTS. So these are all the machines and the pictures of the components required for all the dressing. So this is the tuner assembly which is at the different stages of the tuning of the cells needed. Then we have helium vessel fabricated. This is one of the very good development we have at SCDD division, Mr. Chokse and team, for the glow box development for welding this dressed cavity with all these tuner and helium vessel. And this is the picture of the fully dressed cavity after tuner. As we all know, we have a big clean room. I request if somebody wants to visit, then this is a very, very big infrastructure. So we have got the complete clean room installed and under commissioning at SCDD lab, and looked after by Shri Raghavendra and team. So this is just the layout of the, I'll show in the next slide how the cavity is. So this is having the ISO class 4 from class 8 to class 4. So all different class of 10,000, 1,000, 100, and so in the next slide it will be clear all these hashed, what are these. So this is the main class 10 clean room, and this installation is complete, and all these have been fixed, and now it is under commissioning. And these are all the pictures of the processing facility, right from electroplushing, rinsing, and then assembly, cavity vacuum test at the different stages, and then rinsing of the jacketed cavity even. So this will also be present in one of the poster. I request you all to, and of course we need annealing also. So the furnace is there. I will show in the next picture. So this is one of the detailed slide of the clean room where you see this total area of the clean room is 650, and the class 10, which is this one, is the 80 square meter. So this is the class 10, this is class 1000, this is class 100. So I have one slide which will just give a slight feel of how the cavity will move inside this clean room. This is the 10,000 area. And the person after gowning and air shower will take this cavity to the, of course, vacuum furnace, it has not been shown, but in between vacuum, then this is the storage, and then it goes into this for high pressure rinsing, inside the high pressure rinsing, and then for assembly in the class 10, and then the person takes it after all. It is just a very, very preliminary demo of how it will, and in between all this cavity tuning and the furnace operation will be needed. So as I was telling you, for testing the cavities at low power and high power, we have the VTS and HTS. So VTS, we have been testing so many cavities, and this is for one of the cavities we have achieved, which is 505, which is I would like to mention to Fermilab also we have delivered few cavities which I will mention in. So this is one of the cavity which has to be shipped to Fermilab, and this is having some issues of the required achieving required Q at that field. So This is Q0. So at this, it is getting down. So we are under the dialogue with the Fermilab for the qualification of that. So this is one of the development for the detuning compensation system during the operation of the RF cavity, which is FPGA based by our superconducting development division team, and all this has been tested on the cavity with the proper all the for our LFD and online tuning needed. This is also one of the good development, because this, as we all know, that superconducting SCDD, the superconducting cavity cannot be taken to VTS and HTS quite often. It is a long process. So for characterizing this cavity in the lab, a dummy coupler has also been, which is simulated and which has the characteristics similar to this high beta coupler. And this has been characterized with the and qualified with the cavity. So Adarsh and team, I mean our RF system division team has worked. So this is basically to measure Q external of this cavity with all these VNA with S21. Now I will mention that for a high beta cavity, we have developed all the solid state RF amplifier required at 40 kilowatt and high power also, under development at 70 kilowatt. This is just the specification of 40 kilowatt RF amplifier on the similar logic as the low power amplifier, all cascaded to get the 40 kilowatt. So these are all the components. This is one of the module 4 into 500, 2 on the top, 2 on the bottom. I think most of us know, and this have been will be presented in the poster, in different poster for the different all the components of the combiner. This is very good development of RF power sensor, which we have indigenized, and I will just mention we have transferred this technology to the private vendor also for all these RF.
5 more minutes.
Yeah, I will just rush up. So these have been characterized, and of course, as I was telling this, we have developed water-cooled DC power supply on the similar logic for CW. We have developed for this. After this RF, we have also got into the Prashant Khare and team has got the design of the high beta cryo module in collaboration with Fermilab. On the similar design, we have developed HTS cryostat for testing the superconducting cavity, and this is fabricated with the help of Inox. And all these components are there. Which have been, this also has one of the problem or the leaks in the feed can, which was attended and maintained by, and this is the advantage of our team being experienced, and for a very low downtime and at low cost, our team has repaired the leaks in one of the feed, in the feed can. This is the similar low level RF system for high precision for all high beta cavities. And this is the design of 650 megahertz cryo module beta 0.92, and the similar will be low beta cryo module. And this has been completely designed, and this is with the Fermilab under the procurement readiness review stage. So these are all the components which have been fabricated. We have also, for the pulse system, worked on the spoke resonator, and we have developed in prototype in aluminum and then in copper also. And now we will in the next year go for the niobium cavity, which is SR011. As Fermilab call SR001, BARC called ABC, we call 011, 012 like this for low beta. And of course the characterization was done for this low beta, and this all will be presented in the poster. And this is one of the good development by our, again, physics design team to measure the dark current, have the simulation during the testing of the cavity, and how the field emission, etc. will be there. And this has also got the peer-reviewed journal and presented in the poster. This is one of the, again, activity for the accumulator ring, for the beam dynamics of the accumulator ring, and all the, as Dr. Arup and all the physics team must be knowing how difficult is this. And this was also one of the press target. I will just mention quickly about the whatever deliverable we have done. We have delivered 3 cavities which have been gone into the prototype cryo module at the Fermilab. And we have our colleagues from the Fermilab, and this is in series with the 3 cavities from the UK, and then this has been tested for the vacuum and cryogen testing. So this is very one, and this was published in their newsletter also in the Fermilab. And we have delivered 2 numbers of solid state RF amplifier, and then HTS cryostat, which is under shipping and will be reaching in a 15 days time to Fermilab. So these are all the shipment where the Prashant Khare and team has worked. We have designed the complete, because this is a huge structure for all these shocks, etc. He has designed the complete, and this has been done with the help of the Messrs. Inox. They have been given the order for shipment till the Fermilab. So these are all the pictures, and when it was shipped from Indore to Mumbai and then onwards, and this is on the way. And we have been working on the R&Ds for, so with the help of Dr. Raghavendra Tiwari and of course the NFC. So this is for the development of an IOBM at high triple R, and we have got the success in collaboration with NFC. Our job is to characterize, and NFC will, from ingot, will give the, so they have given us a lot of samples, and we have got, through all the collaboration, developed this. This is one of the, again, R&D activities for, these are all the plasma processing technique for the cleaning of the cavity inside if they are contaminated. And this has been also characterized and tested for all the modes of superconducting cavity. These are the studies for achieving the magnetic flux expulsion studies to have the cool down rate at different rates, to get the high quality factor in general. So these are all Raghavendra and his team has worked on. Of course, there is this is very important activity as far as DAE goes. Dr. Raghavendra Tiwari's team and our team has been working on the coating of niobium tin on the, which is a very standard technique for having the alternate material of the niobium, which works at the high temperature of this. And this has given the very fantastic results. And we have so many options for coating of other things. And we have characterized this also to get this niobium material qualified. Then we have also got the R&D for the low temperature microscopic setup to investigate the hydride formation to augment the quality factor. These are all the, means always in superconducting cavity we have the problem of Q is achieved at the low gradient, but once at the high gradient because of field emission and contamination, it's a very complex procedure. So we are working on the R&Ds for different options to increase the Q. So this is one of that, how to investigate the hydroid formation on the surface of the cavity, and this has been characterized with the seams and other setup in the beam line, also using Indus beam lines. And they also, this is another study for the how to have the baking. There is a called mid temperature baking, which will help to have more again the quality factor, I think. Yeah. The job of this study was to have, so this was all a PRIS target and has been, this is one of the spin-off which everybody knows for the, means Prashant Khare and team has worked, and he will cover, there might be some poster for carrying the perishable item, liquid nitrogen cooled. And we have got MOU with all, this product is called Shivai, and it has been technology transferred to Tata Motors, and they have delivered, and they have developed 32 feet, 20 feet, and we had been helping them in testing. And of course for fish, so with the CIFT, we have the MOU for the shipment of fish from the, right from the source to the destination. And these are the technology transfer. I will just mention all very important. Import substitute. Our RF system division has transferred this to all these vendors, Mumbai based or Indore based, for all these products which are needed for the solid state RF amplifier. And this is one of the good development we have done for the substrate development with the help of CMET. We have got developed, which is the only available from the import source from Roger. So this is the setup, and we have generated the recipe, but it has not been transferred, being the very big setup, and we are in the process of trying for a vendor to get this technology. This is put on our website, and also it has been patented. So this is the picture of the handing over of patent. And this is the one of the cryocooler, which is at 30K, tested at 45 watt at 77K, and of course at the self-load at 30K. And this is a very important development by Raghavendra and team, used by all the academic institute. And this technology has also been transferred to one of the private industry in Mumbai. I was telling you about the societal machine. Since we have all the experience of the pulsed cyclic machine, so we have got the exploring the design of the pulsed 72 to 30 maybe for the heavy ion Right now we have designed for the, not for the, but for the carbon also we can have all the design qualified and done for all these. This is like the booster ring for injection at the low energy from RFQ. And either superconducting or normal conducting, and then this is the standard synchrotron ring for ramping the energy, and this is very low power needed for this, for all low power of the beam, but high in pulse current. So we have developed ion source for this also. Latest design has also been looked after. This was, I was telling, this is the high current pulse proton source for that same proton synchrotron, and this also been tested and characterized by Mr. Ghodke and team. These are very good development. Of course, this is one of the spin-off of our proton group, laser welding, which we all know. So in summary, I will mention that for all these state-of-the-art complex technologies needed for proton accelerator, we have developed the infrastructure for all superconducting cavity processing, and of course all the technologies of RF, vacuum, and other normal conduct structure. And we are confident that we can contribute in this high intensity proton accelerator to the best possible way in as a DAE project. Thank you for your attention.
Thank you, Sir, for excellent comprehensive overview of so many activities going on in this very important area. Now, maybe we can take a few questions if there are.
Yeah, the talk was generic, so no question.
No.
See, basically, right now, niobium is the only option. But for the coating, if it succeeds in getting all the characterization and at high temperature, providing that Q, we will definitely, and our DAE should have. So Raghavan Tiwari team is very serious, and we are interacting quite intensely with them. What? Yeah, it is a tremendous development. And there are other options also, copper coating on that. So for all the mechanical and the electrical properties. So this is a very good and need of an hour for like indigenous development. We should work on that. And our team is, thank you. Okay, thank you all.
Thank you, sir. Thank you for excellent talk. On behalf of InPAC2025, I have the pleasure to give the memento to Sri Lag. Now we move on to the next talk, which is another very important development that are taking place. It is by Shri Jishnu Dwivedi. So let us invite him to the dais. Shri Dwivedi, who is presently Director, Technology Development and Support Group at RRCAT. He is mechanical engineers with many working in the area of 10 MeV industrial LINAC and process controls for e-beam processing. He has multiple achievements in these important areas, including development of multi-domain e-beam radiation processing technology. So going right from lab to industrial level, qualification of e-beam radiation processing facilities and INDORE, which is working in commercial mode for sterilization of medical devices, where more than 8 million medical devices have already been sterilized. So these are very important. Taking technology to this level, I think, very laudable. Let us listen to him from all the developments in this important area. Please, sir.
Thank you, sir. So I'm going to speak on electron beam technology, which has been developed at RRCAT, and now we are in the process of taking it to industry in various domains as a service provider, as a LINAC builder, and as a facility builder. So the total team involved in this work at RRCAT is a very big team from various groups, electron accelerator group, proton accelerator group, and TDSG. And we have also got support from BARC and other institutes in this work. So we acknowledge all of them. So this is the title, this is the outline. So I will briefly give the status of RRCAT industrial LINAC and E-beam process technology. Then what are the opportunities based on the developments we have done so far in the scientific, technological and industrial domains. Then engaging with industry. This is the way we are trying to engage is totally new to us. It is not a buyer-seller mode. We are trying to collaborate with industries and we have a lot to learn from this. As you know that government of India has give lot of emphasis to make in India, Atmanirbhar Bharat and nurturing Indian industry because these are the key to our economic, technological and security progress. Challenges and preparations we have to do to industrialize E-beam technology in next 2 to 5 years. So these are the LINACs that we are working or we are planning to work on. So in 2016, we developed our first LINAC. This is 10 MeV 5 kilowatt. This was the first prototype. And this is now stationed at ARPF and is serving as backup for the LINAC there. And we also have sometimes used it to cannibalize some of its subsystems or systems to put in other accelerators. Then in 3 years after this, we developed another LINAC called LINAC2. This had several more systems which were missing from the 5 kilowatt system. And we had a good beam current here, stable beam current. And we could also qualify it for very long duration operations. So all these LINACs were characterized by long duration testing. So for example, the first LINAC, we tested it for continuous operation of 90 hours and then several operations of 8 hours continuous duty. So typically several months we operated this LINAC to understand where are the weaknesses and how to strengthen them. And this is our current workhorse at ARPF, which is sterilizing the medical devices. Then in 2022, we qualified our LINAC3. So this LINAC had 10 MeV 10 kilowatt beam power. And this also had a maximum electron energy limiting system to meet the regulation on maximum electron energy for food irradiation. So food irradiation regulations are very strict about electron energy. We should not have any electron going on to the product which is having energy more than 10 MeV. This LINAC is currently at an industry in Bangalore where it has been installed to test its performance in actual industrial setup. I will give a brief detail subsequently. And this has been type approved by AERB. So this is a standard now model which we can sell in the market and it can also be sold to various industries which are interested in manufacturing of such LINACs. But the beam power level of 10 kilowatt is not suitable for getting it profitably installed in the industry. So beam power level for a profitable installation should be somewhere close to 20 kilowatt. And recently, last summer, we tested our LINAC 4 with 10 MeV and 15 kilowatt beam power. So this is the first prototype at 15 kilowatt level and we tested it for short durations. Unfortunately, we had an issue with the klystron. So our beam power, we are right now able to go to only 12 kilowatt, but we will overcome this problem. Then we have entered into an agreement with the ECIL for co-development of 10 MeV 20 kilowatt LINAC. This we hope to do by the design part we hope to do by this year, end of this year. And in another 2 years, we hope to make 2 more LINACs, LINAC 6 and 7, which will be rated at 10 MeV 20 kilowatt. And these will be installed at high throughput food irradiation facility, which we are developing at ARPF complex adjacent to the existing facility. The LINAC 2, which is at 6 kilowatt rating, we will upgrade it to 10 MeV 12 kilowatt in the same time frame. And for upgrading LINAC 2, we have a wall shielding limit probably at close to this limit. So that is why we will not go to 20 kilowatt. And this is our LINAC plan. In addition to these, we will also be making several other LINACs with industry. That is what we can expect based on the interest industry has in our LINACs. So you can expect that maybe 4 or 5 more LINACs in the time frame will be built. And also BARC has interest in LINACs, and we have a MOU with BARC for giving 1 LINAC to them. However, the industrial machines are characterized by very high efficiency. So any loss of efficiency even by 0.5% or 1% is not only economically costly, but it is also damaging your own machine. Whatever power loss is there, it is actually eating your machine. So all the components must be brought to highest possible efficiency. And then the control system must be very robust, because these machines are supposed to operate for months together without any trip. Currently, we are able to operate them for weeks together without trip, but we have to go to a level where we can operate them months together without any trip. And then we have to have the performance quality in field operations, which also includes our ability to service and maintain them when they are at the field. And we have to have the trained manpower for servicing different systems. We have to have capacity to have the spares and qualifying the spares. This is the first prototype of 10 MeV 15 kilowatt food irradiation LINAC that we tested last summer. And here you can see a 1.5 hour run at this power level. So the LINAC, as you may be already knowing, there's an electron gun, 50 keV electron gun. There's a pre-buncher in the LEBT, and these bunched electrons are injected into a traveling wave LINAC. It is 2 pi by 3 2856 megahertz traveling wave structure and having about 60 cavities. And this is a new design of the structure where we have gone for constant gradient structure from our earlier design of constant impedance structure. So constant gradient is expected to give a gain in efficiency of about 5 to 8%. And we are still calibrating this particular aspect. Then this is the energy filtering system, which can remove electrons above 10 MeV. And then these electrons are bent towards the product. Unfortunately, there's a small conveyor which is not seen here. And the beam scanner is there to scan the beam onto the product surface. So this LINAC, though we could operate it only for short durations, we could qualify it for maximum electron energy limiting system. And also we did volumetric dosimetry on food products. And this LINAC is now operating with another klystron which is having a power limitation. So you can see this LINAC if you are interested. At ARPF, we are operating the facility in commercial mode. We are operating the facility in commercial mode and sterilizing the medical devices. So this is the, you can see a typical view of the vault, and this LINAC, this is the LINAC 2. This is the LINAC which we are using for the process. And the product is put on a tray. The tray goes inside on an automatic conveyor, and in front of the beam, which you can see here, this is the scanner. and the product is moving from bottom side to the top side, and it gets irradiated through the movement and through the scanning of the beam. So this facility has got AERB license for safety, FDA license for sterilization of risk class B medical devices. Then medical devices have to be processed under a very strict quality control. So we have quality management system. These are all quality management systems. So we have ISO 9001 and ISO 13485, which is specific to medical device sterilization. Then we also have audited, the facility has been audited for export to Europe, and ISO 1137 is the standard which governs the sterilization of medical devices by radiation. The typical throughput at this facility, as you can expect, the beam power is low, is 200 kg per hour for a dose minimum of 25 kilogram. So even with this small LINAC, we have been able to work continuously since October of 2022, and we have irradiated and sterilized more than, now it is more than 90 lakh devices. So we are reaching close to 1 crore devices. As you can see, the usage of the facility is increasing in the recent months, and we hope to have further strong use of the facility. And this is the only facility in India which can provide electron beam radiation processing for sterilization of medical devices. So several manufacturers who are exporting their devices to Europe and US, they now have this pressure of sterilizing the devices through electron beam, because ETO, which is the common process based on chemical fumigation, is being banned in these countries, and also they are phasing out cobalt because of several direct and indirect threats to the society. So the typical devices which we have qualified are listed here. So we have qualified 17 devices for sterilization using electron beam, and device qualification is a very long process. So you have to have the devices, pack them in a suitable box to make sure that electron beam reaches at every nook and corner of that box, and all devices have different geometries, different materials and different densities. And then you have to carry out process trials using large number of dosimeters throughout the volume of the box. So typically in one box there would be 57 dosimeters, and then we have to repeat this process, read the dosimeters till we have established a process where we are able to deliver a constant required dose at full volume of the product. And then the magic of process control system comes in, that we use the same process parameters for subsequent sterilization of the devices, and process control is able to guarantee that the doses are within the permissible, within the specified requirements. And this is also confirmed for every batch using 4 EPR-LNI dosimeters at front and back of the boxes to confirm that we are within the process parameters all along the process. This is a typical example of one of the devices which is being sterilized at ARPF. It is an advanced version of intravenous cannula. So those who have faced hospital visits, they may be knowing that when you put this cannula for any fluid transfusion to your body, after some time you come to know that whether the cannula has gone to the right vein or it has gone out of the vein. But this cannula has a feature by which when the medical professional is inserting it into the vein, they can find out whether it has gone to the right place or not. It has a very small tiny hole at the front, by which when they are inserting it, they can get a small color of blood. So when they get that color, it means it has gone to the right place. Actually, it is the blood which is coming out of that small hole. And because of these small metallic features, it cannot be sterilized by any other process. So this is one of the major product that we are sterilizing. There are several variants of this, and this is also being exported to various countries. And before our facility came into operation, this sterilization was being done outside India, and now we are happy to say that we are able to do it in India. So this is our LINAC 3, 10 MeV, 10 kilowatt LINAC 3, which has been installed, as you can see here, in a vertical configuration at an industry which is Microtoll Sterilization Private Limited, Bangalore. So the purpose is to test, do the trials and technological skill performance studies of our LINAC. Because the LINAC, when we operate at ARPF or at our labs, it is operated by our manpower, which is trained manpower, and we can anticipate the failures, or we can see the symptoms of failures, and we can also quickly regain the operation in case of any problems. But here the machine is to be operated by industrial manpower, so the real robustness of the machine will be tested, and also how long we can keep into operation before it trips, that also has to be tested. So for last 2 years, we have had very intense work on transferring this machine from RRCAT to Bangalore, because transferring a machine of this complexity and the very fragile components, including klestrons and thyratrons, electron gun, all these things. So this has been quite a remarkable experience for us to learn. And we have successfully transferred the machine, installed at a private industry. Then we commissioned the machine. Then we have got a type approval based on the testing. So AEW team visited the facility for 5 days, and we operated the machine in front of them for 5 days. After that, we have qualified the machine using installation qualification, operation qualification, and performance qualification procedures. So these procedures typically demand that you irradiate phantom boxes initially, and then you irradiate actual products through detailed volumetric dosimetry. And using all these procedures, we have qualified this machine. And now, since the FDA has the first such machine in private sector, so they have first given a license to on a trial basis, we have to sterilize some products. So this company is now sterilizing the products on a trial basis, and also for unregulated products, they are operating the machine in commercial mode. So this has been a real transfer from R&D center to industry. And just to tell you the magnitude of the work, this facility would cost you about 30 to 35 crores. So it's not a small thing. Now we are also working to develop a food irradiation facility at ARPF. So here we will have a different type of industry interaction, because the people who will be coming to get the services, they are from food processing industries. And the basic layout is having two LINACs in opposing beam configuration. So the product is passing on this conveyor, and we have a set of LINAC on this side and set of LINAC on this side. So this set consists of one 10 MeV electron LINAC and one 7 MeV LINAC, which will deliver the X-rays, because we don't have enough confidence on our structure that we will be able to get 10 MeV and 7 MeV in a controlled manner from the single structure. So we have put 2 structures, but the backup system, RF powering system, is one. So while passing through the interaction zone, the product will get the required dose in one pass. The difference between medical devices and food products is the food products are typically low dose and high throughput. So for example, when you see the medical devices, the throughput will be typically few hundred kilograms per hour, or at the max 1 ton per hour. Here the throughput we are targeting is 40 tons per hour. So 40 ton per hour is typically if you see a full, now you can see double or triple XS trucks. So they load typically 10 tons of onion on the full big trucks. So 4 such trucks we have to process in 1 hour. So that is the type of processing we are targeting. So in this facility, we do not have the elaborate arrangement to unload the trucks, but we will demonstrate this throughput on per 1 hour basis so that we prove this design. And when we replicate the food irradiation facilities, we are able to aim even higher throughputs. So here in the bottom frame, you can see the electron beam, how it is being shooting on the product. So from 2 sides it is shooting and the product is going through in between. And this is the local shielding to prevent the equipment being damaged from the intense radiation. So the radiation here is the highest that you can get from any machine in India. It is an extremely high radiation, and in a very short time you may end up burning all your equipment with the radiation. So that also we have to take care. So all these sensors and all electrical systems have to be very specifically designed that they operate reliably in
Sir,
very high radiation.
5 minutes, please.
Right. So now we are working with an industry to install a facility in the industrial domain for medical sterilization. And these are, here you can see these are 2 horizontal machines. The processing throughput is typically 15 megagram per ton per month. And this facility, we are in this work is in initial phase, and we are working through ECIL on this facility. Now we are hoping to multiply these E-beam facilities through an arrangement with ECIL and industries, for which our AIC Pi Hub is also working with us. This is the Atal Incubation Center. This is our incubation center, RRCAT. And one important thing is that we have to have low cost Indian solutions for everything, for components and services, including Indian clistrons, because with imported clistrons, we may not be able to work in the long run. And other things are also have to be Indian, including the consumables that are used in the electron beam. So for EPR dosimetry systems, we are working with BRC, and now we are working to indigenize all the remaining items. It is a very unfortunate part that we don't have a klystron in India, though we have been trying for more than 30 years. And now we have to take lessons from the type of responsibilities we gave. And now we are facing the pain of this. After having done all this development, we are facing the pain of trying to develop the klystron in a short time. This technology can also be extended to other areas, including radiotherapy applications, where beam energy is required to be 4 to 18 MeV. In fact, Chairman AEC has several times asked us to extend this application of this typical LINAC to radiotherapy machine, and we will try to do this in 2 or 3 years of time frame. Then LINAC for imaging and radiography in this energy range is needed. We have several inquiries. We are not able to fulfill them. Then we are also working on development of high power recirculating accelerator with solid state amplifier. So this will obviate the need of a klystron. And as Larji has explained, we have a very good capability on solid state amplifiers. This typically works at 108 megahertz frequency. Then the new technology which is coming is very high energy electrons for flash radiotherapy. So here a distinction is made that the differentiation is on the base of dose rate. So cancerous tumors cannot sustain a dose at a very high dose rate, but our normal tissues can bear it. So, and this particular mode has several other advantages, including a very short time for the therapy. So we should keep an eye on this and develop it as soon as our resources permit. Now, this is not clear to many people what is the role of industry. So R&D outcome is uncertain, so the R&D setup is devised in a manner in which we have to have transparency, scientific rigor, and very strict rules for public fund. However, when you go to industry, transparency is, they will not even permit you to enter into their premises. Transparency is contrary to their business interest. So we have to have a system where we can convert the knowledge that we have generated in R&D centers in economic and strategic benefits. So there we need industry, because industry survives on product performance, customer satisfaction, and cannot be loss making. Therefore, the industry is more outcome driven and timeline sensitive. And therefore, the industry develops expertise to carry out product centric activities. So when we work with ECIL, we have to keep in mind that they are in industry and they are not in R&D institute. So we have to provide them all the documentation in a form which is suitable for industry for product centric manufacturing. If we do this, we believe that ECIL will be able to make our machine a very short time frame. And if we start treating them also like an R&D institute, then the whole thing will fail. Now, when we work with industry, what are the challenges which are uncommon in R&D in our setup? So first of all, we have to change our approach to win the confidence of industry. We have interacted with a lot of big industries, and their common complaint is they are not sure that whatever we are claiming, whether our equipment performs to that level. Probably a lot of false claims have been made in the past, and we are feeling the pain. So we have to go through the pain of bringing them here, demonstrate our machine by 2 or 3 days of continuous operation, and then they start believing that this team is telling the truth. Then our work culture, they often taunt us on saying that on Saturdays, can you respond to our phone calls? On Sundays, can you respond to our phone calls?
I'll request you to kind
just 2 minutes.
Just of time.
Then we have to have a risk management plan, the premature failure risk, because sometimes in some of the systems where we have not done enough work, we cannot transfer that premature failure risk to the industry, and they have a very tight expectation about the time frame. They are expecting that we will be able to do full facility including Linux within 20 months, and which is, by our best estimates, it is a factor of 2 shorter than our imagination. Then we have to go through a large number of iterative developments, and all these things you can read later. They are not expecting any costly solutions when we claim that it has been developed in India, because they understand, they are in this business, they understand that what truly make in India means. So all imported components have to be removed. Any import will be a path to failure in this type of work in the long run. We can manage in short run. This is a typical model that we have developed. You can see it is a complex model, how from an R&D center through our incubation center to ECIL and to the user industry, and there are some contractors which this industry will be directly engaging. So this is the typical model we are working with. And here you can see the preparations that we are making. We are making in-depth preparations to work with the industry so that we transfer this technology in a very reliable manner. And we have exhaustive documentation behind this, and we are still working to on these things and learning from all these new experiences. So in summary, RRCAT has developed technology for electron beam radiation processing to a level suitable for introduction in industry towards gradual commercial gains, because this is the ultimate aim of R&D in any country. So commercial, it includes strategic gains and also technological powerhouse. Industrialization is a necessary step to accrue the benefits contemplated while supporting R&D of e-beam technology in the country. Several other opportunities for applications of Linux and e-beam technology also exist. RRCAT is making in-depth preparations to enable Indian industry to establish e-beam facilities in line with Make in India and Atmanirbhar Bharat. AIC Pi Hub is participating in this work. technology of such complexity and scale is being handled for the first time for incubation and technology transfer activities. Challenges still exist, and we have to focus on resolving them in next 2 to 5 years time frame. Thank you.
Yeah.
Thank you, sir, for such a nice talk on a very important subject, covering all aspects and taking this technology to this level. Maybe
Chairman,
a few questions.
Chairman sir, Sanjay Malhotra, good morning. Online, I am online there. I have typed one question.
Please, sir. Please, Sanjay.
Chairman sir, you are very well associated with the development till today and aware. First of all, I wish to congratulate Jishnu and mainly the team around him who have taken this technology right up to the industry level. They have achieved much higher they have achieved, and this is the right model of working. We must not jump the gun and declare a product to be complete till it is we know that it has been suitably tested. Test benches is the backbone and the host rock in a way on which we should take this development forward. And my question is only he is developing a ECL, that is also the right institute to get this developed linear accelerator. Only thing is that there are still major parts which needs to be indigenized, and we should make a form. A task force is already formed by Director BRC himself is monitoring this progress, and we must join hands to do this Clystron. There are mistakes in the past. We will not go into that, but we should take it forward. One technical question was how the energy modulation takes place in the 15. Do you actually detune the cavities while running that, or do you play with the energy from Clystron?
Energy modulation for the purpose of getting 7 MeV?
Yeah, lower energies, how will you, or
Yeah,
you,
so
do
we
you
have,
drive it?
so we have a separate structure right now. We can reduce the energy to some extent, but we are not sure about the energy spread at 7 MeV. Because at 7 MeV, when we convert this electron beam to X-rays, the danger is lurking nearby because the tantalum has a threshold of 7.56 MeV for gamma in reaction. So we have to be below 7.5 MeV in any case. So we are right now going with the structure, separate structure, which has less number of cavities, and probably we will also be able to use higher beam current and have some gain in beam power that we have not yet tested, but that is what we hope. So we will use two separate structures.
Okay. Okay. Thank you, Jishnuji, and congratulations once again.
Thank you.
One more question. Okay, let's.
So I have a couple of questions. First is, sir, you were talking about customizing this LINAC for use in radiotherapy in the future. But here it is basically what I see is that constant power, single energy, whereas in radiotherapy you have multiple energies of electrons as well as photons, 6
Right.
MV, 10 MV, 15 MV. So whether this multiple energy beams can be extracted from this machine, this is one question. And second is, you are talking something on flash radiotherapy. What is that, and what is that advantage of that, sir?
Yeah. So we can get multi-energy beam. There are the typical way for the traveling wave LINAC is you use two structures. So you split this one accelerating structure into two. So you get part of the energy gain in the first one and part of the energy gain in the second structure. And now you can change the phase of the field in the second structure, which will determine whether you are accelerating or decelerating the beam. So using the combination of these two structures and a phase control, you can get large variation in energy. This is typically done. This is already well known. So the electron radiotherapy LINACs, if you see the radiotherapy LINACs, there are two principal varieties. One based on earlier variant design, which were standing wave type, and second one Electa, which is still in operation. Probably you also have some in Indore, which are based on traveling wave design. So this is a well-known technology. And flash radiotherapy, because when we get radiotherapy for treatment of cancer, the biggest problem with any therapy is the collateral damage to tissue nearby. And there are various attempts to reduce the damage to the tissue nearby. And it has been found that the normal tissue can very well tolerate a dose if it is given a very short time. So the time scale which they talk about is in milliseconds. And the one advantage also is the total therapy time is also reduced. So currently if you go for typical cancer therapy, they will give 60 gray of dose, 60, 70, 100 gray depending upon the tumor. And this dose is given every sitting you get 2 gray. So you have to be there for 30, 40, 50 sittings. In this case, the number of sittings will also be much reduced. And the damage to collateral damage to the nearby tissue is probably very small as compared to the present day technology.
Vediji,
Thank you, sir.
I would like your comment. I mean, from your presentation, we see there is requirement to go to higher powers. There is problem with klystrons. In the previous presentation, we saw so much of infrastructure set up for superconducting RF. So suppose, like we have seen wavelength shifter now working with closed cycle refrigeration. If superconducting cavities can be made with closed cycle refrigeration, would that help in industrial deployment of high average power?
Yes, of
Because
course.
in India, unfortunately, superconducting electron beam from an superconducting cavity is still quite a few years away. So should that be taken up as a possible activity with a closed cycle refrigeration?
Right. So I think in electron beam using superconductivity, there is no challenge from accelerator side. Challenge I think is from cryogenic side, because in an industrial facility, you have to have a cryogenic plant of a very manageable capacity. So various laboratories across the world, they are trying this, and they are trying to, there is no challenge in accelerating the electron beam. People have accelerated powerful electron beam in superconducting.
Like MRI, closed cycle refrigeration, if they can do.
See, the challenge is in an industrial facility, you can keep a small cryogenic plant. So that is what is the challenge. So people are trying already. Several laboratories are trying. And it is an expensive business for us if we have to try. So we are poor country. We have to do things which we can manage with our present resources.
Thank you, sir. Thank you. Thank you for the excellent talk. And please, sir, I think you, please, sir, I think let's have the honor offer you memento from InPAC 2025. I'll say this is an excellent work, and thank you very much for making us all proud as a community. Continue the good work. All the best wishes. Thank you. Sorry, we have exceeded our time, but the talks are so interesting and so it is very hard to cut down. So now we move to the third talk, which is also on a very important program for the department. It will be delivered by Dr. Mangesh Borge. May I request him to kindly approach. Dr. Borge is an outstanding scientist with the RRCAT, and his main area of work has been power converters for particle accelerators, which is so very important field. And he has won number of achievements and awards, starting from his university to getting Homi Bhabha Award at BARC, then Scientific and Technical Excellence Award, and other several DAE awards. And he has a large number of publications. So let us
Thank you.
request.
And I'll try to save upon some time. Thank you.
Please, sir.
Thank you.
Thank you.
So good morning all. The topic is in front of you. It is an update on high brilliance synchrotron radiation source, HBSRS, and we name it as Indus 3 just to signify the succession to Indus 1 and Indus 2 synchrotron radiation source, which are prevailing and operating as national user facilities in round-the-clock mode. So in the inaugural session, we heard the dignitaries mentioning about the significance and the importance of this particular program. In fact, the need to establish this high brilliance synchrotron radiation source has been deliberated upon and has been discussed at various forums and various levels. It is in the recent past that the efforts have been intensified and the activity has gained significant momentum in the past few months. So what I will do is I'll try to touch upon the various developments in the recent past, and I am presenting on behalf of the entire project team. And as our previous speaker mentioned, that it crosses across different groups of RRCAT through the thin boundaries. So I've not mentioned explicitly all the names. So I'll try to start from where we stopped during the INPAC 2023 presentation. So in this talk, we discussed about what is the need for HBSRS and what are the scientific possibilities about with the HBSRS in India. Of course, in the afternoon, we have a detailed talk which will give a wide spectrum of scientific possibilities with the high brilliance synchrotron radiation source. Then as compared to INDUS2, what would be the salient features and specifications of the INDUS3? What would be its layout and parameters? What would be the challenges and the scale of technologies? How INDUS3 or HBSRS will help in industrial R&D in India? And what would be the role of Indian industry in constructing the facility? What were the readiness for the project and what would be the way ahead? All these points were covered in the previous topics. So we take forward the presentation from that point. And as I mentioned, the activities have significantly intensified in the past, in the recent times, and this is aptly reflected in the number of in the form of the statistics, which shows the number of papers on HBSRS at INPAC. So the numbers have increased threefold. So in this talk, I'll cover, and I divided my talk in four broad categories, and I'll briefly touch upon the updates on machine and lattice evolutions, and updates on the initiative towards the component design, initiative towards the capacity building, and the other initiatives. And through all these papers, the majority of the first two aspects have already been covered in this very conference in the previous 2 days, and in the remaining 2 days, some of these will be touched upon. You all must have already visited the posters, attended to the various contributory and oral posters in this, and I'll just try to kind of concatenate all these, not all these, some of these representative developments, and I'll also be touching upon towards some capacity building and other initiatives. So I begin for the sake of connection with the INDUS1 and INDUS2 facilities at RRCAT. The fact that these two facilities, INDUS1 and INDUS2 at RRCAT, have been designed, developed, commissioned, operationalized, and upgraded. We heard Tusharji mentioning about the various upgrades through the indigenous efforts, in fact, has led to accumulation of a vast knowledge base, expertise, and experience in all the technical fields and the scientific aspects of this project. And in fact, this fact is the, I would say, the backbone and the main facilitator in aiming for a challenging project like INDUS3. So while INDUS1 and INDUS2 are serving the needs of the Indian research community very well, with 20 operational beam lines on INDUS2, 7 on INDUS1, with nearly 140 universities, researchers from 140 universities, research labs and institutes and industries. About 20 pharmaceutical industries are doing their experiments, about 1,000 user experiments annually, with bringing about 200 research publications in peer-reviewed journals internationally. The these facilities experiences certain limitations to fulfill the contemporary high-end experimental needs due to their limited specifications, and these are essentially related with the inability to focus on the submicron spot size, low flux to do the macromolecular crystallography with high throughput, and low brilliance making the time resolved measurements difficult, non-availability of high energy photon making the X-ray penetration in structural materials very difficult or poor, and relatively poor imaging resolution due to low coherence fraction of the source available in this source. So, but there has been a growing interest among the Indian researchers and industries, and the new SRS with significantly better performance in terms of energy and brilliance of the synchrotron radiation has been the need of the scientific and industrial user community within India. And if we take a stock of what is the scenario of the such new sources which are called as 4th generation synchrotron radiation sources in the world, we can see that there are few operational sources around the world. Some of them, I mean, they have been operationalized recently. There are few sources which are in the advanced stage of construction and commissioning, and a large number of sources which are already in the planning stage, and or they are, even some of them have already started their upgradation process. So therefore, the time is perfectly ripe to take forward this proposal to establish industry in India with the parameters of 6 GeV, 150 picometer rad. Just a brief comparison of the salient parameters of INDUS2 and INDUS3. INDUS2 is a 3rd generation synchrotron radiation source, and INDUS3 in contrast will be the 4th generation synchrotron radiation source with a stored electron beam energy of 6 GeV, stored current of 200 milliamperes, and the emittance below 150 picometer rad, which is a way small as compared to the emittance available with the INDUS2. Similarly, for the peak brilliance, it is orders of magnitude higher as compared to the INDUS2, and so is the maximum photon energy available from the source, which will be roughly 4 to 5 times higher. And this is achieved with the smallest spot size, again much smaller as compared to what is achieved in INDUS2. And the salient feature of this facility would be that the machine will be operating in the top-up mode of operation, where the current remains almost constant, in contrast that the INDUS2 operates in a decay mode, where that is once filled, the current decays with the time, and the number of beam lines of course will be higher in INDUS3, and the major emphasis and the major distinguishing factor that the number of beam lines which are available on the insertion devices will be far more larger as compared to the INDUS2. Of course, therefore, the machine is significantly large in dimension. The storage ring circumference, it will be approximately 960 meters as compared to 173 meters of that of INDUS2. Now let's coming to the updates on the machine layout and the lattice evolution. Before that, let's have a quick look at the layout of the proposed facility. That the pre-injector to this facility would be a 500 MeV LINAC, which will inject the electrons at 500 MeV through this LINAC to booster transport line, and the energy of these electrons will be ramped up to 6 GeV in a booster synchrotron whose circumference will be of the order of 960 meters. Please note that the booster synchrotron and the storage ring are planned to be housed in a concentric manner in the same shielded area to save upon the cost. And these 6 GeV electrons are then injected in the storage ring through this booster to storage ring transport line, and they are accumulated up to a current of 200 milliamperes, and the current is maintained 200 milliamperes within plus or minus 0.1% to provide the synchrotron radiation from the bending magnets as well as the insertion devices to the various user experiments, and the storage ring will be of the circumference of the 960 meters. So earlier, what we call as a version 1, we designed this storage ring. This storage ring is designed on the principles followed based on the hybrid 7-band achromat design. Here the number of major magnetic elements are shown, and they have been shown with the different colors, and it contained 224 dipoles. And these dipoles will be of the major homogeneous field dipoles, and some of the dipoles will have the strong quadrupole gradient also, and few quadrupoles and sextupoles, and lot of other magnets also. Now while this lattice was perfectly workable, it had a few avenues for improvement, that the dynamic aperture for the desired for the off-axis injection into the storage ring was less than 10 millimeters. Being a compact lattice, there was a very little space to install various engineering and diagnostics components. So working upon these avenues for further improvement, the version 2 of the lattice has been prepared with extensive deliberations and interactions between various stakeholders of this facility, and the primary focus initially was to adjust the drift lengths between the magnets to create the space essential for engineering components. Here we have to take into account every single millimeter of the component dimension. So the people had to really work upon the preliminary designs, predict what would be the dimensions of their component, and try to accommodate those components, or if required, adjust the drift lengths. In fact, we had to optimize certain components and try to combine the certain components into a shorter space. So that was a very long and very interactive optimization session. Now, to improve upon the performance of the storage ring, the longitudinal gradient bending magnets have been incorporated in this. So here the dipole magnets were homogeneous field. Here the dipole, some of the two families of the dipole magnets will have the longitudinal gradient. This was essential to reduce the sextupole strength, and in association with the antibends which are introduced in some of the quadrupoles, they helped to reduce the emittance further. Of course, the central dipole, that is the dipole here just shown in the blue color just over the number 15 at the position of 15 meter, was considered to be a high field of 0.65 Tesla to provide to use it as a source of synchrotron radiation. Again, recently a few upgrades to this lattice has been done, and there are, of course, there are no changes in the dimensions of the ring, but the optimizations focused mainly to optimize further the synchrotron radiation characteristics, to ease out the injection and improve the lattice performance. So, for example, the central magnet which was here, which was a 0.65 Tesla, now has been modified to be a high field superband with 1 Tesla. For example, this was the central BM4 magnet. It has been split into which was a DQ magnet. It has been split into 2 small DQ magnets on the side and 1 purely dipole of 1 Tesla to improve upon the flux as well as the energy that would be available of the synchrotron radiation from this bending magnet. Similarly, in the straight sections, the beta values have been reduced to improve the brilliance, and to facilitate the efficient beam injection, the injection straight section has been made little longer of approximately 8 meters. Please note that the other straight sections, all other straight sections are of 6 meter dimensions, 6 meters in length. So this is the version 2.1, and this essentially is now the baseline lattice for our design. Now, when we talk of the booster synchrotron, the primary requirements or the design avenues for the booster synchrotron are to have the high dynamic aperture. First of all, to accept the electrons with specified energy spread from the LINAC. Similarly, we have to keep the emittance of the electron beam at 6 GeV, typically low and typically less than 10 nanometer rad for injection into the storage ring without creating much oscillations so that the users don't get affected with this beam. So with all and these such information, this and of course we have to have a high tunability in the machine to perform certain initial commissioning experiments and initial injection trials, ramping trials, and all those things. So these the earlier version with this photo lattice has been modified or has been changed to double band achromat lattice, and that this has enabled us to achieve the large tunability for initial commissioning, as I mentioned, dynamic aperture and reduced sensitivity to the injected beam perturbations, because this lattice provides the DBA lattice provides longer straight sections as compared to photo, so the injection angles are small. So the sensitivity to the beam perturbations are less. Of course, some studies such as sensitivity to linear errors, power converter tracking errors are in progress, and DBA lattice, as I know, is bit inferior or bit problematic as compared to this, but fortunately the physicists have suggested that the solutions exist and the number of solutions exist, so this should not be a problem. We heard yesterday that about the development or the design studies on the LINAC part of it. And the LINAC essentially is a traveling wave constant gradient LINAC, and it has 10 accelerating 4 meter long, roughly 4 meter long structures. Now, this LINAC energy has been changed from, say, from 200 MeV from version 1 to 500 MeV in version 2 to increase the instability thresholds and reduce the scattering, but it offers a lot of advantages from the technology perspective, that the dynamic range of the power converters and the RF cavities is significantly reduced, and the eddy currents in the vacuum chambers, and similarly the effects of the remnant field at the injection because of the increase in the ratio of injection energy to the extraction energy is higher, that is increased, and this choice has been in line with the other sources like APS-U and HEPS. Okay, so of course in the afternoon we'll speak, Dr. Tapas Ganguly will speak a little more well in depth about this, but the brilliance curves has been calculated considering different insertion devices, and you can see that the peak brilliance is of the order of 10 to the power 22, which is comparable with other 4th generation sources such as ESRF, EBS, or APS upgrade. With this, let's come to the initiative towards the components design. And when we talk of a machine of the complex and of the order of industry, it involves essentially several technology domains, right from the magnets, power converters, vacuum chambers, RF systems, diagnostics, controls, making of constant gradient accelerating structures, doing efficient radiation shieldings, developing beamline components for high thermal load, achieving tighter alignment tolerances, and other associated infrastructure, cooling systems, vibration controlled, and controlled ambience are also important aspects. So just a few illustrative examples. This is the design of the storage ring vacuum sector has been established. This figure shows the layout, and this is the 3D CAD version of this. It was a very intricate design because of certain very long list of design constraints such as low thickness, narrow aperture chambers, and these chambers are fairly long, and we have to make precision manufacturability, ensure the manufacturability, maintaining the tolerances. You have to design the chambers to keep the impedances low, maintain the structural stability, make the provisions for in situ bake-out, and of course ensure the feasibility of the assembly in the densely populated unit cell. For example, here I am showing one such vacuum chamber which is CH2. Here it is CH2, and this single vacuum chamber essentially is placed within three magnets, that is the dipole magnet, quadrupole 3 and sextupole 1. So the structure is, structure is a quite complex, and you have to provide different cross sections at beneath all the three dipole magnets. And besides the pressure simulations and the other thermal simulations, structural analysis have already been done, and the deformations under the atmospheric loading have been found out to be insignificant or well within the acceptable limits. Now about the magnets, I mentioned about the dipole quadrupole combined function magnets. It has a lot of advantages. It provides few beam dynamical benefits, such as enhancing the beam stability or reducing the emittance, and they are in fact essential due to the to make the compact ring, and lot of by combining this by making this combined function magnets, we are able to realize essentially the crowded lattice of synchrotron radiation, and less power consumption, lightweight and reduced cost are of course are the advantages. So you can see that this is basically an asymmetric structure, and because of this asymmetry, lot of magnetic and this magnet is bound to have certain deformations under the electromagnetic forces, as well as due to the self weight, and iterative design simulations and calculations have gone into it to keep the deformation of the pole within 12 microns, which essentially keeps all the multipoles also within the acceptable limit of 400 to 500 ppm even under the deformed states. Now, but in place of the homogeneous field dipole magnets, the longitudinal gradient magnets, where the magnetic field from one side to the other gradually reduces from say 0.6 Tesla to 0.2 Tesla, needs to be placed, and there are different ways of realizing this. But this particular structure, where the coil is single but the pole gap is progressively tapered, has been designed, and it is this design is worked upon by following both the options of the permanent magnet as well as electromagnet. Right now the electromagnet option is being pursued to essentially avoid the risk associated with the availability of permanent magnets.
5 minutes, please.
Yeah. Now coming to the RF system, we heard the RF system or the system developments for the proton accelerator program. The same division is also responsible for the development of low-level RF system for RF system in general. Whereas there are 20 RF cavities in the storage ring, 4 in the booster ring, and there will be 20 and then there will be 10 stations of 21 megawatt peak for the LINAC system, and all these systems need to operate in the perfect synchronism, and therefore low-level RF system plays a key role in that, and digital low-level RF system has been developed, and certain prototypes boards have already been developed. The power converters for electromagnets, basically they are essentially very large in numbers, and to facilitate their development in a very efficient manner, developmental activities towards the digital controller for power converter have also been initiated. And of course, with they have the host of advantages which are associated with the digital technology. But more importantly, they standardize the design from the project perspective, and they offer the flexibility to adapt to different kind of application areas. In addition, of course, RRCAT has all the basic infrastructure which is available for necessary for realization of these components and their qualification, but there have been certain initiatives to enhance the capacity. For example, recently to complement the old 3-meter CMM, a 5-meter CMM with probe positioning errors within micron size have already been operationalized, and this is in addition to the already existing lot of characterization facilities which are available at RRCAT. The vacuum chambers being thin and narrow and long, their vacuum attainment is conductance limited, and therefore here we have to have the the vacuum chambers have to be neck coated. The existing facility with 1 meter long solenoid which is capable to do the coating for the chambers up to 3 meter has already been existing, and to complement that a facility for longer 6-meter chambers has been initiated, and the works, the designs have been completed, and various works such as the design of a 6-meter long solenoid and the engineering design of the entire facility has already been completed, and works have been initiated, in fact, towards the development of this. This slide shows the application of concept of induction brazing as an alternative route for the expensive brazing furnace to make 3.8 meter long accelerating structures. Here there is in this direction a 100 kilowatt induction power source has already been commissioned, and the trials for the induction brazing on a similarly looking workpiece has already been completed, where the temperature attainment has been demonstrated. Presently, RRCAT has the power converter test facility up to 20 kilowatts, but understanding and realizing the importance that every component that goes in the machine has to be qualified a priori or beforehand, we have to augment the multidisciplinary test facilities, wherein these these components not only are tested for their own performance, but they can be tested for their integrated integrated with some other components. That also has been carried out. And finally, on the some other initiatives, so since we are in the planning stage for the project, we are pursuing various activities like defining what are the activities, sequencing, development of schedule, planning for the quality management, resource management, and all the project management aspects. But essentially, the creation of the work breakdown structure is the first part of it, and we have already embarked upon it, which is a hierarchical decomposition of the total scope of the project team to accomplish the project objectives and create the required deliverables. So essentially, if you see the top level work breakdown structure for Industry project looks like this. So Industry, it has project has been broken down into 4 verticals in the second level. The first is about the strategies, planning and coordination, which covers the global planning and management aspects from the conceptualization to the realization of the project. Second work element talks about the development of the accelerators and the storage ring. Third one talks about the beamline. Fourth one about the infrastructure, which covers the establishment of necessary engineering and IT infrastructure for the facility. As a representative, for example, if we dissociate this, decompose this work elements further, for example, in the strategies, planning and coordination, you could have the development of the science case, which has already been done, designs already have been done, reviews are in progress, statutory clearances, we are in fact initiated activities towards that. Project management, yes, we have initiated activities towards that. We have to plan for the installation, integration, operation management, and training and outreach. And similarly for, if we break down it further, then for example, in the storage ring as an illustration here, we have to cover all these aspects, and in the project management, right from the schedules to the procurement management and risk management, everything needs to be planned. And these have been identified as the work elements or the work packages. Of course, I have illustratively shown this, but it, of course, I mean, has been, in fact, with the help of all the stakeholders, it has been broken down into further levels. You can see that this is the what is known as the work breakdown dictionary for the storage ring magnets, which shows what is the WBS level, what is the WBS ID, what is its name, description, quantity, and in fact, it will have more columns, like what would be the quantity for the foundation, and responsibilities, resources, what would be the dependencies. It will also provide the schedules and milestones.
Okay.
Yeah.
Request you to kindly continue.
1 minute. So now, since the accelerator facilities, or particularly such kind of big accelerator facilities, are conceived typically by one generation, executed by the third, and operated by the with next generation, the continuity of the knowledge is important, and from that point of view, the documentation management system, we are already initiated the developments wherein this documentation management has features of categorization of the document, version control, storage, organization and retrieval, several approval procedures including review and revisions, access privileges and audit trails. And for the categorization of the documents, we have defined certain classes, certain types, and certain activities so that the documents can be easily numbered and categorized for further search and this thing. And finally, about the project management framework, a task force has already been constituted, and it is looking at the various aspects of the project management, such as study of project management principles, what are the systems which are implemented in other Government of India projects, and generating the requirements of the application softwares, defining the processes for quality management, risk management, earned value management, issue management, etc. And its first report is expected in 1 or 2 months. Finally, about the site or the land which is required for the project is already available, which is technically suitable, which is approachable. You can see that it is approachable from directly from the national highway, and is accessible from this thing, from the Indore and Indore railway station as well as airport. Electricity is available, spare capacity in the for the electricity is available, water supply and infrastructure exist to meet the requirements. So to summarize, the initiatives on the several fronts towards the design optimization, component layout, enhancement of technical infrastructure and project management aspects have already been initiated at RRCAT, and these efforts will be continued and in fact will be intensified. Finally, this work, the entire project team at RRCAT is carrying out under the guidance and leadership of Director RRCAT and Additional Director and Director EAG RRCAT. So therefore, I acknowledge their guidance and of course the contribution and the enthusiasm with which the entire project team, as we call it, is working at RRCAT. Thank you very much.
Thank you, Dr. Bhagye, for providing detailed update on this very important upcoming project.
Thank you.
Maybe we can have a few, 1 or 2 couple of questions. There are. Yes, please, sir.
Yeah.
Compared to Indus 2, when you come to Indus 3, any difference in the vacuum requirements, level of vacuum?
कृपया आप लोग हाल में बैठे रहें प्लीज कंप्लीट होने के बाद उसमें धन्यवाद.
Any difference in the level of vacuum you require in the ring? Indus 2 and Indus 3.
Yes.
Is there any difference in the requirement of the vacuum in the ring? Yeah.
No, vacuum is more or less same, 10 to the power minus 9. Indus 2 and Indus 3. It is the same. It is the same. It's only the technology to attain that vacuum has changed.
Is there any more question?
Joshi sir typed out a question. How much is the technology will be homegrown for HBSRS separately? The insertion devices
Technology
and
is moved on.
I'm sorry.
for all three.
You are not audible, Malhotra ji.
Can you please, somebody in?
You can
Yeah,
please give the
I have
mic.
typed out the question, sir.
No,
We can.
please. Now the arrangement is made. Please speak out, sir.
Yeah, again.
Okay. Thank you. How much is the technology indigenation for HBSRS and its insertion device and the beamlines?
Okay. So as far as the indigenous portion of the technologies for HBSRS is concerned, the target indigenization of the technology is well above 70%, point number one. And about the insertion devices and beamline components, the insertion devices, as I have just briefly mentioned, and we'll listen to it in the afternoon, they contain a variety of insertion devices such as out-of-vacuum undulators, in-vacuum undulators, superconducting undulators, and the other wigglers and wavelength shifter, etc. Now in this, for example, the out-of-vacuum undulator technology has already been established. Yesterday there was a talk on it. And we are in fact in a couple of years from now will be ready with 2.5 meter long out-of-vacuum undulator. We have already started our works in the direction towards the development of in-vacuum undulators. Right, and as I was mentioning during my presentation about few task force, that the task force for the development of undulators is also being constituted. This is about the undulators, and the third part about the beamline components. Certain beamline components such as liquid nitrogen pooled double crystal monochromator or optics or some other stations, and in fact we have a program for the substrate development also. So with this, we are in fact moving ahead with we have identified indigenization.
Okay, thank you.
Thank you.
Okay, please,
Yes,
last
please.
question, please. Sir.
Storage ring both are concentric electrical circuits. Will there be any effect on the storage ring because of the performance of the booster circuit?
Area is purely driven by the economics. I mean, how much would be the cost involved? Different ring. I'm coming to your specific answer to your question. The trade-off only if your booster ring is significantly smaller as compared to your storage ring, and this option was discussed and elaborately discussed with our accelerator physicist, and to make that small. There will be two type of effects when you consider this booster form. One would be to have the booster foundation to the storage ring foundation. That would rings will be entirely different. So these two there will always be a chance of some pickups on the signals. So a careful layout of the cables is required to be done. But I believe this is possible to be done because it has already done. We have had certain communications with possible. But then, of course, the precaution needs to be taken.
Okay, fine.
Thank you. May I have the pleasure to offer memento on behalf of INPAC2025 to Dr. Porky, please.
Thank you, Dr. Joshi, for conducting this session. Memento to Dr. Joshi.
हेलो
हेलो हेलो आयुष हेलो प्रेजेंटेशन टीम से कोई है? ऋषि, रिंकी मैम, सर का पोडियम टीम प्रेजेंटेशन से कोई है यहाँ पे?
Huh? Huh? Lecture आपका? Look. लेक्चर आपका है?
नहीं मेरे
हेड के हिसाब से करो ना, आपके हेड से, आपके हेड के हिसाब से।
Welcome back to the next session of the technical session of today's program. And to chair this session, I request Dr. Arup Bandyopadhyay to take the chair, come to the stage and take the chair. On behalf of the organizing committee, it is my pleasure to introduce a brief account of the accomplishment of Dr. Arup Bandyopadhyay. And I am sure that the community who are here are very familiar with Dr. Arup Bandyopadhyay because of his immense contribution in the field of accelerator physics, especially at Variable Energy Cyclotron Center, Calcutta. He has obtained his BSc Physics from University of Calcutta, MSc from University of Pune, and PhD in Accelerator Science from Jadavpur University, Kolkata in the year 2008. And as you all know that, or you might have heard yesterday during his presentation, his field of expertise in the radioactive ion beam facility, room temperature, cyclotron, a superconducting cyclotron, and this LINAC and superconducting quarter wave resonators. So in the accelerator physics field, he has made immense contributions. And keeping in mind his contributions, he has been awarded many significant awards, scientific and technical excellence award by DA in the year 2006, group achievement award, several immense amount of number of awards, and he has more than 50 international journal publications and conferences, more than 100 international conferences. And with this brief introduction, I request Dr. Arup Bandyopadhyay to conduct the session. Thank you.
Thank you, and good morning. We are starting technical session 7. We are having very interesting presentation here, but compared to the earlier plan, there is a change. So the first talk will be given by Sri D.P. Jadhav, and I request Jadhavji to come here, please. So Jadhavji is basically B from MIT Muzaffarpur. He's from the 38th batch of the BRC training school. He is recipient of various awards like DA Scientific and Technical Excellence Award 2017. He's a life member of IVS, IWS, and ISPA. He's a member of LIGO Vacuum Review Board. And his area of research is design and development of ultra-high vacuum systems, design and development of magnetron sputtering deposition system, functional coating and metal joining, non-evaporable gators, and sputter ion pumps. Today, he will be talking about design of industry storage ring ultra-high vacuum system compatible with 7-bend acromate lattice. Jadhavji, you have to complete within 15 minutes, and then we'll keep 5 minutes for discussion. Okay, thank you. Please start.
So thank you, Session Chairman.
Pointer, arrow up down.
So thank you for Chairman for my introduction, and it's an honor for me to be here to share my work before this distinguished gathering. And thanks to organizer for incorporating me for this talk within a very short period of time. So some earlier, some other speaker was supposed to be for this talk, but due to some reason, a few days back I got that information that I have to give this talk as a replacement, and I accepted that. I hope that I will be coming at par with your expectation. So this title of my talk is Design of Industry Storage Ring Ultra High Vacuum System compatible with 7-band Acromat lattice. So outline of my talk is introduction, followed by need of UHV condition, design requirement or proposed design solution, experience with industry, and followed by conclusion. Yeah. So already earlier speakers explained about this broad layout of this industry facility. Just for the sake of completion, that this industry 4th generation synchronous radiation source with 6 GB and 200 milliampere specification, having this horizontal emittance of 150 picometer rad and peak brilliance of around 22 photons per second per millirad square per mm square for 0.1% bandwidth. And proposed beam lines, 50 beam lines are proposed. It's 25 for IDs and 25 for this bending magnet. So here you can see that there are this super band of this machine, this storage ring. It is having 35 magnets per this band, which is 11.25 degree. So it will be rotated 32 times to make the entire circumference of 960 meters. So this total out of this length of this each super period is 30 meter, and breakup is that bend portion is around 24 meter, and straight section this 6 meter. You can see 3 meter this side and 3 meters. So if it is rotated, then it will have that 32 bend sectors and 32 straight sectors. Those straight sectors will be utilized for various regions apart from these IDs, like incorporating RF cavities, that injection straight, etc. Okay. So need of ultra high vacuum. This hermetically sealed off UHV condition. This UHV for a beam envelope of 960 meter of circumferential length to minimize the beam gas interaction, and the level of vacuum is less than 10 power minus 9 millibar for longer beam lifetime for the stored beam condition, that is 6 GeV 200 milliampere. So here, for the sake of comparison, you see that industry is having 172.4 meter this UHV length, circumferential length, and industry it is 960 meter. So this is scaled up by a factor of around 5.6. So this coming to this layout of this bend Acromat. So top one, this is magnetic arrangement, and as I told, that's around each this bend achromat. We put gate valves on both the sides, and we call it bend region vacuum sector. So by putting 64 numbers of this sector gate valves, we will have 32 bend regions and 32 these state regions. And here we can see that this bend region, that there are two types of aperture requirements. One is plus minus 13 millimeter, and second is plus minus 7 millimeter in central portion. So both the sides of this central portion, upstream and downstream, two regions, we call it this high aperture region, and the central portion plus minus 7 millimeter is this low aperture region. In each bend achromat, there are 15 chambers. Out of 15 chambers, these 7 chambers are bend chambers because there are 7 bending magnets, and remaining are straight chambers below other magnets like multipole magnets like quadrupole, sextupole, fast corrector, etc. So this you can see that for extracting this is the ID source point. For extracting the ID SR for beamline, that this ID SR generated here is passing through this chamber sidewise beside the electron region. We call it this keyhole aperture region, and passing through this anti-chamber portion of bend magnet, and again passing through this keyhole aperture of this multipole magnet, and like that it is coming out to the respective front end. And here also this bending magnet, this central portion, bending magnet 4, this bending magnet radiation will be tapped from this central point of this bending magnet 4, and which is again passing through this subsequent chambers, this straight chambers, then next bending magnet chambers, and coming out to this two respective front end. So this is the 3D this CAD model of the same 2D layout which I described. So what are the design requirements for this UHV system? So first is the UHV containment, that beam envelope material and hermeticity requirement. For any this UHV system, that the most important requirement comes in terms of this material compatibility, and then this hermeticity of the joints, different joints like demountable joints or weld joint, etc. So for this material for this containment, this envelope should be UHV compatible with a low vapor pressure and a specific outgassing rate of less than 5 into 10 to the power minus 12 millibar liter per second per centimeter square. Then compatibility with the surrounding magnet. All those chambers should be non-magnetic in nature, that material of the vacuum chamber. Then further requirement comes for the electrical conductivity of that beam envelope material for minimizing the beam coupling impedance. And for a structural requirement, stability against atmospheric pressure loading on these thin wall chambers. It's worth mentioning here that this because of this very low aperture magnet, high strength magnets, that there is hardly any room for the thickness of the beam envelope, and it goes to at some points to the level of around 1.5 millimeter or so. So that material should have adequate this yield strength. This compatibility for this elastic this stability. So and with to be stable against that pressure loading. So that material should have certain this level of this strength. So material compatibility for dissipating high SR heat load that requires this high thermal conductivity material. Around more than half megawatt of power generated by all those, these 32 multiplied by 7 bending magnets will be taken care by in vacuum beam dump. We call it photon absorbers. Because that out of that those produced this much this bending magnet radiation, hardly that bending magnet 4 radiation will be used. Rest we have to dump inside UHV. So that will further enhance this outgassing rate. We call it PID gas load. Then this hermeticity of the joints. This is another stringent requirement for UHV system, that helium leak tightness of all the joints, maybe this welded joint or demountable joint should be better than 1 into 10 power minus 10 millibar liter per second. So proposed design solution is this all metal design. Materials, this 6061T6 for bend region chambers, 6063T6 for extruded straight section chambers, chromium, zirconium, copper for photon absorbers, copper beryllium for RF shielding of SS bellows. Of course, this out of standard SS component like SS bellow, etc., this SS316L will be used. And flange sealing technology, we will be adopting this diamond shape or aluminum metal sealing. That is our own indigenous developed technology. Worldwide, there are two more technologies are used. That is one conflict, this copper-based conflict technology, the conflict plant, and this spring energized, cladded with that this soft material. We call it helicoflex-based flange. Two different designs globally used. In case of Indus 2, we had to develop our own this thing, because those this compatibility issue was there, because we decided to use aluminum chamber, and aluminum chamber it is not possible to make the knife edge, which is compatible for sealing with the copper gasket. So that making the knife edge in aluminum flange is it's not possible. So that we had to decide, we had to develop this particular this diamond shape aluminum metal seal for the this hermetically sealed joints, this demountable joints for both similar and dissimilar metal joint, SS to aluminum and aluminum to aluminum. And joining method we have this chosen for this this GTAW or electron beam welding, because some area we have to use high resistivity material like stainless steel for fast characters. So that will be thin walled chamber that we have to join by using electron beam welding. Rest we can go for TIG welding as we did in case of Indus 2 aluminum chambers. Okay, so this pumping requirement, coming to pumping requirement. So here you can see, as I told, that because of this scarcity of space, this between these poles of this magnet, this hardly this space for putting the chamber thickness. And this inside already we have been specified to have room for this beam up aperture that I described, that plus minus 7 millimeter for this low region and plus minus 14 for 13 for high region. So here you can see this by this aperture, for these apertures, this vacuum conductance that along the longitudinal direction, it is around 0.2 to 2.2 liter per second per meter in the molecular flow, this conductance for these given apertures, because this ultra high vacuum is in that molecular flow regime. So this with this small this conductance, it is not possible to generate the UHV and by putting conventional pumps, and that too with limited space. There is no space to put directly those pumps between magnets, because magnet to magnet there is also no space for putting the pumps. So and there are two types of gas load. One is this thermal outgassing, and second is PID gas load. So PID gas load is, of course, is higher than this thermal outgassing rate. Thermal outgassing rate, I told we have to maintain below 5 into 10 power minus 12 millibar liter per second per centimeter square, that we can control initially. But the PID, which is when the chamber is put in the machine and this photon starts bombarding the surface, then it creates a lot of this dynamic gas load. We call it photon-induced desorption. And this photon-induced desorption yield, it varies from 10 to the power minus 2 to 10 to the power minus 6 to coming to a steady state. Means that initially when we start the machine beam commissioning, that time 100 photons are ejecting one this gaseous molecule from the surface. But when we come to the steady state of minus 10 region, then 10 lakh photons eject one molecule. So we have to reach we have to decrease the 4 orders to come to that steady state level, and then we will be able to store that 200 milliampere current. So right from this beginning, we have to start microampere current, and then slowly we have to reach up to that level, so that coming to that steady state level, we will be able to store that 200 milliampere current with that 6 GB energy. Okay, so proposed pumping scheme. As I told that this longitudinal pumping scheme will not work because of the less conductance. So what is the way out? That then you can see that all the 7 bending magnet, that gives us room to design the chamber by using anti-chamber design. But rest of the multipole magnets, those magnets don't allow to make that anti-chamber, where we can put pumps sidewise. So instead of pumping this longitudinal direction because of the conductance limitation, we take help of anti-chamber, where in the radial direction we through this slit that we joining this electron beam aperture region to this anti-chamber region, and this anti-chamber region we connect all conventional pumps to produce this vacuum. But here in case of INDORE 2 also, this scheme has been adopted for all bending magnet chambers, that this pumping through anti-chamber, that those pumps are put in the anti-chamber. So the same scheme for bending magnet chambers we are adopting here. So but as I told you, this where anti-chamber is not possible. Suppose for example, this ID chamber, this ID gap, we have to go this few millimeter. For example, in this INDORE 2, we have to have around 11 to 12 millimeter we have to go that each side. So from the beam axis, the surface of the magnet, permanent magnet, will be hardly this 5-6 millimeter that gap. So within that, and we cannot put this anti-chamber scheme here, because we cannot have the port to connect those all conventional pump. So we have to go for this NEG coating of this small aperture to counter this problem. And what does this NEG coating? This NEG coating does 2 jobs. Here it reduces the outgassing rate from the chamber surface. I mentioned that the bare chamber surface we can control up to the level of minus 12 milliwatt liter per second per centimeter square. But that much this thing gas coming in this much a small further conductance area, we can, I will come afterward, I will show through the graph that how it is not possible to generate this minus 10 vacuum here. So this NEG coating first job it does is it reduces the outgassing rate. When you put this coating, this we are able to decrease the outgassing rate from the surface from minus 12 to minus 14 region. So because of this, it acts as a diffusion barrier. So from the bulk hydrogen migrating to coming to the surface and desorption, it acts as a barrier. So it reduces the outgassing. So the first benefit. Second benefit it does is that it acts as a pumping it starts pumping when it is activated. Activated is when it is heated to some temperature or a given composition. All the oxide sitting on the surface gets dissociated and it diffuses inside, and this getter material is ready to pump. It getters the getterable gases, and through that it starts pumping. So this is the pressure estimate for this bend achromat region, which is around 25 meters. This around here you can see that in initial this condition where is static condition we call it, this for this thermal outgassing load, when there is no PID. So only for this static condition thermal outgassing, we are able to generate in -10 region with this given pumping scheme. But when we add the PID, then you see that after 10 ampere hour, this pressure profile is like this. So we are going to -7 region. And then when we accumulate more and more current and it clean, I told you that this effect is -2 to -6, means initially this PID is more, but gradually it decreases. And that effect you can see here, that when we go to this 200 ampere hour, that all these peaks come down. So here, corresponding to 200 ampere hour, you can see we are entering in -9 range. And this -9, and subsequently after 1000 ampere hour, we are able to enter in this average around 2 into -9 millibar. So after 100, this 1000 ampere hour accumulated beam dose, average pressure of 2 into 10 power -9 millibar is predicted with 6 GV, 200 milliampere stored beam current. Okay, so a structural requirement, I think previous speaker also that showed this slide. So this as a part of this optimal arriving at the optimal design, as I mentioned that this stability of that chamber against this pressure loading, we have to go for this stress, this simulation and stress analysis and deformation. So here you can see that for this chosen material and the geometry, this stress level and this deformation is well within this acceptable limits. Now the next issue which I mentioned earlier, that handling of the high bending magnet SR heat load, and this you can see that this bending magnet SR that which is produced is proportional to E raised to power 3 energy raised energy of the beam raised to power 3. So in case of this Indus 3, that I told you earlier, that's more than half megawatt of power is produced through all these bending magnets, and around 17.5 kilowatt per bend acromat. And this Gaussian beam, that sigma is of the order of 1.085 millirad, and this heat flux, this Gaussian heat flux, it goes around 600 watt per mm square. Whereas in case of Indus 2, it is around 50 watt per millimeter square. So around 12 times more than this Indus 2 that this heat flux level is there. So we have to design the heat the absorbers accordingly. That this thing. For that, this problem comes in case of Indus 2. I told you that we have used this photon absorber made of OFE copper. That those structure is brazed to have to this entire assembly. And once you braze the this OFE copper, this strength of OFE copper reduces drastically. So hardly in the soft anneal condition, its strength is around 40 to 50 megapascal. And here in case of this level of peak heat flux, that stress level, thermal stress level is very high. That is going even when twice 2 sigma y of this copper. So we should have the high strength material, and that is the need of this for industry. So for this, like other machines, they have used, we have to also go for new material. This high strength material, high temperature, high strength material, that is called copper, chromium, zirconium. And this material we have not used in Indus 2, but in this case we have to go for this material. So this handling of this thermal load, already I explained. It's a typical this this photon absorber we will be putting in the antechamber to take that all this tangentially coming this SR photon. So, and it will take care. Yeah. Okay. I will be fast. Thank you. So another requirement comes is that low loss structure, that beam envelope should be designed such that it is adding low impedance to the circulating beam, and that is one of the key requirement for specific to this kind of machine. So this need of low impedance, a smooth beam passage design, and for that I told you that we have to use this bellow at regular intervals for taking care of thermal expansion of vacuum chambers. We heat during bakeout operation for getting the UHV level, and that time it needs room for this expansion, and that job is done by this flexible members called bellow. And this bare bellow we cannot use because of this impedance region. So we have to give the RF shielding, and that RF shielding should be designed such that optimally, so that it is having the least, it offering least value of this impedance to the circulating beam. Okay. So and the fabrication method I already explained. In case of Indus 2, we have adopted this lip welding of aluminium, because aluminium joining is again a very involved task. So in case of Indus 2, we devised this, we developed this method of lip welding. The same route we will follow in case of Indus 3 also. And this thin walled, this fast corrector magnet that I already explained, that it will be joined by electron beam welding. Okay, so there is a comparison of Indus 2 and Indus 3 component wise. So here you can see Indus 2 it is 426, and in case of Indus 3 it is 3315. So number of component in Indus 3. So our experience with Indus 2. So all these component photographs show that the similar component will require for Indus 2 exception material wise. For example, I told you that photon absorber and beam dump we used OFE copper. Here we cannot use that material, so we have to go for another material. So again we have to generate that recipe of joining that material with SS, flange and all. So that this RF shielded bellow, of course, similar approach will go for. This diamond shape aluminum seal already I explained. Bending managed chamber already I explained. A straight section chamber, as we had one experience. We used this friction welded joint for port. That gave a lot of problem. That we are eliminating in industry. We will not be using this thing, this joint curve. So then this is a taper chamber, which is giving the gentle taper from one cross section to another, which I told you that this high aperture region to low aperture. So it's so that again from beam impedance point of view, that that it should have gentle taper. Then neck coated ID chamber. So these 3 chambers already installed in Indus 2, and we have capacity to coat up to 2.3 meters chamber in house. But for future, for upcoming this Indus 3, we have to go for larger length, around 6 meter length. This recipe of this TI coated alumina chamber, this entire supply chain ecosystem is developed within country for this. Earlier it was imported component. Now right from material to joining, qualifying, everything, that entire recipe is with us, and we can use the similar thing for our Indus 3 also. So in conclusion, experience with third generation Indus 2 SRS as guide for low risk design decisions, UHV sealing, pumping through anti-chamber, etc. I already explained. Large number of customized UHV chamber required for 4th generation HBSRS requires capacity enhancement, like establishing full length solenoid based NEG coating facility capable of coating long chambers up to 6 meter length. Aluminium TIG welding automation for repeatable performance. In case of Indus 2, we did manual way, but here it is not possible. It's a kilometer length welding will be involved. So we have to go for automation for this repeatable performance. Prototyping and testing to prove the compatibility of fabrication cycle for the desired performance. And relevant 3 posters are there in this, so whosoever interested, they can contact or they can refer this these sessions. So they related to this design aspect of UHV system. So collaborative efforts and exchange of related inputs are very much required for evolving the optimal design of UHV chambers. Colleagues of beam diagnostic group of APSUD, magnet design group of AMTD, and beam diagnostic group of ACBDD deserve our sincere thanks for the desired interface inputs. Efforts and engagement of colleagues of UHPTS are duly appreciated for the design and simulation works for design optimization. Thanks to the conference organizers for the opportunity to present this work. Thank you.
Okay. Thank you, Jadavji, for nicely bringing out the requirements and the criticality and challenges of the vacuum system for the next Indus source. So the talk is open for a few comments and questions. Yeah.
Yeah, Dr. Arup, this is online.
Yeah, I can hear.
Come to that. We'll come to Dr. Malhotra. Will come to you.
Okay, thank you.
Can you take the microphone? Then it will be everybody can listen. What is the microphone?
We are saying lot of exhaustive state function and dipole chamber will be quoted.
No, dipole chamber will not be quoted. Only a straight chambers. See, for the pumping aspect, two kinds of pumping scheme we are adopting. We have proposed for this thing. One is through anti-chamber. We are using, we will be pumping with the combination pump called Espatra pump and NEG pump combinations. And in the state region where it is not possible to put through this anti-chamber, that will be coating. Now, your first question that about this, our planning for that. So that all the chambers that I told that our present capacity to coat is limited up to 3 meters. So we have to go for capacity enhancement. That already in the capacity project, this project 94, it is there. We are going to develop this 6-meter facility, and that facility will be available by that time. So that chambers coming from industry after fabrication and clean condition, those chambers will be deployed there for coating and this series production.
Any technology transfer is being envisaged for this transfer of coating to private parties?
See, the problem is not the technology transfer. Problem is that this expertise and the set of members. See, this UHV has not taken the shape of industry so far. So if this investment for this type of system, that return on investment and that to perpetual, that becomes a big question marks. So for that, we should have our own facility so that our project can be, that requirement can be met, and if that subsequent requirement comes, we can offer this facility to private agencies also.
Okay, next, we have an online question from Dr. Sanjay Malhotra. Can somebody give the...
Yeah, Sharmaji.
Yeah, Yadavji, I do understand that there is a... am I audible, Yadav?
Yeah, very much audible.
Yeah, nicely presented. I know that this technology for coating the alumina chambers with titanium to match the impedances has been developed with Midhani, with several vendors at Hyderabad, and you may continue that part. It's good. That needs technology development part. Second, my query here is there are thickness to be optimized for vacuum chamber. You need to have higher thicknesses, since you are telling I have external pressure load and so forth, 1 kg per centimeter. There is, while the thermal stresses demand a lower thickness and the external pressure demands a higher thickness. How have you optimized the same? Although thermal load is not very high, but it is localized.
Yeah, I got your question. See, there are two scenarios. That vacuum chamber, especially this bending magnet chamber, that is not water cooled. So we are not allowing this photon to land on the uncooled surface of these chambers, and the entire this load of this photon, this heat load will be taken care by a water cooled photon absorber made of high strength material. I told that chromium, zirconium, copper. So that this two simultaneous requirement is not binding on that chamber for the thickness optimization.
Okay.
One last question from here.
Hello, sir. Is there any effect of lifetime of energy coating when we go from industry? Because lot of maybe after sometimes.
Is it? See, Sharmaji, I got your question. photon flux is not a problem for us, for NEC. In fact, photon flux helps to maintain its activated condition. It gives a lot of energy to NEC, which initially we give through temperature. So the challenge is to retain the hermeticity of your entire this system, not to allow this leakage from atmosphere. If you are successful in that venture, photon is always helpful for NEC.
Sir, thank you for a nice presentation. You talked about 0.5 megawatt of power heat load.
Yeah.
So this is the continuous amount of heat load that we are going to deposit in cooling water?
Yeah, in a steady state, when we achieve the 200 milliampere current at 6 GeV, in a steady state condition, that time that much level will be there. But before that, when we gradually going up, certainly it will start from lower level.
Okay, thank you.
Good morning, sir. Sir, my question is regarding the monolayer formation time at this vacuum level, 10⁻⁹ millibar. I want to know how it evolves with the electron beam, the monolayer formation time, and with SR losses.
It's a good question. Okay, to some extent I can answer your this thing. See, we have practical experience. We estimated also in case of Indus 2 that this coated chamber came from abroad, and we had discussion with the supplier, and that time it was estimated that in the this -2 say -9 1 into -9 millibar condition, that if you see the spectrum of that residual gases, around 15 for this 80 to 85% is hydrogen, and rest the second abundant gas is CO. So we took that this 20% CO, and it was estimated that how much time it will take this for the monolayer formation, for get surface saturation, as you are saying. That time he predicted that if is your leak-free system, and for that your vacuum is poor, -9 range, then he predicted for around this 5 years or so. But the situation is that we were able to maintain the vacuum better than -9 in continuously in -10, and the chamber which was installed in Indus 2 in 2014 till today, it didn't require any activation. So there is no saturation of the surface. So it has taken that much time and is still pumping nicely.
Thank you, sir.
Okay, we have to cut short here. So Jadavji, please take any further question during the lunch time. And thank you very much for your nice presentation and the information. And I have a memento from the organizers for you.
Thank you, Chairman.
So we'll go to the next presentation, and that will be by Sri Bijendra Prasad. And he's from RRCAT. I'll request him to please come on the stage. Bijendra Prasad ji is he's the head of the Proton Linear Development Division of RRCAT. He's a BTech Mechanical from Lucknow, IET. He has vast experience in the development of proton and negative hydrogen ion sources. He has worked on RFQ, DTL, and SSR. He is involved in the development of biostats for detecting insertion devices. He is involved in the installation, precision survey and alignment of synchrotron machines. He has been project associated of ALICE at CERN in various occasions. He has developed the software package SNAPS for survey and alignment, and he is recipient of 6 DA Group Achievement Awards. I think we'll be listening a very interesting presentation from him. He will be talking about the development of ion sources and low energy proton accelerators at RRCAT. Bijendra Prasad ji, please start.
Okay, thank you, sir, very much for giving me a nice introduction. And good morning to all of you. So my presentation is basically development of ion sources and low energy proton accelerators at RRCAT. I'm presenting it on behalf of this ion source development section that is headed by Dr. Ghodke. And then other part, linear component development section, that is basically headed by Sri G.V. Kane. So both work I have combined this under this proton linear development division. So this is the outline of my talk. This development of ion sources, we have developed multiple type of ion sources, that is multi-cusp cathode arc-based negative hydrogen ion source. So basically we are concentrating on the development of negative hydrogen ion sources. Then RF-based negative hydrogen ion sources, we have developed two negative, this RF-based negative hydrogen ion source, then RF ignited multiplasmatron based proton ion source, and then one pulse DCR rather than continuous, we have developed a pulse DCR proton ion source. Towards development of low energy proton accelerators, we have worked on the 325 megahertz RFQ, 325 megahertz DTL, and presently we are also continuing the work on 325 megahertz SSR. So first I am taking this development of ion sources. So this was the first developed this negative hydrogen ion source, that was the arc-based cold cathode multi-cusp type, and its parameter is to extract the negative hydrogen ion source 50 kV, and then this it was operating at 2 Hertz. It is a multi-cusp type ion source with the magnetic field of the 2 kilogauss, and it was operated at 0.1% duty factor. This was the first one we developed, and with this one we were able to extract this beam of approximately 12 milliampere, but it was 12 milliampere, it was not the complete negative ions, it was along with the electron. So afterward we tried to extract this, isolate this electron as well as negative ion sources, negative hydrogen ion. So for that we coupled it with just before that, I'll give this different parts of this negative hydrogen ion source. So this is the plasma chamber, this one, and then this is showing this complete different parts of this ion source. These are the electrodes. It was 3 electrode based to accelerate the beam from the this extracted from the plasma chamber up to 50 kV, and this was cold cathode for this generation of this arc, and then their multi-cusp, these magnets are there, these permanent magnets for the this confinement of the plasma. So this is showing the extraction vacuum chamber through which we extracted this negative hydrogen ion, and then TMPs were connected to this ports, and then back side is our plasma chamber and then ion source, and this side we connected this our low energy beam transport line. So the next one here it is showing our plasma chamber was on the back side, then it was the pumping this TMP station, and then we connected with 2 solenoid based low energy beam transport line with the different diagnostic mechanism inside to characterize the beam and to measure the current. So to characterize the beam, we used scraper, means like this 4 electrode, this aperture type characterization technique to measure the emittance, and for the current monitor we used the Faraday cup. This was connected with this one, and then to isolate this electron from the co-extracted electron from the ion source, different steering magnets and other things. So ultimately we are able to transmit the beam of around 800 microampere up to the end of this LABT here, measured here. So this was the first one, it was the arc based. Then afterward we switched over to, this is showing the different, this measured current at the end of here. This finally at the end of LABT it was the 0.6, but afterward optimization we got around 0.8 milliampere, that is 800 microampere current, and in between it was, in between the LABT we are getting around 2 milliampere this negative hydrogen ion. Then afterward this we switched over to this RF based negative hydrogen ion source. So we developed two RF-based negative hydrogen ion sources. So rather than using this arc-based, the plasma in this one, the plasma is created by this RF source. So the main plasma is created by this 2 megahertz, and then igniter plasma is 13.5 megahertz RF source. With this one, we are able to extract the beam pulse, negative hydrogen ion, along with co-extracted electrons at the 2 millisecond pulse width, and it is designed to operate at 50 hertz with the duty cycle of 10%. So this is showing different parts of this ion source, and this basically connected with this chamber, and then different parts, it's the igniter plasma, then main plasma chamber, and then other things it is showing. And with this after this basically characterization of this qualification of different parts and components, here it is, just a minute. Yes. So this is our first chamber. First, this is the RF-based negative hydrogen ion source. Here it is this plasma chamber, then high voltage isolator, and then this side we were measuring this beam current and then characterizing the negative hydrogen ion source, but it was still heavy. We tried to isolate the electron, but we were not able to completely isolate the electron beam from co-extracted with the co-extracted negative hydrogen ion beams. So afterwards, but this overall, this total extracted beam current was around 26 milliampere with this ion source. Well, afterwards, then we developed the second RF-based negative hydrogen ion source with a lot of improvement compared to the earlier one, so that we can, just after the extraction, we can install our LEBT and solenoid very close to this just after the extraction electrode. So there this complete ion source is mounted inside with a multiple facilities, even to align the electrode and then change the direction of the beam with respect to LEBT, rather than moving the complete LEBT for aligning of the alignment between the ion source and LEBT. And here we put this like this magnet to bend the co-extracted electron beam to dump at some other places. And here we measure this we put a different diagnostic element like current transformer, then profile monitors to qualify the beam, negative hydrogen ion beam. Afterwards, well, just before that, yes. So here you can see what modifications we have carried out starting from this our multicusp ion source, that's the arc-based ion source, this complete plasma chamber, then high voltage isolator, then vacuum pumping chamber, and afterward our solenoid was connected with the LEBT. Then in the second one, this was RF-based negative hydrogen ion source, then this plasma igniter, main plasma chamber, and then electrodes. So here you can see this voltage isolator and electrode mountings were totally different. Then there has been a significant change in the complete architecture, complete design of this ion source, so that our plasma chamber is here inside, our extraction electrode is there inside, and from here we provided one additional wedge welded bellow here, and then connected this LEBT. So this complete thing we can align with respect to LEBT, so that our extracted beam is in line with the LEBT. Well, LEBT and then low energy beam transport line, and then plasma this extracted beam, so that they can be aligned and then can properly go up to the end of the LEBT. So the this modification has improved a lot with the this one. Well, so after qualification of the first ion source, and then second ion source. Well, yes, after characterization from here, this beam, and we connected this ion source with this low energy transport line. So this low energy transport line basically is having these 3 solenoid magnets, And in between, we are having pumping station, different diagnostic chamber, and at the end also we are having this beam characterization. That's a paper pod monitor to measure the emittance, and then different beam profile monitors, current transformers, and everything is there inside. So with this one, we are able to transmit up to 2.8 milliampere negative hydrogen ion beam up to the end of this LEBT. So from here up, this measured emittance is also compatible with this for injection in the RFQ. So from here, we will be connecting this RFQ to accelerate the beam from 50 kV to 3 MeV. So this is showing the different photographs taken during the characterization of the beam. That is basically for the emittance monitor using this paper pod technique. Then this beam profile monitor, and then current measured at different locations in the transport line. So finally, here afterward from this, we will be adding this RFQ. Well, in the continuation with this ion source development, we have developed these three sources. That's arc based and then RF based ion source number 1 and then ion source number 2. They are basically negative hydrogen ion source. But at the same time, we are developing a high current pulsed proton source. This is basically, this pulsed proton source is required for medical applications. Like suppose we want to use this proton synchrotron for the medical applications or at any other place. So rather than going for continuous like ECR sources, this high current pulse proton source. So for the development of the pulse proton source, we have taken this RF initiated pulse proton source. So here it is RF rather than using this arc plasma. We are using RF plasma to generate the seed plasma, and then afterward, then it's a plasma is generated by the cathode and anode voltage, and then you can extract by using this 3 electrode extraction mechanism and then acceleration mechanism. So this multi-plasma trans source is with this one. This is here it is showing. This is this igniter plasma, this first one, this based on the RF plasma, and then in between inside there is a main plasma, and then we can extract from this plasma this proton ion current beam. So with this plasma source, this ion source, we have been able to extract 85 milliampere proton beam current with the 0.3 millisecond pulse width at 2 Hz repetition rate. So this graph is showing that was mounted measured with the Faraday cup. So this 85 milliampere proton current at 300.3 microsecond with that 2 Hz repetition rate, we have demonstrated it, and it was extracted at 41 kilovolt, 41 kV energy. So then next one, we are also having one PCR proton source. Earlier it was operating in the continuous mode, but we have modified this. It's a RF, and now we are operating it. It's not exactly it can be operated in both pulse and continuous mode. And with this one, we have extracted 10 milliampere beam. That is with H plus, H2 plus, and H3 plus all combined. Well, these are the ion sources we have worked. The next one is the development of low energy proton accelerators. So towards development of low energy proton accelerators, we have worked on the development of 325 megahertz radio frequency quad poles. So initially we made this one radio frequency quad pole before taking up into the actual copper material. We did to qualify our machining process and then design in aluminum, and then afterwards in the copper. So I'll give the status. What is the status of the presently our RFQ? Well, it is 4-band type of RFQ. So most of you all know about RF radio frequency quad pole. So it is a 4-band type of quad pole. These are the showing different this mechanical and thermal analysis. This is the model of this radio frequency quad pole. So it will be consisting of this 4 vane, 2 W type vane and 2 T type vane, and put one over the other. It will be approximately 4 meter long and in 3 segments. So for machining of this RFQ, we have established this high precision CNC machine is working in the controlled atmosphere to maintain the profile, this surface finish, and then dimensional tolerances. So these are the machined radio quad pole vanes. So this is W type of vane and this is T type vane. So after machining this, both the W type and T type, this is the assembly process. They complete how they are assembled, and then we are making this complete radio for RFQ assembly. After assembly, we did this cold test of this radio RFQ by bead pull measurement, and then field profile. After this tuning, initially we got this, and then after tuning it, we got this completely flat field profile. So it is a very good, and it is as per designed by the beam physicist. Well, after this cold test, we cleaned it, and first chemical cleaning, and then afterward cleaned in the vacuum furnace, furnace cleaning. Then after furnace cleaning, we assembled it. This all the 4 vanes, and then assembly. After assembly, we kept in the brazing furnace, and this is the one brazed 325 megahertz RFQ. The first segment of this we have already brazed and successfully brazed with very nice brazed joints without any leak. Then, well, we have already machined the second segment also, and machining of the third segment is going on. So once we'll complete all the 3 segments, we'll assemble with our LEBT. The second work we are doing on the development of 325 megahertz RFQ. So these are the designs, and then already we have made this first. It will be approximately 6 meter long. So first 1.2 meter long this tank we have already fabricated. And for the dip tube lunex, this is under the testing of this dip tube lunex. This is end flanges, and then for this is the structure, complete structure for the dip tubes. It will be made with the permanent magnets. So these are the assembly, and this is our harmonic bench for measurement of for the qualification of the quad poles of this dip tube. And then we are also working on the 325 megahertz single spoke resonator. Well, so after the design, these are the design, and then afterward with this fabricated this die and punch for the forming of this different parts of the spoke resonator. And then first we formed this spoke, took the trial in aluminum, then afterward in the copper. And then after trimming and then other things, these are showing the different process during the fabrication of this spoke resonator in the copper. And then it was in the aluminum, it was fabricated, and then it's in the copper. And afterward we tuned it, this, and in the copper, bead pull arrangement and then measurement. Well, so this part we have qualified already in the copper material. Now next we are going to form in the niobium. So that will be the actual one which will be used for this SSR. Well, so what is the purpose of all this ion source development? And then just 1 minute, this is last one. So here it is, our ion source. This is LEBT. We'll be assembling this RFQ, and then afterward, then beam dump line. And here after 3 MV, we'll be getting 3 MV beam from this complete system. This 3 MV beam we can use. Basically, it will qualify our this RFQ, and then transport line, then ion sources. This can be used in future pulse proton accelerators, even including the proton accelerator proposed at the YJAC. So here is one bending magnet, then we can go afterward here for acceleration, further acceleration. So this is our plan. So this part we have completed here. This is showing this complete one. This part we have already completed, and from here we will be assembling our RFQ. This is the present status, and that's all. Thank you.
Thank you for the nice presentation. Can take one or two questions.
Yeah, Vijen Prasad.
Yeah.
Thank you, sir. Very nice presentation.
Where is it?
Here.
Yeah.
Your source emittance or Levitt emittance is almost matching the RFQ acceptance.
Yeah.
So what will happen in the higher beam current? Are you planning to reduce this emittance or increase RFQ acceptance?
Well, so we are trying to reduce the emittance in the ion source itself. And then we are modifying this slightly, this electrode geometry, and in the LEBD also we are taking care of by reducing the gas pressure and other things. That's why we have modified, updated this overall geometry. So increasing the means acceptance in the RFQ 325 megahertz is already fabricated and it's under assembly, so that may not be possible. So we'll be trying to reduce the emittance at the source level only.
Okay. So let's thank Vijendra. अरे भाई जो पूछ रहे हो खड़ा हो जाओ ना, नहीं तो दिखाई नहीं देता. Online.
That's okay.
Okay. Yeah.
Just one question, Bijen Prasad ji, congratulations. I have given my message in the chat box. I just wanted to know this H minus ion source, and you have placed the solenoids very close, LEBT line solenoids.
Yeah.
So how you shield the ion source from the solenoid fringing fields actually?
Yeah, that's right. We have used one bucking coil in between the ion source and the first solenoid. So the bucking coil we have designed so that the field of the solenoid magnet doesn't penetrate up to the ion source, the plasma chamber. So
Okay.
that we have taken care of.
Secondly, this 352 megahertz DTL experience is there at BRC. Of course, you have right now made, I look like in aluminum and all, and those chambers in permanent magnets also. So the laser welding, of course, RRCAT is the main hub for laser welding, so you can close the cavities nicely. And congratulations, I think this program should go ahead fast. Yeah.
Thank you, sir. Thank you. Thank you.
So
Thank the speaker once again.
Okay. Sir, thank you, sir.
Next, we are having two presentations from the industry. First is Massibus Automation and Instrumentation Private Limited. So we are having Mr. Sandeep Patel from Massibus Industries. So Mr. Patel, please continue.
So thank you, sir. So first of all, thank you very much for inviting us in such a beautiful event. Good afternoon. I am Sandeep Patel. I am heading R&D and ODM division in Massibus. So let's start with the Massibus introduction first. Yeah, so Massibus is a well-respected brand in India. We have started our journey in 1975, so we can say we are almost having 49 plus years of experience. We are a technology-driven company. So if you have a chance to see our product, we are equipped with the latest protocols like Modbus, TCP/IP, Ethernet IP, Profinet, Profibus. So we are having a technology-driven company. We are always current in the technology. In fact, we are the first who have invented digital panel meter and handy calibrator in India. So we are the first technology-driven company in India. More than 50 channel partners in India. So we are having dealer distributor network, and in most of the cities, we are having a dealer and distributors. 300 plus associates, over 20,000 satisfied customer, and our last year revenue is 150 crore. Okay. And we are having units in Gandhinagar and Goa. So basically 3 units in Gandhinagar and 1 manufacturing unit in Goa. So if we talk about our business panorama, so we mainly deal in 4 categories. So we are having our own products. We are having a product like data acquisition. We are having a right fit product for the industry 4.0. IIoT digitalizations. We are having a product like controller indicators, product for the time synchronizations, isolators, field interface module, temperature transmitters, energy meter transducers. We are also representing some of the companies like Pulse for the power supply, HMS for the M2M gateway, BMX for the calibrators, Williamson for the pyrometers, for the vibration sensors like VibraSense, Technicat, INOR for the transmitters, Procomsol for the hard communicator. We are also into the solution business. We are an authorized distributor for the Schneider. We do have expertise on PLC, DCS kind of automation. We do IT/OT kind of integration. We are a system integrator of Schneider. We are also doing solution using our own product. We are having 100 plus our own products. And we are also having a dedicated facility for the ODM. We have ODM. ODM means original design and manufacturing, where we provide complete product engineering services like hardware design, software development. And we are also having a panel assembly facility. So all Siemens, Toshiba panels are assembled in Massibus facility. So these are our complete product range. So in indicator, start from 0.4 inch to 6 inch displays. We are having this kind of product. In power side, we are having energy meters, energy transducers. For data acquisitions, we are having a scanner, data loggers, IO modules like AI, DI, AO, DO kind of modules. We are also having a product for wireless communications. In time synchronization, we are having a good range of product. Start from very compact NTP server to PTP kind of redundant big systems. We are also having a product for the vibration monitoring like vibration switches, vibration monitor tracks. In controller, we are having a product like on-off controller, PID controllers. Calibrator, we are having a loop calibrators, temperature calibrators, universal calibrators. And in transmitters and isolators, we are having a good range of product. And it's a make in India product. We are having a design house in Gandhinagar and we are also manufacturing in Gandhinagar only. So these are our infrastructure photographs. You can see here our Gandhinagar and Goa facility. Here is our own SMT house, panel assembly room. Yeah, so apart from our own product, we are having one dedicated unit that we call a ODM. So in ODM, we provide complete product engineering services like complete hardware design, embedded software development, product manufacturing, schematic and PCB designing, certification services, application software development. In fact, we are working with ISRO for all their higher end and multi-layer PCBs. So these are some snapshot of that PCBs. So these are some products we have developed for different OEMs. You can see here IoT gateway, PID controllers, railway, some feeder RTU for the Siemens, access control system for some of the Canadian, one of the Canadian company, textile controller for one of the Japanese company. So we are having a very strong R&D team in Gandhinagar, Gujarat. Some interesting product. So you can see here, it's our flagship product. So basically it's a 24 channel data acquisition module equipped with the latest protocol like Modbus TCP IP, Profinet, Ethernet IP, Profibus. These are some key applications like boiler tube temperature monitoring, stream leak detection system, motor protection, bus bar temperature monitoring. Individual IO modules we can use in IoT applications. So you can see here it's a these are some application diagram you can see. Local monitoring, we can also connect the HMIs. And we are also having a CPU card so that PLC or SCADA using Modbus TCP IP. These are some converter like Modbus RTU to Modbus TCP IP. Data acquisition software that we call a Smart 2.0. So for local So for time synchronization, we are having a varieties of products start from very compact 1 NTP port to bigger size redundant systems. Yeah, so I have my colleague, Mr. Dakshesh Parmar. He's handling our automation system, automation business.
Yeah, so thank you everyone. So we are associated with the company called Schneider Electric for the PLC and the DCS business. In conjunction with the PLC, DCS and SCADA. So that is our one of the world SWB, Bhavini, BRC, different locations, Tarapur, Trombe, Mysore, Kalpakam, and IGCA. So these are the lot of automation projects that we have done. Apart from that, there are a lot of other applications also like energy monitoring system, power distribution system, wireless solar string, material handling system, what different application in which Messibus has expertise. So if you go to see, we have touched upon each and every sector which is available into the Indian market too, and we are catering to the solutions for all the sectors. Thank you, RRCAT, for providing us the opportunity to.
Line?
Thank you, sir.
Thank you, sir.
The next presentation is from Piper Vacuum India Private Limited. I think Mr. R.K. Sahu will be presenting it.
Yeah. From everyone. This is the first slide. Now, everybody aware of the fiber vacuum, but last 6 months is a part of Bush Group. Bush Group is a Bush vacuum, fiber vacuum under Centrotherm. So this is me working in fiber last. I think many who don't know the Bush vacuum, but they are very good in the rough and medium vacuum. And there are the very nice product which is used for the helium pumping. Fiber, you are aware of the turbo pump, leak detector, and this is used for the many industry and the components. And Centrotherm is a clean solution like the semiconductor market and solar market where we are using the lot of corrosive gases and it goes to the atmosphere to filter it out to protect the environment. So this is how we are using a lot of filters before gas goes to the environment. Sorry. So this is what I explained, the roughing pump of Bush and fiber of turbo and Centrotherm for the gas abatement system. So these are the products. So the people, the user who are in the cryo, they're evacuating the helium pumping. So here you can see Cobra industry. So those pumps are used for the helium pumping specifically, and those are designed with a lot of temperature sensor and controlling the pumping speed. And Hukepack is there are the liquid ring pump, the roots pump Panda, and there are the some vacuum gauges. And to control, to monitor the all vacuum pumps, there is a OTT digital services is also available. So this is fiber vacuum, multi-stage, roots pump, dry pump, leak detectors, and you can see magnetic elevated turbo pumps. I don't know, I don't have the pointer. So scroll pump. So next week we are launching the high scroll 46, which is the 45 cubic meter per hour. So now it is starting from the 6, 12, 18, 46. And there are the a couple of valves, butterfly and thermostat, Digiline. Thermostat is basically, it is a gas analyzing equipment, which you know the RGA, but thermostat and Omnistat is like, it will operate from atmospheric to -9 or -10 vacuum to analyze the gases. So this is what already I explained to, this is a gas abatement system, thermal gas treatment, wet chemical and dry bed. If you are using sometimes the corrosive gases and you have to protect, like now the semiconductor industry is booming and many R&D people are using, establishing the lab. So there, this gas abatement system is useful to clean the gases before it goes to the atmosphere. So this is the Bush group. Here in Manesar in Delhi, we are assembling complete system. So this is the real picture basically. So complete system, piping. So you will just connect to your chamber. And this is one of the application, as I said, it is a helium pumping. And all the pumping, it is a 600 cubic meter per hour for air, but helium it is 300 cubic meter per hour. So Bush group at India. So here we are almostly 127 team members and sales and service and the full systems building capability. Here we are, it supports our Make in India. Then we are maintaining the quality department, ISO 9001 and 45001. So this is what I can, now this is the new turbo pumps. So in past, the all rotors and starter was balancing with those balancing screws. So now we are using the laser balancing, which the whole rotor is laser balanced, which is 20% low vibration level compared to the Hypes 80, which is around 60 liter per second, less bearing stress because of the laser balancing and more robust and sharp design. So this is one of the beautiful pump, high compression ratio pump. This is also, it is on our stall 6. So it's a very small pump, 250 liter per second. Backing is the hardly 1 cubic meter per hour, and the chamber is a 30 liter. So we reached almost 5-9 and also 5-10. If you see, without backing, without anything. So it's just a pumping, and after 2 to 3 days, we reach this vacuum level. So this is what we supply to the PRL. It's a complete system from Pfeiffer Vacuum India. So you can say local content of almost 60% or more than 60%. So this is the outgassing system. The whole chamber, we made it in India. This is our service capability. We are here to complete service of the turbo and whatever we supply products. So we can do here. And 80 to 90% product, we can do the service at your site. So what we are doing in the service center, there are a lot of test benches. If you are leak detector testing after a repair, we test it, multi-rods, turbo pump, and also the multi-rods and dry pump, which is used for the solar and semiconductor market. Thank you.
Thank you, Mr. Sahu, for presenting the product line of Pfeiffer Vacuum and Bush. We still have 2 presentations, and those are very nice presentations, so you have to sit tight. The next one is Mr. from Rajesh Kumar Agarwal. He's the head of the accelerator control section of RRCAT. He is B Electronics from GC Ujjain, ME from DAVV Indore. He is recipient of 6 Group Achievement Awards from DAE. His area of expertise is design and development and commissioning of control system for particle accelerators, Indus 1, Indus 2, electron linac, H-mine and sensors, high availability database and data visualization application, energy ramping, cycling and their verification system. He has more than 35 national and international journals and conferences. Agarwal ji, please start kijiye.
Thank you. And first of all, thank you for nicely introducing me, the chairman, sir, and also to the organizers of the InPAC 2025 for giving me an opportunity for presenting the work related to the Indus complex and Indus control systems. And what I am presenting is on behalf of Accelerator Control Section, ACBDD. All my team members and seniors are acknowledged for this work. So the talk will be based on the some lines, and I will just start with the introduction part directly. So particle accelerators are basically complex machines, and everybody knows about it. And Indus 2, why I say that is a complex machine, that Indus 2 has 15,000 signals, analog and digital, and more than 20,000 data points, which we are handling right now. And it involves many interacting systems. Many engineering systems are operating in tandem, and like vacuum, RF, magnet power supplies, BDS, MSIS, and RSS. I would just use the acronyms. And the tight performance demands. The tight performance is required for beam injection, extraction, accumulation, and then highly stable and tightly synchronized systems are required for this purpose. Then extended period of operation of this and with minimal interruptions. Otherwise, what will happen? We are filling the beam and it is stored for 2 days. Any deviation, small deviation in the control system will kill the beam. So that's the requirement. And this is the well-known diagram. We all know about it. I will not go in much details, but just concentrate on that. Indus 2 was commissioned in 2005. And then we are continuously upgrading with the enhancements and additions to the systems like beam-based alignment, finger operation, slow orbit feedback. Even we have tried fast orbit feedback. And then the Indus 1 was commissioned in 1999, and major control system upgrade was taken up in 2018-19, and then another upgrade in 2023, where we have upgraded the magnet parts to accommodate the COD correction. So all these machines are operating in the round-the-clock mode as national facility. So this is the architecture of the control system. It consists of 3 layers, and the lowest layer we call the layer 3, layer 2, and this is the equipment control layer, this is supervisory control layer, and this is the top layer for the user control applications. We have WinCCOA SCADA from ETM Austria, and now it has been taken by Siemens. So this is the SCADA system, and this is whole is in-house developed. We have around 120 L3 stations consisting of 1100 VME cards, all developed in-house, distributed in 500-meter area of Indus complex, and the total 10 subsystems are in the layer 2. So what happens when we have a Profibus between the two? This is the Profi master, this is Profi slave. We are communicating on the Profi and getting the data from each subsystem. We have a specific supervisory layer controller for any specific system like magnet power supply control system or the vacuum control system or similar other 10 subsystems are there. And then we are getting the data, and the interface between the layer 2, the supervisory controller, and the user interface controller is based on an API manager being developed in-house, and this whole UI development and the database development has been done in-house. So these are the features. Hardware, mostly VME based, in-house developed. Machine control applications for cycling, bunch filling, ramping orbit, bumps, orbit feedback, tune feedback, ID control, diagnostics, MSI, machine safety and interlock system, loading the required system files. Quick diagnostics has been made available, heartbeat status of various layers, history data logging and beam kill event analysis, event and action log for any postmortem analysis. The fast data acquisition system has been commissioned, cycling and ramping analysis has been done, the most important part is that we are having machine states and all the things are being logged and operated with the help of machine state driven based systems. So beamline front ends for coordination and control with the beamline part and the user part, permitting the and regulating the users on the beamline, machine safety radiation, and all such systems. I will not go into the details of those things. And these are the various technologies used, right from even the DSP based controllers have been used. And I will not go into those details right now here. Mainly we have used VME and PXI platforms, and we have also used RTOS, OS9 and VxWorks, and LabVIEW-RT. For LabVIEW-RT has been used for the SOFB application. So these are the some typical specifications. We have physical signals going now for the whole complex. If I caught, it is more than 20,000. The data points are again more than 20,000. We have configured 1500 alarms. Data log rate is 1 Hz, and the parameter deviation alarms are also available, where in the DC mode, if any deviation is happening, then that has been alerting the user that the deviations are happening. So hundreds of such number of parameter deviation alarms, and we are generating a data of 3 TB per year and logged. The most important part is the low timing jitter of less than 2 nanosecond timing pulses, isolated trigger signals to the synchronized with the RF clock, with programmable delays in millisecond, microsecond, and nanosecond range, with 1 nanosecond resolution as per the bunch filling mode requirement. We have 15 ppm dipole and quadruple power supply references. These are some system glimpses. The cycling of magnet is one of the operation where we have to regularly cycle the magnetic components for making them history free. And for that purpose, there are 117 power supplies which are cycled in this manner. If any deviation is happening, they may lead to issues in the beam filling in the later on stage. So one has to qualify that the cycling has been performed properly, and whatever references have been given, they were proper, and as well the power supplies have behaved properly during the cycling period. This is half an hour, almost half an hour period. 3 cycles are been done, and this is a manual process, is very tedious. So what we do is we have an analysis already that has been done, and the deviation, if any deviation is happening, that is reported in the form of a report to the operators so that they can quickly identify and find out the issues in the cycling process. So interface, we are also providing interface to the machine applications for booster current optimization, finger magnet operation for program in a programmed way, optimization loop for industry injection process and microtron beam current, interface for beam life measurement, automation for sequences of the complete machine life optimization and protection. So basically what happens when the TL3 is, when the machine is being injected, the TL3 is being used at that time. After the injection and the beam is ready, we are automatically bringing the TL3 to the minimum value so that we can save the power also. Industry injector, pulse power supplies, ST on off, and these are the injector, these are the kicker magnets which need some stabilization time. And for that stabilization time, the automatic sequence ensures that the stabilization time has been given to them and they are operated in that condition. And then microtron active and standby mode is also made available so that we can save the cathode life to a maximum value, and we can operate the cathode for more than 2 months or more than 3 months. We have low, these are some of the developments which we have done later on. This is the low jitter timing pulse modules. We have such VME bus based systems are developed, and we are getting FPGA based VME delay generator boards. It is the remote programmable delays possible, and delay setting and in the coarse and fine scale of 0.5 nanosecond resolution is possible. Channel to channel timing jitter of less than or around 200 picoseconds have been achieved. Now coming to the recent upgrades part, So the verification of energy ramping process, like cycling ramping process, energy ramping process is also verified, which is also a 13 minutes, around 13 minutes total task, in which all the 117 power supplies and 6 RF cavities to take part. And what we have to do is verify that the energy ramping process is proper in case any partial loss or any loss of the beam happens. So that requires that what all the devices have been selected, all the power supplies that participate in the ramping or not, ramp profile matches. So these ramp profile matching has been achieved with the help of software. Now, the upgrade part of this is recently we have implemented low emittance optics for the machine operation, where we required that the ramping process itself has to be modified so as the dipole, which we had initially made as a monotonic operation, it can only increase, but we have allowed to go in the non-monotonic way also. So for required that, the ramping process was updated and the verification was also upgraded. And now it is possible to operate the machine in the low emittance mode without any user intervention with a single file of ramping. And also re-ramping is possible. Re-ramping is one of the features where we are generating all the data and that data is being reused again. So beam-based alignment is one of the operation which was commissioned after, I think it was commissioned 2018. And then we have done it a full-scale deployment with 80 power supplies and 56 BPMs. The overall algorithm was time optimized and a comprehensive report is generated. Now it is a regular feature after every shutdown to do the beam-based alignment. In the beam-based alignment, what we basically do is the magnetic axis and the electrical axis of the magnetic axis of the quadrupole and the electrical axis of the BPIs are not normally, because of the placement alignments, there is an offset, and that offset is required to be known so that it can be corrected for COD correction and SOFB operation of the machine. So alignment of all the BPIs now is possible to be done in both the planes, horizontal as well as vertical, almost unattended in one shift operation. The machine safety and interlock system, it protects the machine from any kind of overheating to avoid, and also protects the human from entering into the radiation zone. The output action is based on the temperature of the respective magnet coils, and it trips the RF and stops the injection based on the condition that whether the temperature is high or the DCCT issues are there. Based on that, I will just skip this slide. This is the overall architecture, how the MSIS, the machine safety and interlock system works. Now, what we have upgraded is that we have modified the communication over the Profibus between the layer 2 and layer 3, and the scan and poll rate has been increased to 2 Hertz, and the self-test feature in the IO cards has been incorporated, and reassessment of the signals interfaced has been done so that the availability of the machine can be increased, keeping the safety of the machine into mind. And this has resulted in almost fault-free operation in last 5 years. Just last month only one first fault came, which was related to the some contacts. Then we have done the test and simulation setup for Indus control system, and this is the setup which we have deployed, and this is the software. We have the similar software what we are using in Indus 2. Actual replica of that has been done so that the VME bus-based 3-layer architecture test simulation setup can be used for any modification or enhancements done in the existing system. So this is the fast data acquisition system for Indus control system, where we are acquiring the data at 50 kbps, 80 channel synchronized way, isolated, so that we can find out whether the RF is tripping first or whether the beam is tripping first, or whether the issues of DCCT, whether the issue of the power supply tripping and RF tripping are, to find out the exact reason as a diagnostic tool. So this is another development which we have done. This was the earlier we have done for 80 channels. We have now done it for 200 channels. This system is already ready, and this is totally indigenous. That was based on the procured cards. However, this is totally indigenous system and it is ready for deployment. We will be deploying it for all the magnet supplies. We have done high throughput data acquisition testing, where we have tested it for 20,000 analog channels at 5 Hertz, so that we are ready for the next generation machines, and we have used the Cassandra database. Yeah, I will take two or three more minutes. This is the fast data logging. I will just skip this slide. Here we are inserting the data into the intermediate database, and we are also having three, which we have already covered on this topic. Web-based applications are there. We have also upgraded it to the Linux OS for the security reasons, and additional features of website for event view, dashboard, zoomable graphs, multi-parameter graph, scalable data download has been achieved. Serial bus analyzer is used because the Profibus we are using, and that the serial bus analyzer system provides us the signature-based analysis and time profile measurement in various transmission packets, measures the voltage signals on the RS485 links, and transfers to the host PC for any abnormal condition. This is one of the recent developments which we have done, is the indigenous BPI development, which is also presented by my colleague Dr. Rishipal Yadav in the contributory oral. This is now qualified and ready for mass production, or we will be soon doing 10 numbers of such devices to be fabricated. Recently, we have upgraded Indus 1, and that has been presented as a poster session in INPAC2025 itself, as this work was done for, and the new control system for all the 30 new magnet power supplies has been deployed, and we have achieved the closed orbit distortion reduced to a minimal level. We also have used this system for using the feedback mechanism, slow orbit feedback, and then it is possible to keep the 60 micrometer peak to peak beam variation within that 60 micrometer range. A single button operation is also ready. Now we will be in a position to operate the whole machine by a single button click, and it will take interface of the auto injection, optimization, cycling, ramping, handling. All these will be handled, and it will also handle the optimization algorithms, intercommunication with them. Now I will just touch upon the next generation challenges, and this is the clock synchronization is one of the challenge for the next generation systems, where the synchronization in the 1 kilometer area is required, and for that purpose PTP is one of the solutions. And there are three basic operations in the synchronization, either PTP or other timing systems we are considering. The one is the synchronization, the other is synchronization, and the third is tuning of the phases. So synchronize, I'm sorry, this has got auto corrected. This is synchronization, where the equalizing of the frequency is done, and then in the later phase we use the stroboscopic method called the digital dual mixer time difference basis, and that the tuning of the phases is done, and the last state will be the synchronizing of the counter values of the two clocks. So this is how the all either PTP or any other timing system which are in the distributed way are using. So this is either IRNS or GPS receiver will be, or CZM or other clock, stable clock will be given to the encoder, where the local clock and data, and then it is transmitted using a fiber optic at 250 megahertz. The PTP basically calculates out the time difference between the transmission and the receiver, and it corrects automatically with the help of this trapezoidal. If we see that this is the trapezoidal, T1 minus T4 minus T1 and minus T3 minus T2 divided by 2 will give the estimate of the delay, and this delta is used, and statistically it corrects the, in the case of PTP. In the the other distributed timing system is White Rabbit, which is operating at 125 megahertz. It is soft synchronous. It is being used and it is planned to be used in the ESRF. MRF timing is basically event-based timing system, which is operating at 50 hertz, 50 megahertz to 142.9 megahertz, which is synchronous, used in NSLS. Greenfield timing is considered in Soleil, JPark they have, and BINP, they are using their own system based on this.
Sir,
So, yeah, I will just finish last slide, sir. So this is the possible way of event-driven distribution of the timing, where we have the master and we can connect multiple local, and these locals will be generating different triggers to the devices. So event distribution and sequencer is possible to be programmed over here. Distributed IOs will be, so I'll just go for the future plans. This is the last slide. Booster control system upgrade is in the next phase for Indus 2. Harmonic sextupole, deployment of FDAQ, which is ready for more than 180 channels. Control system upgrade for in-house IDs like MPW and WLS, and new SRS complex moving ahead with the challenges. So thank you for listening and allowing me overtiming for around 2-3 minutes.
Thank you. Oh, is there any question? The talk is open for discussion and I can't see any hands. So let's thank the speaker once again.
Thank you, sir. Thank you, sir.
So let me invite the last speaker of this session, Dr. Abhay Deshpande. He's from Samir, Mumbai. He'll be talking about electron accelerator research for societal applications at Samir. And Dr. Deshpande, he has BSc from Mumbai University, MSc from Mumbai University, PhD from KEK, Japan. His achievements and awards include convener for the Indo-Japan Accelerator School from 2012 to 2020. He is a visiting speaker for International School on Beam Dynamics and Accelerators, Hiroshima from 2018 to 2024. Area of work is the design of LINAC at S-band and X-band. Designed RF photocathode gun for KEK facility. 2.6 cell RF gun for Delhi light source. Current research interests are high gradient, compact LINAC-based neutron source, multi-energy LINAC for therapy, novel medical therapy technologies. He has more than 30 publications in international journals. Deshpande, please continue.
Thank you so much. At the outset, let me thank the organizers for inviting me and letting me present the work of Samir in this conference. And I thank Arubda for the excellent introduction. So I know I'm standing between you and the lunch, so I'll try to be as fast as possible. There are two parts. One is, of course, the medical applications, which is one of the focus area for us, and other is the novel technologies that we are trying to establish. So in next 15 odd minutes, I'll run across various such activities. So from the design point of view, we are having a very stable design of 6.5 cell side coupled biperiodic standing wave structure. We operate at around 3 gigahertz frequency, so-called European frequency. In our case, the buncher is integrated part of our accelerator, followed by the main cells. So in this sequence, with this field, we are able to achieve very stable beams. So once the designs are done using, now earlier Superfish Poisson, we had our own codes, now CST as well. This is the CAD, 3D image of the CAD, translated into a CNC turned machine and translated into brazed activity. So we follow a very stringent mechanism of establishing the cavities. And the LINAC is also very compact. This is a 30 centimeter long structure. We are trying to reduce it to 25 centimeter long structure to achieve the same same parameters. With the 2.6 megawatt magnetron, we are able to achieve 6 MeV energy with a reasonably high current for the radiotherapy applications. So this is the structure. The gun is of course designed and made at Samir. We purchased bare cathodes from the market. The entire machining, tuning, brazing, characterization, parameters, including the RF window, everything is designed and made in-house at our facilities. We also have a longer structure, which is also now very well stabilized. So this is a 23.5 cell structure with 2.5 puncture sections included. The gun in this case is a demountable type in the sense that we can remove it and reconnect it if we require to change it. The window is also demountable and the target is also demountable. So in principle, either of these three, if they go bad, we have the ability to go to the site, remove and replace on site, do a quick processing and then restart the entire accelerator. This is the advantage of this particular longer structure. The longer structure uses a magnetron. Although we go for a 6 megawatt, we don't need such a high power. We are sufficing with 4 megawatt. At 4 megawatt input power at the LINAC port, we are able to generate 15. Although I'm saying 15, we have even crossed on the higher side MeV energy with a very high dose rates in this case. So what are the applications? The major applications, as you all know, is of course the radiation system. So using the 6.5 cell structure, which I showed earlier, the 6.5 sits vertically over here, followed by a primary collimator, followed by a asymmetric jaw secondary collimator. The electrons hit the target and X-rays are coming out of it, and this is used for patient treatment. The component that you see, the LINAC is here, the modulator is on the rack, all the controls and everything is inbuilt in the gantry stand, and the controls is of course outside. This is the patient couch assembly. So the designs are made in-house and nowadays these are fabricated from the industry. This is a very active program. We are having 3 functional machines as of now, all in hospitals and doing the active treatment even today. So Adyar, Chennai, Indore and Amravati are the 3 locations where the patient treatment is going on. The technology is successfully transferred to Panacea. Panacea has now working on 8 machines, of which almost all are in the final stages of deployment. We also have 2 more TOT partners recently, and with the present split that we foresee 20 machines per year based on Samir technology, and that will happen sometimes in 2026 onwards. So this may also go up based on how the next TOT partners are going to shape. So this is how we have translated the machine from a physics design to in the industrial design and to actual functional machine. That was the first stage done totally by Samir, 4 machines deployed in the hospitals. Now the TOT partners are taking up and everything is standardized from the international standard point of view. The machine qualifies all the stringent norms as set by the Canadian as well as all whichever protocols you want, we are able to suffice. For us, AERB is the most stringent protocol and we have been cleared for the AERB protocols at every point of time. The next subcore, of course, is the longer structure which we have made. So we have already converted the longer structure into a dual mode multi-energy LINAC. And by dual mode, it means that it will have the ability to give electrons as well as photons. For example, the 6 MeV machine which we have shown just now, it's a single standalone photon machine only. It does not have electron output. Now we are modifying that. But for the longer tube, we are having 2 modes. One is photon mode and electron mode. In photon, we can offer 6 and 15. That's our design. And for the electron, we are 6, 9, 12, 15, and 18. And now also we are able to offer 21 MeV. This machine is now ready. It's already integrated at our Kharghar setup. How do we achieve the dual mode? Dual mode is fairly straightforward. We have our own beryllium window at the exit. The electrons keep on coming out. Thereafter, there's a bending magnet over here. You can see this is the 270-degree doubly achromatic bending magnet designed and made by us. And the target comes after the bend. So you can have the target in, you get photons. You retract the target, you'll get electrons. For changing the energy in photon mode, it's a very tricky issue, and for which we have plunger mechanism at this location. And the plunger mechanism, basically what it does is it goes and detunes the sides coupled cavity. So this part, the longer part, becomes only vacuum. There is no field over there. So with the plunger in, we'll have this much structure which will give 6 MeV. With the plunger out, you have the entire accelerating structure that gives you the 15 MeV output as required for the medical applications. This was quite intensive. We have done too many technological development in this machine. Of course, triode gun, plunger mechanism, power variation for Claston, carousel for fitting various flatteners because you need a flat beam at all the ports, achromatic magnet, asymmetric jaw collimators, motion controllers, record and verification softwares, wedges, applicators for the electron machine. This all has to be done, and this we have already done and tested. From the electron beam point of view, we have demonstrated all the energies. For photon also, we have demonstrated both the energies, but for the 6 MeV, we are slightly falling short of the photon dose. So that is the only part which we are right now working. How do we improve the photon dose? We have understood the problem and we'll be able to resolve the problem very soon, and this entire parameters demonstration will be done. Then we'll go for the QA/QC from the patient point of view, and I expect by this year end or early next year we'll do the QA/QC, and the machine will be ready for the patient trials sometimes in 2026. We already have EOI floated for this activity and we are getting good response. So we expect the industry partners also to come on board for the pending work, and they will take up the machine. We already have 3 TOT partners and all of them are asking for this machine. From the point of the utility, maybe 90% of the patients suffice with 6 MB. Rest 10% patient cases, you need 15 MB. So for a country like India, 6 MB machine is more or less sufficient if you want to deploy at various hospitals. But the longer machine is a requirement from the oncologist. So we are providing that option as well. Now, this was the therapy part. So traditionally, Samir Group has been always focused only on the therapy part. So last few years down the line, we started doing the switching from the therapy part to the diagnostics part. In diagnostics, we are running 2 programs. One is, of course, the MRI program, in which the magnet and all other components are being developed in India, and a magnet and systems are more or less ready. We expect it will be going to market sometimes next year. Other part of the diagnostics where accelerator will come into picture is, of course, the isotopes. So we are running a small activity for isotope generation, accelerator-based isotope generation for past few years. In this case, what happens, as you all know, the isotopes are injected in the body with suitable tracers. Those get accumulated and the isotope start emission. If you do a single photon emission CT, simultaneously with CT, you can get a slice by slice of the body and you can find out where the issues are in the particular body. Now, of course, it's just a photon emission mechanism. The doctors has to correlate with the clinical symptoms and identify. So this is where the accelerator physics people come is to how do you generate and can you generate isotopes using accelerator. So we identified this as a potential problem for our group. One thing is to upgrade our technologies, and we have identified these many isotopes. Of course, number 1 and number 2 to begin with, using a gamma N and gamma P reaction, can we produce technetium and can we produce copper 67 from a linear electron accelerator? That was the problem offered to us by our funding agency, and we have taken up this challenge. And now there is one more addition. This is 225 actinium, which can be done from radium-226. Of course, if I get radium-226, this would be a straightforward thing. And lutetium, if I am able to do N-gamma reaction. So nevertheless, right now the focus is on number 1 and number 2. And these are very specific accelerators. As you know, accelerators can produce isotopes. Cyclotrons, of course, are producing FDG in the country already, and it's well known. But for moly, it is always a reactor. Now BRIT has got a separate moly generation mechanism. So from the point of moly, more or less, this is taken care of. So our accelerator will be focusing on development on various new applications and new isotopes. So what we are doing is that we are trying to put 2 of our 15 MB structures, similar structures with slightly additional enhanced features in series to generate an electron beam which is very high energy and bombard it on a converter target to produce X-rays in the forward plane, then place a secondary target and try to change the features of the target based on the various reactions. So for moly, it will be 100 moly with a gamma N reaction will give us 19 moly. This is the advantage of a LINAC. In case of cyclotron, it will be technetium will be the outcome if it's a 16 MB cyclotron. technician will be outcome, which has got a 6 hours half-life. But in case of LINAC, it will be moly 99, which is having 66 hours half-life. So if I am able to produce even slight amount of moly, we can send it wherever we want as far as the moly is concerned. So these are the parameters. So we plan to achieve somewhere around 28 to 30. In principle, 25 MeV is more than sufficient for moly production, but the average current should be as high as possible. So we are targeting a parameter of 30 MeV and somewhere around 300 to 350 microampere as the average power. We are using a Claston based system. So what I'll be doing in next few minutes, I'll quickly run through where are we as far as this system is concerned and what are our plans. So this system needs two accelerating structures, as you know, and we already made both the LINACs. So LINAC 1 and LINAC 2 both are ready. They are, in our case, we bake the LINAC and then pinch it off and it becomes a standalone system with an ion pump mounted on it. This ion pump takes care of the vacuum during operation as well as a monitoring device. So it's a dual purpose ion pumps which are sitting, these are 20-liter pump which are sitting on the accelerators. And as of now, you can see both accelerators have gone because we are testing them independently and then we'll be synchronizing both the accelerators together. So these are of course ready. The exit window over here is not visible. It's covered by a flange. That's a 50 micron beryllium window made at Samir by our team. This is the converter target. As I said, it's a retractable target. The target is over here. The beam comes from this plane. We can push in a copper target if you want to have only parameter testing measurement. You don't need great amount of X-rays. You can push in the copper target, remove it, push in the tungsten target. The photon dose goes sufficiently high. If you don't want either, you can just remove both the targets and electron beam will fly through the beryllium window and come as bare beam in the vicinity. So in this case, we are planning two experiments, and this is called, we call this so-called converter target approach and the direct target approach. So these are the simulations using Giant 4. And what we do is here, the electron beam hits a tungsten target, produces photons, and those photons will bombard on the moly 100 target, and we get this reaction. In this case, this is the distribution that we are expecting. But if we remove the converter target, moly itself could be a converter target. You really don't need a tungsten. So the beam will come out and hit the moly. Moly is also capable of producing X-rays. So the converter target and the final target will be identical. That's we call it as a direct target approach. So we got a publication in ARI on this paper, on this proposal. So we have found that if you discard this approach and go to this approach, then this entire mechanism becomes extremely lucrative. The amount of activity produced in this case will be sufficiently high, and therefore we are focusing very nicely on this particular activity so that we will be able to produce moly 100, moly 99, which will be of sufficiently good activity. Of course, this is a paper and the output will be seen in few months down the line. Traditionally, we make our own modulators. Our modulators are line type modulators, but in this case, we have purchased a Scandinavo modulator over here because we don't have experience of making such high rep rate modulators. We are now working out to make this kind of modulator. So we are using a Canon Claston, by the way, which was Toshiba earlier. So Canon Claston with 10 microsecond pulse width, and it can go up to 500 Hz repetition rate. So 7.5 megawatt and 37.5 are the features. Yeah. So where we are standing, so we have integrated the entire system. It is integrated at our Kharghar facility. There was a radiation hall at Kharghar, and what we are doing is the Claston does not sit inside. It's a solid state system, so we have shifted it to the next room, and we are running the waveguides along the wall and bringing the power to our accelerator. So these are the Claston parameter measurements. You can see that we are getting good pulse width. The peak power is measured at 7.51 at the exit of Claston. We have got a excessively good water cooling system. This is important, but I'll skip it for the time being. The other major issue that we have to address was, of course, the shielding, because we expected the photon flux will be high as well as the neutron flux. So what we did is that with the help of Health Physics Department, BRC, we ran a simulation setup and proposal that can we create a local shielding structure around the target so that the radiations will be contained in the same zone. So based on the discussions with Health Physics Division and other experts from BRC, we designed a local shielding structure. So the target sits inside a shielding structure which is covered around lead is there, then HDP is there, then borated HDP there, and finally 40% boron rubber sheet is at the final stage. So we can contain lead as well as neutron in this vicinity. Of course, beyond that there is a 2.6 meter concrete wall of our location. So this we have created from scratch. We have integrated the entire structure, and the structure is ready. We are doing the measurements at this stage. This target is sitting inside, and you can see the wall distance is 3 meters from all the direction. Next is the question is therefore, how do you load the target, the moly target, for example, if we are using a structure like this. So for example, if I am doing a isotope beam line, I could have a shuttle. But shuttle will lead to leakages in this shield. So what we did is that we went for a robotic arm based system. So in principle, this was the video, but because I am using PDF to this, it's not visible. This entire machine moves from one station to here based on this automated guided vehicle. It follows the magnetic trap. And this is a 6 degrees of freedom robot with a pick and pull mechanism. The vehicle can go wherever it wants and pick up the target and put it into a container and bring it out to our hot cell location where we can process it. The control system is FPGA based system. We have our own designs of the board. Those are very well customized. We have made so many systems using this board. It's very stable, very nicely functional. This is the LINAC integration. We have integrated the accelerating structure with the system. This is from where the waveguides are coming in, and we are doing the connection over here. There's a bending magnet for the energy measurement. This is the entire system integrated, LINAC number 1 and LINAC number 2. Right now, we are testing them independently. And this is the control room from where we monitor the entire mechanism, and each and every signals are digitized, brought to our FPGAs. There are 2 slave controllers in the local region and 1 master controller which takes care of entire system. And we can control radiation. This is a radiation monitoring system. The CCTV, these are the modulator units, these are the chillers and gun injection supply, and everything is visible in our panel. These are the actual test results. This I have already shown. So this is the forward power, the pink one, if it's visible, is the forward power going to the LINAC. The blue one is the reflected power from the LINAC at the LINAC port, and the yellow one is the reflected from power once again, but at the circulator load port. This is without beam. This is the with beam configuration. You can see beautiful for reflected waveform. This blue line is the target, which is a Faraday cup. In this case, this is a Faraday cup waveform. We are able to give very stable operation. This shows that as I change the gun injection voltage, I can increase my current sufficiently. We have already crossed 80 milliampere as a peak current. With the repetition rate that we are having, we can easily cross 2.4% duty cycle. This is the loading mechanism. You can see the loading changes as I keep on changing the current. We can overcome by increasing the power. That experiment we have done very nicely. Beam energy measurement, there are 2 mechanisms. Traditionally, from the medical point of view, we go by aluminum sheet measurement. That is what we have to configure when it comes to dual activity, and that is giving somewhere around 18. Now last week we also configured the beam bending magnet, and we are trying to use the beam bending magnet also to verify the energy mechanism. This is not very exactly done, but we will eventually reach and precisely measure the beam energy with the beam spread. What are pending is, of course, synchronization of both the LINACs that we plan to do in August, put them together, do a phase shifting mechanism, and demonstrate 30 MeV with 5 to 10 kilowatt. That is our plan till September 2025. Then with INMAS, who is our partner, and the people who are helping us, will do the irradiation experiments. Various groups are helping us for the isotope related work. There are also some neutron measurement experiment in discussion with the people because we don't have the background of neutrons. 2 more slides from me. What next? That is the key question that we keep on asking us. One is, of course, the compact ion therapy prototype, which we have presented earlier. Now we are working very systematically on this mechanism. It is a 7-meter structure based on induction cell mechanism to produce 70 MeV protons and 18 MeV per nucleon. So right now we are in physics design of this particular structure. We'll come with a paper very soon, clearly bringing out the lattice and all other parameters. From the electron point of view, we are now working on 6 and 9 MeV triple F system, which is one of the most crucial requirement, which will have photon mode as well as electron mode. FFF is the keyword. We are not right now working on the flash therapy system, but we have a mechanism to incorporate flash therapy in our existing machine. Right now, we're not working on it. The multi-energy radiotherapy, which I have already shown, we are doing a rigorous restructuring of the components. We will achieve this in next year and we'll be able to demonstrate the QA/QC to the medical community sometimes in 2026 and then push the machine for the next stage. Our X-band activity is taking very nice shape. Our structures are very stable. We will come with the final X-band activity. We are in a very advanced stage of design. The main issue is of course not the accelerating structure. The main issues are how do you populate the entire machine into a robotic arm, which we can operate on 6 degrees of freedom. That is the main issue. So it is essentially a mechanical issue coupled with the various components that we are trying. It is taking quite exciting work. And now we are having many good partners who are coming on board with us for this activity. We expect to move very fast, very soon. From as Jishnu sir has already shown, various components we need to indigenize. We are also the sufferers of the klystron lackage. We don't get klystron so easily nowadays. And in fact, the dual energy activity is pending because we don't have working klystron or klystrons are being used here or there. So if DAE comes with a klystron, we'll be very happy. We'll straight away start saying, humko 4 klystron to chahiye. So that is where we are also struggling. We are not working on klystrons, but we are working on a magnetron. Our 3.1 megawatt magnetron is under vacuum processing. Once the vacuum processing is satisfactorily done, we will do the beam testing sometimes in September 2025. And we are pretty sure the design is very, very, very elegant. And once this is complete, the entire setup is already ready. So we hope to get our 3.1 megawatt magnetron maybe early next year for the prototype completion, and then stability time will take usually a year. Then it can be offered to a TOT partner as the indigenous 3.1 megawatt magnetron. We have already developed 3-port circulators. Our own systems are using our own circulators. So there is no mechanism which we say it doesn't work. It works perfectly well. We are doing 4-port circulators mainly for our dual energy structure. And those are done by Guwahati group. RF loads and water loads, which I am using in the HEL, is to say a 45 kilowatt load. So those are being done now by our Guwahati group. So we will be able to achieve 4-port circulators, loads, and 3.1 megawatt magnetron for our own systems. And we can borrow the magnetron klystron from DAE for our virtual system. With this, I would like to thank all of you for listening to me patiently. Thank you so much.
Thank you, Dr. Dikshit, for the very, Dr. Deshpande. Thank you for the very nice presentation. And I really liked your work on the molybdenum. It's a new information for me also. So the talk is open for discussion if you have some question. Yeah. Can you take up the microphone? Then everybody will be able to listen. Yeah, just hold on a second, sir. Take the microphone.
Hello. Yeah. I understand that Siri Pilani has done a technology transfer for magnetron to some private party. Are you aware of that?
Yeah, we are aware of that. In fact, we are also landed into MOU with Siri Pilani for the cathodes. Siri Pilani has done TOT with Panacea, our own partner, so that he can make the magnetrons and use in our own machines. So those magnetrons are also reasonably okay, not yet fully functional from the point of view of the operation. We are aware of that. He has visited us multiple times for discussion.
Okay, yeah.
You have just told that you have developed 3-port circulator. What is the material is indigenously developed?
Yes, indigenous, yeah.
Garnet indigenous.
The ferrites are not indigenous, but that we are purchasing the ferrites right now.
Where from?
I don't remember the name. I'll share with you.
It is imported or?
No, these are the initial ferrite that I'm saying are imported ones.
Imported.
Any other question or comment from anyone? Okay, then let's thank Dr. Deshpande once again.
We can discuss later. Yeah, please.
Yeah, please go ahead.
Other modes like IGRT, IMRT, VMAT will also be there.
Right now, IMRT will be eventually, as I said, the multi-energy machine that I shown at the advanced next stage development, it will have IMRT mechanism. We are now into MLC and TPS. Our machine doesn't have treatment planning system. We are relying on treatment planning system into third party. For MLC, we had done a developmental work, but eventually we have not configured and used our own MLC in our own machine. So now we are running a industry-based system developmental program where MLC is being done by the industry. So we need to develop MLC, TPS and EPID. Of which TPS we are not attempting at this stage. We are focusing on MLC and EPID, and then we'll purchase the TPS for the time being, because anyway hospitals has got their own licenses. We'll hook on them. Our issue is to make our machine compatible with the existing TPS in the market. Our machine will be IMRT compatible, IGRT compatible.
Yeah, session is now over, and in fact, it was a very interesting session, and it is very difficult to control the speakers because they are so enthusiastic in presenting their own work and interesting work, and in fact, controlling the audience also having a lot of curiosity, because the speakers have generated a lot of curiosity, and controlling the audience also is very difficult. And Dr. Arup Bandyopadhyay ji has done a very balanced job. And on behalf of the organizers, I request Sri Jishnu Dwivedi ji, Director TDSG RRCAT, to come over the stage to hand over a memento as a token of appreciation from INPAC 2025. So now we will be back by 2:25. The next session will, post-lunch session will start at 2:25. So please assemble in time. Thank you.
Uh, good afternoon, all of you. Post lunch, the technical session will start in around 5 minutes. So I request all of you to take the seats in the auditorium. नहीं अभी रुक जाइए 5 मिनट 2 20 आप बताइए Banner.
Elected.
Full screen. Kar.
Good afternoon. Welcome back to session 8, technical session 8 of INPAC 2025. This session will be chaired by Dr. Archana Sharma. She is a distinguished professor at IIIT Nayapura. She is also a former distinguished scientist and former director of BTDG and a professor at HBNI BRC. She is also fellow of National Academy of Engineering, National Academy of Science, and the Institute of Engineering and the Institute of Engineering and Technology. She is also a recipient of IPA award last year and listed in the top 75 women by PSA. Welcome, madam.
Thank you for this opportunity for chairman, convener, director of RRCAT. I am really pleased after retirement. Also, you remembered me to invite. My heartfelt thanks. And let us start the session. And our first talk is today by Dr. Tapas Ganguly. He will talk about science using high brilliance synchrotron radiation sources, industry. We have already heard in detail by Dr. Mangesh in the morning session. So something about Dr. Tapas. He is a PhD holder after MSc MTech in microelectronics and BTech in BSc Physics from IIT Bombay. And his area of research work is X-ray based technique for material characterization, synchrotron beamline design and development, intermetallic alloys, and semiconductor material. He has been awarded by DAE's EST Science and Technical Excellence Award 2013 for development of semiconductor material and their characterization, a team member award for his group achievement work for utilization of 15 bending magnet-based beamlines on Indus 1 and Indus 2. And he is recipient of Indian Physics Association and a Satyamurthy Young Scientist Award in 2006. He has more than 125 publications in reputed journal. So, Dr. Tapas, you have 15 minutes, and after that I will ring the bell for 5 minutes. Okay? Thank you. And if time is left, we'll have good question answer session. Otherwise, we will have to escape.
Namaskar, and thank you, madam, for your kind words. I start by thanking the organizers for giving this opportunity to me to present to you some of the glimpses of science that we propose to carry out using the high brilliance synchrotron radiation source industry. We've heard a lot about the machine, you've heard a lot about the physics design of it, and of course, Dr. Mangesh Borge today morning also gave you a full idea about the way we are progressing in this direction, and he gave you some basic motivation as to why we should be talking about this machine as complex as the one we are talking about, this industry machine. So here I'll just give you a detail about, a very brief detail about the kind of stuff that we propose that we can do with industry. And before I do that, of course, I would like to start by talking about the Indus facility currently, Indus 1 and Indus 2 beam lines. Very briefly what we do there so that we set a stage for going ahead and seeing what are the things that we would like to specifically address at using the kind of facility that we are talking about at industry. So after I talk about the Indus facilities in general, I'll talk about the need for this new source and of course some experiments that can be done in this new source. These experiments are based, the data here that I'll show are all based on literature and available data which people have already reported in various either fourth generation light sources or advanced third generation light sources where the emittances are of course quite small as compared to that of Indus 2. So this is a slide which I think you would be aware of. Sri Tusharji, while elaborating on the activities of Indus beam lines, had also mentioned about it. But just to repeat on the numbers, we have more than 1,000 user experiments annually, more than 200 plus publications out of these 18 user beam lines. And some of the techniques that we regularly do are shown here with some techniques which are supposed to be coming up in the near future at Indus 2.
So if you look at the kind of experiments that are typically carried out, so this is only a very brief glimpse of it, and I'm just trying to talk about a family of experiments that people are doing. So these are kind of in operando experiments that we do very frequently at Indus Beamlines. They are referred to as experiments where an operation of a device is going on when simultaneously you are probing into the device and seeing what are the changes that are taking place, typically like in batteries. This is an set of experiments which people do very frequently to understand kind of reactions that are going on. So a reaction is going on and you are trying to probe how the reaction is proceeding in time. So these are called in situ experiments, typically to study catalysts and to study the way a reaction is proceeding in the presence of different environments. So this highlights the kind of work that is done related to drugs and pharmaceuticals. We have a protein crystallography beamline which primarily concentrates on determining the structure of proteins. And remember, structures of proteins are very important because they basically modulate the complete functioning of the human body, and therefore you need this structural knowledge to design medicine. So that's why it's a very important activity. And today we have more than 180 protein structures which have been determined from the facilities at Indus, and even the Indian pharmaceutical industry today is very active in using the facilities at Indus Beamlines for their drug development activities, and the data that they take from here essentially helps them to get licenses to market those drugs. And these are some examples of the kind of experiments which we have done for ongoing DA projects. This is a picture that shows how we are trying to understand the strain in the at the joints of zircaloy SS alloys, or this is a strain in a heat exchanger tube, and several other activities related to finding out impurities in uranium and materials and other charged states of uranium in the fuel pellets have also been studied. These are examples of some work which we have done for ISRO. So we've done a lot of work on various activities, on various disciplines, but this slide again is similar to the one Dr. Mangesh showed in the morning. So we do have certain limitations. He mentioned about it, so I'm not repeating it. But to overcome these limitations, we need a 4th generation light source. We need a light source that has a significantly better emittance as compared to the one we are talking about today. In addition to emittance, there are other factors which we'll also come across, discuss. So what are we looking for? We're looking for an extremely small source size and divergence of the photon beam, which essentially means very high brilliance. We're talking about a highly coherent source, and these are related. I mean, if you have this, then you have this right away. In addition to that, we're also talking about a large energy range of photons. Typically, the high energy part of the available photons should exceed around 200 keV. So very large energy range of the photons are being also talked about. Also, the time structure of the pulses is a very important aspect. I will not talk about it here due to the paucity of time, but then this is another aspect which can also be used for users for several kind of experiments. So in terms of numbers, these numbers are very familiar. We have few presentations here, including the one which Dr. Mangesh gave today morning, and the ones which you have seen through posters have been talking about these numbers here. And now we'll try to understand the consequence of these numbers in terms of the kind of experiments one can do. So what is low emittance now? So this is just a brief review of some typical standard expressions that are available in literature. So if you have a filament electron beam, I mean a single electron beam, with practically 0 dimensions going through an undulator, and it is emitting radiation, then it has a natural spot size and a natural divergence. This is the consequence of the diffraction limited character of waves. So this is the minimum you can anyway talk about. But actually what you see in real life is that size and divergence which is much bigger than the one that you would ideally expect. And this is because of the fact that the electron beam itself has a finite size and divergence, and essentially they add in quadrature as shown here to give the final source size and the source divergence, similarly in the x direction, in the y direction. Now, if this final dimension is very close to the dimensions which you actually expect from just the bare size which you expect from a diffraction effects, then you call it to be a diffracted limited source. And you hear this term diffraction limited storage sources, DLSR, you hear about these terms. This is essentially the case when the source broadening because of the source is either less than or at least equal to that which the source ideally would have only because of diffraction effects. Okay. Yeah. Now, if you have a low emittance, you have a low spot size and low divergence, as we saw in the previous slide also, and that also translates to an increased coherence in the beam. So if you have a single electron beam, which is a single electron beam or a beam with a zero emittance going through an undulator, then the beam that is being emitted, the X-ray source, X-ray photons that are being emitted are perfectly coherent because it is a point source. They're perfectly coherent. And this coherence is destroyed because actually the electrons which are present in the storage ring are distributed inside the bunch, and each of these are a source of radiation, and they would naturally not be exactly in phase, and that is what leads to partial coherence. Thus, lower the emittance, higher will be the degree of coherence, but definitely not 100%. And you can always determine this partial, the fraction of the coherence through an expression of this. Please note that these are approximate expressions, and they, depending upon the assumptions, these expressions could be slightly different. But if you evaluate it, you can see that in Indus3 you can have a coherence fraction of around 5% for a 10 keV photon, given, of course, the kind of undulator and the kind of optics that one has chosen. But typically these are the kind of numbers. Thus, if you have a brilliance of 10 to the power 22 in standard brilliance units, you still have excess of 10 to the power 20 photons, which would be essentially coherent, completely coherent, and therefore you can use them for significant kind of experiments, which would not have been possible at Indus 2. So when we talk about focusing, one of the very important aspects and very important category of experiments is an experiment that you do where you focus the X-ray beam onto the sample, and smaller this focus spot you can get with a large number of photons on the sample, the larger will be the information content in terms of the microscopic or nanoscopic understanding of the material. So that's very important. And therefore, the typical aim would be that a figure of merit of a source would be how small spot size of the X-rays you can get. If you look at Indus 2, we can get to the order of around 4 micron into 4 micron today, with a photon flux of around 10 to the power 7, 5 10 to the power 7 photons per second at 10 keV. And therefore, if you use this spot and you start scanning, you can generate an elemental map through a fluorescence measurement, for example, and these are results that have already been published or have already been obtained at Indus 2 BL16. But please note that these numbers are quite small, and therefore there are limitations in the kind of experiments you can do. Similarly, this focal spot is quite large, and the aim would be to do much better. How much better? Let's look at some examples. For example, even in a third generation light source like Petra 3, one of the most advanced third generation sources today with a 1 nanometer rad emittance, we are talking about, they can actually talk about focal spots of the order of hundreds of nanometer into hundreds of nanometer squared with 10 to the power 9 photons per second. Similarly, in Spring 8, again, this is the Spring 8 when before any upgradations have been talked about. So it is the Spring 8 which is operational, a third generation source, but a very advanced source, of course. You can see that focal spots of this order with this much of photons, 10 to the power 10 photons, are still available. So they can do much better because their emittances are smaller. And if you look at NSLS2, you've got similar numbers of 15 to 50 nanometer square possibilities. And of course, in the nano diffraction beamline at ESRF EBS, which is after the improvement and the modification of the ESRF to a 133 picometer rad machine, you can see that a 15 to 50 nanometer spot would have up to 10 to the power 12 photons per second. That's a very large number of photons that they can actually provide for the users. And why do you need such small spot sizes? And we can see two such examples. This is a thin film, and the X-ray spot essentially scans around this region, and you can get the strain across the thickness of this film. The film itself would be just about a micron. And these are published literature. Some of them are a bit old, but highlighting the importance of the small spot is what my aim was to show this example. Similarly, this is an example where a small spot size has been rastered around the sample, and the grain boundaries have been observed, and the elemental composition in the grain boundary and this effect on the performance of the material has been seen. Very important aspect of having a lot of flux and a small spot size is for protein crystallography or macromolecular crystallography. We although have been doing a lot of macromolecular crystallography activity at DL21 at INDORE, but still there are a huge class of materials which class of proteins which we cannot study because they actually crystallize into very small dimension crystals of the order of a few microns or even less for that matter, and they would therefore not be possible to be studied with INDORE where the focal spots are much larger of the order of hundreds of microns. So we are not in a position to study that complete class of proteins. And please note that this class of proteins actually are the targets for more than 60% of the drugs. So we are basically missing out on a huge amount of opportunity to work on systems which are actually very important. And in fact, if you look at the international scenario, during the COVID-19, you can see that there was a lot of work done and more than 800 structures were determined which were related to the SARS-CoV-2 virus. And eventually, the medicines which came out in the market which actually had a lot of influence from the data which was taken at some synchrotrons, typically APS. And similarly, of course, time-resolved measurements of biological processes are very important. And of course, the structural analysis of drugs are also regularly carried out at these sources, which highlights the importance of these sources for biological applications. I talked about the coherence, and we spent a little bit of time about the coherence because that is a very important aspect of a fourth-generation light source. The coherence essentially helps you to make very good images. If you have the image, making an image implies that you are in a position to find out how this boundary is defined, how this boundary is, how you can resolve this boundary, how well you can resolve the difference between the target and the boundary. And this is possible because, this is done through, and if a coherent X-ray source is used to illuminate this sample, then you can see that there will be some interference patterns at the boundary where there is a change in the refractive index between the material and the adjacent material, and that gives you a sharp boundary of one material with respect to the other, thereby helping you to form very sharp images. This is called a phase contrast imaging. If you look at an example, this is actually aluminum matrix with silicon carbide particles. You can see that small particles and small of these particles which are reinforced in this aluminum alloy matrix can be seen through data which was taken in one of these advanced sources. I think it is ESRF where this data was taken long back. But a similar sample could not be analyzed at INDORE because of the fact that the significant amount of coherence was not there, and therefore the difference of refractive index between silicon carbide and aluminum was not large enough to get a proper interference pattern and thereby generate a proper phase contrast and a proper image. So it is very important that one generates images with coherent beam falling on the sample, or at least partially coherent beam falling on the sample, so that the images are sharp. And you can see some of the numbers. Typical characteristic is called a coherence length, and the coherence length at INDORE is over the order of 5 microns, which is over the order of 250 microns in the case of ESRF. So you can see the difference, the quality actually shows in this difference of numbers. Another very important aspect of using coherent beams is actually trying to do several experimental techniques which were otherwise not possible with an incoherent source, or even with a very poor coherence fraction in the source. Such an effect is one such 5 more minutes. Yeah. One such effect is called the Bragg coherent diffraction. If you have a coherent beam falling on a sample with a difference with a variation of electron density across it, then it generates a pattern which is of this sort. So besides the diffraction peak, you have the coherence leading to interference pattern from the electron density from the scattered beam, and this can be transferred by numerical calculation to get back the electron density distribution of the material. This is referred to as a lensless imaging, and this is the standard technique is called the Bragg coherent diffraction imaging. You can see an example here where a nanoparticle has been applied a bias and how the strain generates in this material as a function of time. This is one of the very recent measurements reported at the MAX 4 after its upgradation. So these kind of experiments are simply impossible to be done on a machine like INDORE, or for that matter, any machine that doesn't have a significant amount of coherence in the source. And these are what are kind of things which definitely one would like to do in the future. So regarding emittance, the summary is here. I would not like to go through it because I've already said everything. But to the main idea is that low emittance helps you to go to smaller spot sizes, helps you to get higher coherence and better images. The other part of it is the higher energy part, which I will very briefly mention, and then I'll stop. The high energy is required for very specific reasons, because you need to penetrate inside the material. So high energy photons are in a position to penetrate deep inside the material, and this would not be possible without a machine like a 6 GeV machine with a lot of photons available at energies of the order of 150 to 200 keV or so. And these numbers show the penetration depths. And this is an example where tungsten has been imaged, and this is a tomograph of the tungsten where the porosity inside this tungsten material has been deciphered and has been seen very easily. But if we try to look at examples at INDUS 2, you can see this is an image of a bone. Bone is a material primarily consisting of low Z materials and not very dense. So you can see a very nice image of a bone, but the same thing if you try to do for an 1 mm thick iron, you can see nothing inside it because everything is absorbed. But if you talk about low Z materials like polyurethane foams and things like foams or silicon-based foams, you can see you can generate very good images and tomographs. So although we are in a position to do extremely good imaging, but only for low Z materials, when it comes to high Z materials, which are typically the engineering materials, you need much higher photon fluxes and much higher energy photons, of course, with high photon fluxes also. And again, an example of the need for high brilliance, a large number of photons on a sample helps you to take a data in a very short time. And therefore, you are in a position to see a process in motion. I talked about the in operando studies and in situ studies at INDUS 2. They are typically done in matters of few seconds or tenths of seconds to minutes. But here you can see some data taken of, like, this is the data of a shock wave propagation. So they are basically scattering data, X-ray scattering data. And you can see the time. Time is only 5 microseconds, then 4, you can see 0.0, it starts here, and this is 1.35 microseconds, and this is only 5.58 microseconds. So you can see within a few microseconds, you can take all this scattering data. And the same thing is shown here. You're taking 30,000, excuse me, you're taking 30,000 frames per second. Imagine how many, within a few microseconds, you're taking a complete image. You're taking a complete image of a system while it is in process. This process is in operando laser additive manufacturing process, and this additive manufacturing process has been analyzed in fractions of a second. These are things which we talk about in a future source. And this is another example of a battery in operation where, again, in a fraction of a second, you are talking about this X-ray scattering data, which is being used to study the processes going inside a fuel cell. This is the example which is taken from APS. So the role of brilliance, therefore, is quite clear that you need high photon fluxes in the case and to get high photon fluxes on the focus samples, on the focus spot sizes. And of course, if you want to do time resolved measurements in microsecond intervals, you definitely would like to have a source like HBSRS INDUS 3. And what we can do, I'll skip this actually, but just to mention that reactions related to energy materials, which is a very important topic of study today, batteries, electronic devices, then you can talk about various kinds of protein structures, dynamic behavior through serial crystallography, synthesis of new materials, high resolution imaging to study them in situ and in operando studies, imaging of engineering materials, even characterizing materials in the gamma ray, especially those that are required for X-ray mirrors, and very high pressure kind of measurements, and a host of other things that you can do with a machine like INDUS 3. So these are the kind of proposed beamlines that we are talking about, and this essentially covers the complete cross-section of the interest of the Indian scientific community as we know today through our experience at INDUS 2 and through our experience with the community at large. And hopefully this will be in a position to address to most of the needs of the community initially. Of course, these are only 13, and as Dr. Mangesh Borge also mentioned in the morning, and as I also flashed, we have a provision of about 50 beam lines, 25 on the insertion devices and 25 on the bending magnets. So we have much more to go and much more to expect in the future, actually. And just to show in a snapshot, synchrotrons cover practically every aspect of science and technology and every aspect of engineering that you can think about. And having a machine like Industry is invaluable for our overall goal of Atmanirbhar Bharat. With this, I would like to acknowledge Director RRCAT for his continued guidance and support. Shri Umesh Malshi, Director RRCAT, Shri Tushar Puntambekarji, Additional Director RRCAT and Director EAG for their continuous guidance, support and handholding throughout our activities. And definitely all the colleagues who are working at the Indus synchrotrons and the beam lines require a very special mention, because it is their efforts that makes the machine running the way it is and helps us to generate the data from the user side, what we are talking about. And of course, the Industry project team, which has been working tirelessly for the project. Of course, Dr. Mangesh Borge mentioned all about those efforts and those results in the morning. So thank you everybody for that. And I don't know whether thank you didn't come. There was a thank you also. So thank you everybody.
Okay. Thank you, Dr. Ganguly, for nicely elaborating what are the utilization presently being done, limitation, and then is future scope for Industry. Any quick one question we can have? I think already everything has been explained nicely. So on behalf of organizing committee, it is my pleasant duty to give you a token of appreciation. Now I welcome Shri Yashpal Singh ji. He is power supply expert. He is going to talk about recent developments in power supplies for accelerators at RRCAT. Most of you may be knowing him as an expert in interview committee, promotion committee, in so many experts. He has academic career of BTech Electrical Engineering from AMU. He has MTech in Power Electronics. His area of research is pulse power supplies, pulse modulator, high current, HVDC power supply, active filters for power quality applications, and DC slide active filters. His achievements are group achievement awards of DAE and university medal. He has more than 30 publications in research journals. So I welcome Yashpal Singh ji for 15 minutes presentation and 5 minutes for question, answer or conclusion.
So thanks to the organizers for giving me this opportunity to speak about the accelerator power supplies in this forum. And thanks, ma'am, for reading out my introduction too. This work is basically on behalf of PPSS APSD and team HVSS APSD, which I have included here. And some of the work is I've upgraded to the existing machines, additions. And then some of the work is, in fact, the upgrade to the existing hardware in the running machines. So I will continue here. This is, in fact, yeah. So Indus accelerator complex, all of you know that there is a microtron followed by microtron is an injector to booster, and booster is 450, 550 MeV machine, which fills the Indus 1 and Indus 2 with a selector magnet dipole in between. So this is here I will be talking about this is a value addition to Indus 2 finger kicker systems. We have added two vertical and horizontal finger kickers to Indus 2. And basically, these systems will be required to study the linear, nonlinear dynamics of the beam. So there are two kicker systems. One is horizontal, another vertical. And these kickers can give beta tones. I mean, these kickers magnets are energized by two separate power sources. And they will generate beta-tron oscillations in a stored beam, few bunches of Indus 2 in a synchronized operation. So these power sources actually are required to deliver a high current pulse of less than 1 microsecond to meet out this requirement. So that the bunches which are placed on the top of the sinusoid should not get another kick after the one revolution. That I will explain in the slides to come. And these tools can be used to study the linear and nonlinear dynamics of the beam. So this is a value addition to Indus2 machine. And these are some typical specifications of these two kickers. So one of them is vertical kicker is requiring a current of 5.5 kiloampere, and the horizontal one is 2.66 kiloampere with a pulse of strictly less than 1 microsecond, so that the beam gets one kick only. Now, the challenges in realizing these kickers was that, as usual in almost all the pulse power sources, they have got large GFIDT, requires a very compact design, and reduction of stray inductances has to be kept in mind while designing the pulsars. Otherwise, the working voltage goes on quite high, and sometimes it may becomes non-realizable. So this is the typical, power circuit diagram of this kicker system. Typical power circuit, pulse power circuit for both the kickers. And here you can see that we are using a high voltage diode here in series with a saturable inductor LS1, because working voltage and currents are quite high, so switch used this thyratron. There was no other option available, realizable option at that time. But as I told you that the half sinusoid should not, the electrons should not have another kick after one revolution. So the current pulse has to be terminated just after half sinusoid. So the design of this LS1 in association with this high voltage diode makes this critical components of the circuit, just to terminate the pulse just after one half sinusoid, because thyratrons and such high voltage plasma switches can give a lot of reverse current in highly underdamped circuits. So now this is the actual device which is in the ring. Here is the kicker magnet lying there, and this is the pulse power supply, and here you can see the current pulse and the magnetic field. The time, I don't know whether they are readable. This time of the pulse is shown in this box, and this is strictly less than 1 microsecond, some 950 nanosecond or something like that. So basically, in the actual experiment, the electrons bunches will be placed here on the peak, some of the bunches, and after the one revolution of the machine, when they come here, they should not get any kick. So that's why the requirement of less than 1 microsecond pulse. And now this is the horizontal finger kicker, again the similar device, and installed in the machine at another location. Now, after these finger kickers, now there is another value addition has been done to IRFEL facility. So here, in fact, we have installed this fast steerer magnet, and this is also a diagnostic device, and this will be used to estimate the lasing efficiency during and without lasing. So requirement of this, sorry. So requirement of this pulsar to meet the objective is stated that we need a current of 2.6 kiloampere with a linearly rising pulse of 7 microsecond. Now these are some typical specifications mentioned here, and this linearly rising pulse will be used to map the spent beam, electron beam, and that mapped beam will be analyzed to find out the lasing efficiency. I mean, how efficient this laser is working. Now here for this, to meet out this 2.6 kiloampere with a 7 microsecond rise time, we have used this type of circuit. And in this particular circuit, though, I mean, this is a typical circuit to realize this requirement, but we have coupled this bunch, this high current pulse of 7 microsecond through a transformer here, fast transformer, and thereby giving an advantage to use a switch with much lower current. And this is a semiconductor switch to realize the requirement. So that was the, this transformer to pass this linear current pulse current. This was a specialty design of this pulse power circuit. Rest, otherwise, it is a conventional circuit. Now you can see the implementation. I mean, this is the the pulse power circuit, and this is the device installed in the ring. This is the current pulse, and this is the zone of interest. This is between these two markers. This is the zone of interest which will be used for the on the spent electron beam. This is the voltage shown across the switch at the time of switch off. We are opening the switch, some higher voltage appearing, and recorded stability data is here. So other than this, we have developed a power supply for microtron cathode. And this power supply is already existing in the machine. I mean, this is being used continuously, I mean, the previous power supply. But here we have developed another one as an spare. And this power supply is having, we have added some interlocks to make it more reliable, rugged, and I mean, dependable supply to upgrade the existing one. So this power supply is rated for 45 amperes, the same rating that of previous power supply with a stability of plus minus 0.1%. And here we are using the SCRs as the switch. Power supply delivers the synchronizing signals also on the zero crossing of the current. And these signals are used to synchronize the machine events. It goes to the timing distribution of the machine control. Now, this is a very new development. This is an effort to test a scheme which will be used for the powering the injection kicker magnets of industry. So far, the requirement which we have understood from the existing discussion which is going on, we have realized a pulse which is the sinusoidally rising pulse of 76 microseconds with a fast fall. And this is a prototype development which we will carry forward to meet the requirement of many other pulsars. So just to see the behavior of the pulse power circuit and the switches, this is a development aimed at the industry. Requirement is something like this. This is for basically these ratings are meant for injection kickers. 76 microsecond half sign rise with a fall time of 850 nanosecond. That was the targeted figure. And the requirement is for injection kickers of the booster. So magnet inductance so far known is 1.5 microhenry with a peak current of 550 ampere. And this pulse has been realized with a pulse power circuit and semiconductor switch. To realize this fast fall, there is a circuit here which facilitates the fast fall of the current and gives a fast and linear fall with the help of this capacitor and diode. So these are high voltage devices, and in fact we have used these devices earlier also, and we are banking on the development of these semiconductor primarily IGBT switches for the development of these pulsars for much higher and current rating. There are many more of the similar nature for the machine, and they are still under discussion. So I mean, this is a first prototype development. And this power supply, actually, these are some of the waveforms from the power supply. So rise time, fall time, and then this is analyzed fall time. The high voltage which is getting kicked on the device. And for the long time reliability study also, this development was important because we want to see the behavior of the IGBT switches under this type of stress. This particular pulsar is having a specially designed drive circuit for IGBTs, and especially for the fast fall turn off of the devices. Now this next work is this is an testing, installation, commissioning of magnet power supplies for LINIAC 4. In the morning session, there was a talk on LINIACs from Sri Jishnu Dwivedi ji. So the development of 15 kilowatt LINIAC device, 10 MeV 15 kilowatt. Accelerator Power Supply Division contributed to LINIAC 4, including the device at this machine we have implemented at Microtoll, Bangalore. So for this 15 kilowatt average power industrial LINIAC, this development was aimed at. The power supplies were, used to power the focusing solenoids and LEVT solenoids, 270-degree bending magnets, quadrupoles, steering coils, scanning magnets, and all. These scanning power supply, some further work is going on this, but this particular implementation used the already designed and developed the scanning magnet power supply. And since the LINEX will be used for bulk and radiation and medical food products, so a lot of reliability and testing, that was kept in focus to see that the power supply works continuously without any failure for long hours. So these are some of the typical tests we especially carried out to see their long-term operation. Long-term 8-hour stability test was conducted. Then we continuously operated these power supplies for 120 hours, 5 days in continuous operation and log their data. And the power supplies are, EMI pre-compliant with this CISPR 11. And then to see the reliability, again the thermal performance, we carried out a thermal imager after one hour of operation of the power supply. So maximum temperature rise was noted as 30 degrees centigrade, and we saw that all the parameters are there in continuous operation well within the reliable operating limits. And these are some of the photographs of power supplies. So these power supplies has gone into the LINEC 4 machine. So focusing solenoid power supplies are in rack A, then steering power supplies in rack B, and then scanning magnet power supplies in rack C. So these are already installed in the machine, and LINEC 4 has been tested with these power supplies to a power of 15 kilowatt. These are some of the test results on this 270-degree bending magnet power supply stability figures. Then the long time testing, 24 hours by 5 days. This is the data from the continuous 120-hour operation of the magnet power supply. And this is the EMI pre-compliance result with the thermal imaging data of the power supply. Now, this is this stepped sawtooth scanning magnet power supply is an enhancement of features on the existing scanning magnet power supply. So this power supply will go in. This is still developed in lab and tested, but yet to be commissioned in the machine, integrated and commissioned. And this testing with the integrated control is going on. Power supply has been developed, and features of this power supply which are different than the previously existing one is that the power supply ensures precise beam positioning, enables proper handshaking between power supply controller, scanning power supply, LINEC master control system, and conveyor system. Basically, during the scanning, if there is a trip on the LINEC by any system, to ensure that the scanning is going on right at the place where it was broken, this power supply will ensure the synchronized operation using a stepped scan scheme. And then power supply will integrate with the splicing feature also to start the radiation from the interruption point, reducing product rejection. So if there is if the product faces a trip from the LINEC subsystems, then the restart of the radiation can be done right from at the point where it was left. So this power supply basically uses a full bridge power converter, and this is a bipolar power supply with plus minus 15 ampere of current.
Yashpalji, 2-3 minutes, sir.
Okay. So this is the operating voltage, and there are some of the load parameters. Uses a closed loop control. I will rush through, and synchronize. This operates in sync mode of operation. So during resumption, these are some of the functions which power supply will communicate with the control. And I think this is a typical block diagram. This is master control. This is power supply control, and this is power supply. So there are two interlocks. The two interlocks ended together goes to the master control to trip. If any of the interlocks goes fail, then the master control will be tripped. And the power supply works on AC/CT signal. So to bring the current at the level at which the interruption took place. This is a lab test with the synchronized triggers. Here, this is a test on the power supply depicting that, let us say this interruption of the product took place here. This power supply is running continuously from positive current to negative current, and let us say this interruption got here because of some trip. Then you can see that once the interruption is taken away and I mean there is a command from the control to restart, then the power supply starts from the same point with the same di by dt as if it was continuing here. This line extended further before the process was interrupted. So basically, this is the test which is being done to see that the power supply is effectively working. Process interruption takes place here. Process resumption starts here with the same features on which it was left. And then there we have developed a power supply for superconducting wavelength shifter magnet, which is already under development and testing. And a lot of, work has gone in the device development, WLS development. The power supply for powering the superconducting coil of this magnet has been developed by APSD. And this power supply uses a full-bridge PSPWM-based circuit and uses ZVS of MOSFETs, high stability power supply, and operates in closed loop control. Power supply has because this is a superconducting coil powering power supply, so it has got the features of quench detection, and power supply is turned off at an output of DC contactor is opened when the quench is detected. So this is the simple power circuit along with control. And except some of the protection of a superconducting magnet, this power supply, power converter, and its operation is similar to a typical power supply. Stability is plus minus 50 ppm. And this is the stability with the load magnet of 8 Henry inductance. These are some of the result of power supply. This power supply is a, unity power factor control at the front end. So you can see that this is drawing a unity power factor current from the source. And these are some of the switching waveforms. And efficiency of the power supply is plotted here with output power. And these are some of the references which I have already mentioned in the presentation. So some of these papers has been presented in the InPAC already. So for the details, one can refer to those papers. Thank you. And in all this development, especially the development of pingers in INDORE, that was a cumulative effort of AMTD, EUHV, BDCSD, many groups there. And that was a integrated joint effort. So I acknowledge the contribution of all of them. The work in IRFEL is also basically a work between APSD and AMTD. And I acknowledge the contribution of our additional director Tusarji, especially in that development of finger kickers and installation. Thank you.
Thank you, Ispalji. Now you know why all these accelerators are working so stably, because of good thermal management and strict stability of the power supply, including magnet parameters. So any question? Continuous evolution of power supplies, parameters, performance. So no question? Okay. So on behalf of organizing committee, we'll have a token of appreciation for you.
Yep. Okay. Thanks, sir.
Now organizing committee has to give some important and interesting information to you.
With due permission of our session chair, I would like to provide this important information regarding the transport arrangement that has been made for today's banquet. I request all the participants to kindly take a note of the timings of the buses. Thank you.
Now we'll go for 7 industry participants will give their presentations in 5 minutes. I hope all of them are ready. First presentation is by Rosalina. All of you may be knowing they are the only supplier of modulators. And I'm really thankful during COVID period, he has supplied magnetron modulator to us besides all those tough period. So Mr. James is presenting. The 5 minutes for you, sir.
Okay. Namaskar to all of you. As Madam introduced me already, we are well known in India. Rosalina is purely an Indian company. Name might seem little foreign, but we are purely Indian. We represent EFT and we represent Scandinova. So Scandinova supplies high voltage pulse modulators for magnetrons and klystrons, and we have a different range starting from 100 kilowatt onwards to 200, 300, 400, 500. So this is these are made to orders. So anytime you have a requirement, you will have to give your specification, and then Scandinova will manufacture and give them to you. The other series is, the earlier series was K series for klystrons, and then we have the M series for magnetrons, which are used in radiation therapy, cargo scanning, radars, and other, there are a lot of magnetron developers. They use our modulators for testing their magnetrons. So you can try ours also. Next, we're coming to AFT. AFT has got a wide range of products, right from circulators, loads, to whatever you can ask from them, they supply. So you have a very wide range. You have customized isolators also, or if you want them to design something for you, then they can also design. Well, that is what I had to say. So if you have anything, can you please put your questions or your emails to these addresses? And if anybody has any specific question right now, please let me have it.
Any question? He is very good in responding, very quick, anytime, phone or mail. That is my personal experience.
Thank you, ma'am.
Yeah. Thank you, Mr. James. Now we'll go to next one. Optimized Solutions Limited. Sorry. On behalf of organizing committee, we'll appreciate your efforts.
ऑप्टिमाइज ना इसी में करना चाहिए हाँ इसी राइट इससे भी राइट करें राइट करें राइट हमारे में एक और है सर इसके बाद एक और प्रेजेंटेशन है प्रेजेंटेशन इसके बाद एक और क्या नाम से उसी में ही है एक और क्लिक करना पड़ेगा 2 मिनट चाहिए सर उसको इसके साथ ऐड कर दिया ठीक है ये ना इसके बाद ठीक है कोई बात नहीं ऑप्टिमाइज ये कर देता हूँ अभी ठीक
है 5 minutes.
A very good afternoon to one and all. I am Arshad Pathan from Optimized Solutions, Ahmedabad. Actually, I'm working as a senior technical consultant engineer in Ahmedabad. Optimized Solution is basically a certified solution providing company. So basically for a quality assurance, we are following AS 9100D certified, ISO 901 certification, ISO 27001 certifications. We are also a part of Data Security Council of India for promoting data protection. So about us, like we are having 100+ engineers, which are expert hardware engineers, developers, analysts and scientists. We are having a past experience of 20 years
So far, we did projects somewhere around 1,000, and we have satisfied users almost around 500, and annual growth rate of 30% we have. So what are offerings? So offerings are like test and measurement instruments are there for the distribution side. We do automated testing, product engineering services, monitoring and automation, digital transformation we do. So basically, majorly, you know, Optimized Solution as a test and measurement instrument company, distribution solution providing company. So we have a collaboration with Amitech, programmable power for the power supplies. So that will be somewhere around, we give solution up to 2000 volt in voltage range. In current range, we are giving up to 8000 ampere and power up to megawatt with the help of Amitech. We have collaboration with the NI instruments. So we do provide LabVIEW softwares, data acquisition system, PXI systems, and compact Rio we give. With the help of Tektronix partnership, we do give oscilloscope, mixed signal oscilloscope, mixed domain oscilloscope, real-time spectrum analyzers. With the Kithli instruments, we have SMUs, this semiconductor characterization systems, we have digital multimeters, we have high precision digital multimeters we have. With the help of Anritsu, we give solution for the RF domain like VNA, spectrum analyzer, or signal generators. We have a collaboration with Fluke Instruments, which provides us the predictive and preventive maintenance instruments with the calibration instruments. So far, we did automated testing we do end-of-line test, functional testing, R&D testing. In product engineering services, we do develop the new product, customized hardware development we do. We basically have a concept of build to print and build to specs. So in build to print, like we need a Gerber or some schematic from your side, and we do develop the product at your end. And in build to specs, we need a specification from your side. We do R&D, and we like the idea we convert your idea into the new real-time real world product. So in product engineering services, we do like that. In digital transformation, we do asset monitoring or deployable dashboards we maintain. And for the automation, we are having a partnership with Schneider Electric. So with the help of Schneider Electric, we do the automation, PLC system-based automation we do. So for the quality assurance, again, we follow all these certifications. So we do have clean room facility at Gandhinagar. That is 10,001 clean room facility. So far, we have developed some product engineering services like alarm module system, video switching module, digital input-output electronics module, high-speed serializer and deserializer. In automated testing, we developed DC to DC converter, AT for negative hydrogen ion extraction, and HHF testing facility. In digital transformation or automation, we did screen thermal test system, remote asset, machine monitoring, thermal conditioning unit automation, liquid flow monitoring solution. So all these solutions we are providing with the help of tools. So we have domestic presence in like every state. So you can see Haryana, Gujarat, Maharashtra, Karnataka, Himachal Pradesh, Uttar Pradesh, Assam, Jharkhand, Madhya Pradesh, Telangana, and Tamil Nadu. So we did all the projects for all these organizations. Successful projects we did for all the organizations. So these are the clients from the private and government organizations we have. We did some technology transfer also from DRDO related to UV disinfection system. With ISRO, we did like technology transfer for the long-range surveillance camera. For SIMPER, we did collaboration for data mining for the like sensors data we have to collect under the earth up to last 400 feet. So these are the technology tools which we are using: LabVIEW, NXP, Xilinx, Renesas, Node, Amazon, Web Series, as a Zigbee, LoRa, MongoDB, PXI, analog devices. These are the, so basically the technologies which we are working on. So industries we serve: manufacturing, engineering, oil and gas, utilities, e-commerce, defense, R&D, healthcare, logistics, and heavy engineering. So I would like to call Ajay for 1 minute to give the glimpse on Amitech.
5 minutes are over, huh? Please. We'll go to next one. The next one is from NKRF Products and Services Limited. See.
Just 2 minutes.
Just 1 minute.
Good afternoon, all. I'll talk about Amitech. Actually, Amitech is a US-based organization. We are into different domain, and they have almost 100+ business units. So I belong from the programmable power business unit, where we have different kind of the high performance precision power supplies. So I'll talk about this, whatever we have done so far, leading supplier across the globe in AC and DC as well. And we are recognized from the Frost Sullivan. This is a US organization which they are rating into the power segment. And we are based in San Diego. This is our journey. We are not.
No, just a minute. It is optimized solution or RF?
Yeah, optimized one of our partner.
अच्छा अच्छा.
Yeah.
तो आप लोगों
So this is
को
our-
मेडल साथ में देंगे.
ले लेंगे मैडम, कोई बात नहीं है. So this is our journey. We started from 1930, and almost you can say like we are a 100-year-old organization and pioneer across the globe into the field of power electronics. These were earlier individual companies. Amitech acquired one by one, and now it's become only Amitech Programmable Power. So we are into this segment like different brand. California for AC power source, Sorensen for DC power supply, Elgar custom products, and BTI for high precision data acquisition system. We are into very compact kind of a very slim form factor. If you see these are our power supply, we also brought some instrument in our booth. You can see. I invite all of you to please visit us. And these are our major segment where we are working with like any, especially defense, R&D organizations, where they talk about the quality, they do not compromise on the quality. So these are the organizations where we are working like commercial and industrial test and measurement, stimulus power, semiconductor, and then government defense, especially avionics and engineering. Then we have energy, oil, gas, and solar photovoltaic also, and commercial aerospace. Across the globe, any organization related to avionics, they are using only Amitech products. And we are leader, as we said, we start from the power supply as low 60 watt to several kilowatt as well as megawatt in very sleek form factor. If you see right side, these are our product images. Large R&D team we have in the US and as well as in India also we do have. And our repair service, we do have our own R&D center and service center based in Bangalore. So for any kind of the support service you need, we are always there. Thank you, madam.
On behalf of organizing committee, I invite you to take this appreciation from.
साथ में ही है, साथ ही में. हाँ, ठीक.
Next one is AD Equipment and Technologies. AD Equipment and Technology.
इसके है ना.
You have 5 minutes.
AD है कि NK?
Good afternoon, one and all. So I am Dhiren Mungra, an application manager from AD Equipment and Technologies. So we are basically a test and measurement solution provider based at Ahmedabad. We have a different offices and representatives at the different locations of India. So we provide the complete test and measurement solutions starting from a small multimeter to complete lab development. Yeah. So we have a expertise in the different field of like a digital RF, like automation. So in government research and development. So in different different segments, we provide a complete range of test and measurement solutions according to their application needs and the challenges they are facing in their day-to-day life. We are partner with different global brands like GW Instech Taiwan, Rode and Schwarz Germany, then Onosoki Japan. So in the different segments, they are expert and we are collaborating all of them to providing the complete solutions. Yeah. So this is just a glimpse of our solution, range of the solutions. So mainly like according to this application, it caters the programmable AC/DC power supplies. So it starts from 50 watt to 50 kilowatt in a very compact form factor with the height of a 4U. And it could be a programmable with open platforms as well. Then we are in process to developing an indigenous power supply at our own with our own team, and soon we will be, coming up with a 10 kilowatt and 15 kilowatt power supplies with a 3U height with the complete like our Indian development. Then we have expertise in impedance analysis, LCR measurement. There are a lot of different kind of test and measurement tools and equipments that we incorporate with our projects. We also do the integration projects as per the application, along with the hardware and software. Then we have a complete range of RF test and measurement solutions, EMI, EMC test and measurement solutions with one of the very well-known brand like R&S. Then we have high voltage test solutions like surge, EFT. So we have a complete electrical immunity plus EMI, EMC kind of a combinations. Then we have a LabVIEW software development team and software solutions as well. We also have expertise in providing the sound and vibration test and measurement solutions. Apart from that, like a mechanical test and measurement solutions, like either it is a strain, force, vibration, load, displacement. So altogether, we have a complete range of sensors plus data acquisition system plus analysis software, as well as we have a complete range of measuring chain according to the applications. Yeah, these are the, our technology partners. Like you must be knowing GW Instech for basic low power test and measurement equipments and tools. Then we have R&S for EMI, EMC, RF and oscilloscope range of test and measurement solutions. Then we have INO for high power testings. Then Prima for surge, EFT and electrical immunity testings according to the IEC, EN or any sort of a global standards. Then we have Onosoki Japan from Japan for sound and vibration range of solutions. Then like HBK Germany for mechanical measurements. Then software like NI LabVIEW. Then Kistler is again for they are well known for like piezoelectric sensors for to measure the very high range of the vibration, shocks, etc. Then Hyoki, like power solutions. And Xenonoe is one of the well-known for programmable AC and DC current source. So where we need a pulse current, high power pulse or a current pulses, there we'll use these applications. Yeah, at the local front, like we have our resellers or maybe a channel partner, like you might be facing every day Rudraksha and OSPL. So they are our local guys here. Day to day, they interact with the different part of a team, and at the back end, we are supporting them to provide the complete range of solutions. So as a whole, we are a team to provide the complete range of solutions. Yeah, these are the list of a very few customers, like government customers, RRCAT, BARC, ISRO, and different part of like our defense teams. Then in industry, we cover different and varieties range of the customer for the different part of, solutions. We have our head office at Ahmedabad, and we have authorized service center at our Vadodara office. Then we have representatives and engineers at different locations of India like Bangalore, Chennai, Delhi, Pune, etc. Yeah, thank you.
Thank you. Yeah. On behalf of organizing committee, please accept our token of appreciation. Yeah. I think now I invite NKRF Products and Services Private Limited. I think there was some confusion.
इससे फॉरवर्ड होगा, इसे बैक आगे पीछे ना।
Hello, everyone. My name is Nitish. I'm from NKRF. I would like to thank the organizers of InPAC and all the people here from all the various organizations behind this. It's an honor to be amongst you and to support the different missions and programs that we have, including the industry that we hope to participate in coming up. A brief introduction about NKRF. We are a 40-year-old company and with a lot of heritage in the military side of the country. We are India's only indigenous RF cable assembly manufacturer. We started this in about 2011, where we took a technology transfer from America to do this kind of work. What differentiates us from anyone who can make a simple RG cable is that we are space qualified and we are qualified by SEMILAC, which is the military, which is the DRDO lab in charge of approving anything which flies on a military aircraft. So in terms of quality, we are able to say that we are not just the best in the country, but we compete with foreign companies on a one-to-one basis on our quality. In addition to this, we also manufacture wire harnesses as well as fiber optic solutions. I'll explain where those applications might be helpful in the next slide. Predominantly in the sort of energy market, what we see is two types of things that we can help in. One is on the cryocoax side. So when you go to very, very low temperatures, minus 268 degrees Celsius, 2 Kelvin, 4 Kelvin, and so on, we have a range of cables, connectors, adapters, and cable assemblies which operate at these low temperatures and provide extremely low loss. And we have a range of them across multiple different frequencies. On the other side, what we also do really well is we have high power cables which are able to manage, almost up to 10,000 watts of power at 500 megahertz. The differentiator here is you might be familiar with the LMR series of cables and cable assemblies used, but those come with cutoffs in frequency as well as slightly lower, slightly higher losses. These R cables are much lower loss and are much more flexible compared to the others. We are also able to add variants and engineer with you a solution that will provide you the ability to meet your application rather than just picking up something which is available in the market and then sort of, putting it in some way which will meet it. Rather, we will work with you on both of these applications to define a solution, provide you external jacketing. For example, we can add a stainless steel armor or a hose on top of it, which will protect the cable over long lengths, so on and so forth. We've also developed many high power cable assemblies, which we have flown on aircrafts with heat sinks. These heat sinks are something that we design locally. We design them according to the spec, what power is going to pass through, what temperatures are going to be touched, and so on and so forth. Of particular importance in this market also is RF components. We started 40 years ago as representatives of these foreign principals in India. We continue to do that business today, but not as much as our cable assembly business. In particular, what's interesting in the high power sort of market would be waveguides, and we have partnered with a company called SMC in Canada for the same. They're able to provide a range of waveguide solutions, not just waveguide assemblies, but also circulators, isolators, filters, and so on. For power amplifiers, LNAs, and filters, we work with a company called Saras in the UK. The benefit with them is they are quite excited about adding more India content and manufacturing a large percentage of this product in India. And we're working with them closely to define the supply chain for us to be able to manufacture these products inside India. Finally, with the Trexon Group, I talked about cryocoax. They are the manufacturers of these cables and cable assemblies, and we work with them closely across a range of applications, but predominantly with the cryocoax. Finally, I want to show to you some of our
customers and briefly talk about one or two big successes. On the left-hand side, what you can see is our government customers. We work with all the defense PSUs, the defense labs, and particularly with ISRO. Over here, I'd like to highlight that we have built space-grade cable assemblies, which are currently going to be deployed upon a launch vehicle. And so, that level of technology, that level of skill that's required in our technicians, we've invested much, much ahead of the need. And as India is taking off in space, so we hope to do so with them. In a similar way, when it comes to the DAE sort of market, we are similarly interested to upskill ahead of time for your requirements. On the right-hand side, I'd like to talk about a couple of interesting developments. In the private side, we deal with a number of both national as well as international integrators, such as Astra Microwave, Alpha Design, and so on. Safran, which you may know, is a French company which does a variety of different defense products. But here I'd like to talk about the medical market, where we are working with a European manufacturer to make medical grade RF cable assemblies, which will be used for imaging equipment. So the point I'm trying to highlight is that we have a range of capabilities. We have a range of engineering people behind it who will be able to engineer a solution for you to connect any part of your system to any other part of your system. Once again, I thank you for the opportunity to be here and wish you all the best in your endeavors. Thank you, ma'am.
Thank you. On behalf of organizing committee, please accept our token of appreciation. Next presenter from industries, Asako Private Limited. Please adhere to time, 5 minutes.
वीडियो भी है ना, वीडियो चलाना है, इसके बाद चलना है, फिर आना रहेगा मुझे, ठीक।
Hi, good afternoon all. I'm San. I head the business development of ASACO, and I have my colleague here, Nikhil. So I just want to give a quick introduction to ASACO. ASACO is a 55-year-old company, which is based out of Telangana. And it's a privately held company, which is AS 9100 certified. So we've been supplying liquid propulsion systems to space, aerospace, and defense industries. And we are the sole supplier of the PS4 engine for the PSLV. We are the only one authorized by ISRO to supply the same. We've supplied around more than 500 engines till date. And we have a NATCAP certified electron beam welding facility, which is one of the biggest in the private sector in India. And we have two verticals of business. One is precision machining and other one is machine building. So in machine building division, hot isostatic press is one of our major projects. We've supplied a couple of hips, around 12 plus, to different PSUs. And these are our prime customers. Coming to domestic, it's ISRO, DRDO, HAL, DAE, BHEL, BDL, L&T, Tata Advanced Systems. And our overseas customers are Elbit Systems, IAI, GE, Safran, Honeywell, Collins, and Eaton. So we do a lot of precision machining and electron beam welding for these customers. And our association with RRCAT has been over a decade now. And we supply the cavities, which is the 1.3 gigahertz SCRF cavity and the 650 megahertz SCRF cavity. And also the some of the components for the accelerator structure components for the LINAC, which include input and output couplers, regular cell A, B, C, and bunch of cells, wherein our scope of work include procurement of the raw material, machining, inspection, forming, rolling. And coming to the LINAC, the components we supply for the LINAC, especially the couplers, the criticality is maintaining the cylindricity of 2 microns and roughness of N2. And most of the machining orders which we take up is 1 to 2 microns. And we are experts in, you can say we are the pioneers in precision. So these are some of the jobs which we do on electron beam welding. The first one over there, the body weldment. It is for one of the Boeing aircraft engine, wherein it's fully electron beam welded. It's an aluminum casting, which is electron beam welded. It is around 5 stages of welding. And PMD assembly for DRDO, which is a propellant management device, which controls the propellant to be supplied to the engine. And again, the compressor outlet for gas management. It's again for Boeing, wherein it's a pure aluminum, which is EB welded to aluminum 6061. And that's a drive shaft, which we do the EB welding for Eaton. And there it's the 1.3 gigahertz SCRF cavity, which we machine and EB weld for RRCAT. These are some of our critical precision mission components. Most of them are done on 5-axis. We are experts in blades and vane machining. So like I was talking about earlier, the hot isostatic press is one of our major projects in the special purpose machine building division. We've supplied 12 plus HIPs till date. We do both for metallic as well as carbon components. So this equipment is mostly used to densify material under high pressure and temperature to improve the material quality. So it's mostly used for 3D printed components and investment castings. And ASTACO is going to have their own equipment. So far, we've been manufacturing and supplying HIPs. And shortly, towards the end of May this year, we'll be having our own hot isostatic press in-house, providing services. It'll be a metallic one. We are thinking of having a carbon HIP also. These are some of our expert components, mostly for the Israeli aerospace and defense. If you see, we manufacture connectors, the landing gears, and avionics shell, which is an airframe for the missiles. And we manufacture flanges and ground support rings. And these components are supplied to us for our aerospace customers like HAL and Safran. These are highly precise components. And ASACO is known for the supply of the complete PS4 engine for the PSLV launch vehicle. If you have heard about Aditya L1, that was a PSLV. And so, in fact, you can say ASACO is the one which takes the satellite to the space. So that's the complete engine there on the top left corner with the divergent. The engine is completely made of SS304. And the most critical part of the engine is the injector. We've even supplied the roll control systems for the engines, which stabilizes the vehicle at the time of launch. And the complete engine has 8 EB welded joints. And the complete engine is manufactured in our facility, which includes the material as well as the machining, inspection, testing, and EB welding. So
Time
this
is
is a
over.
semi-cryogenic engine.
Can please conclude fast.
Yeah. Okay.
Time is up.
Okay, then I'll just straight away go to the walkthrough video of our facility. Yeah. Because it's a long presentation. I'll just take you through a walkthrough video of our facility.
Welcome to ASACO, a name synonymous with excellence and innovation in manufacturing. We are a 55-year-old company and we are a one-stop destination for all your machining requirements. With decades of experience in crafting special-purpose industrial machinery, components with highest precision, sub-assemblies and assemblies, ASACO stands at the forefront of industry advancement. We are proud to be one of India's leading suppliers of critical space, aerospace and defense components, delivering precision and reliability to the most demanding sectors. ASACO is honored to be the sole supplier of the critical PS4 fourth stage liquid propulsion engines for the PSLV launch vehicle to ISRO, playing a pivotal role in India's space exploration success. Special purpose machine building, the only manufacturer and supplier of hot isostatic press in India, and we have a patent for the design. This is one of the biggest carbon hot isostatic press in the world supplied to a PSU in India. We will be having an in-house hot isostatic press facility to offer hipping as a service for metallic components by the first quarter of 2025. Our other manufacturing and supply facility: dissolved air flotation system, aeration grid assembly and perforated sleeve assembly are used for wastewater filtration projects and supplied globally. At ASACO, our state-of-the-art facility houses advanced 4 and 5-axis CNC machines, complemented by a world-class quality control lab. Our commitment to quality is unwavering, underscored by our AS9100D and ISO 9001 certifications. Our NADCAP accredited electron beam welding facility ensures the highest standards of precision and durability, meeting the exacting demands of aerospace engineering. ASACO, where precision meets excellence and innovation drives the future. Join us as we continue to push the boundaries of what's possible.
I would like to thank.
Welcome to ASACO, a name synonymous with excellence and innovation in manufacturing. We are a 55-year-old company and we are a one-stop
Anyone has any
destination.
questions, we are more than welcome to visit our stall, which is stall number 17.
Okay, thank you. Thank you. I invite representative from Dassault now, Dassault system, and you are invited for taking this token of appreciation from the organizer.
6E. ठीक है बस
Yeah, we are planning to just with our RRCAT build our own EPU, like a TOT.
Stall is there. Stall.
Okay.
Let's see. Stall is there. Article.
Yeah, between that, yes. Okay. Yeah. Yeah, we be there. Okay.
So we ready.
So we would like to, because we have like 2 words. Thank you.
Yes, Mr. Shura.
Yes,
Yeah, please. 5 minutes.
thank you, madam. Good afternoon, everybody. My name is Dr. Sai Krishna Puranam. I had the technical team of CST, which is the simulation software, as most of you know, which is from Dassault Systems. So even though I do have very few slides, but a lot of content in them, I know that I'll not be able to cover it in the 5 minutes that's there. So if at all, if you want any more detailed explanation, please kindly visit us at booth number 18 upstairs. Thank you. So CST comes under the brand of Simulia, which basically holds all the simulation softwares that are operated that come under the umbrella of Dassault Systems. Most of you might be familiar with Abacus, which is basically used for the structures part. CST comes under the electromagnetic portfolio, which is the main simulation software. As you can see, the main pie chart of CST is basically divided into 5. So you cater to the entire frequency spectrum. So starting from statics, which is the low frequency solutions, all the way to terahertz antenna simulations and EMI, EMC, and of course the SI and PI, the signal integrity and power integrity for PCB boards, and of course the particle dynamics, which is where the particle studio part comes in here. We also do have cable studio simulation as well, as one of my previous speakers was talking about. You can basically simulate your cables in CST just to see as to how efficient they are. But that's a discussion for another day. So the main solvers in CST basically are 4. So you have the TRK solver, which basically performs your tracking analysis. And then you have the PIC solver, which is basically used whenever there is an interaction of RF signal along with charged particles, which is the PIC solver. The third solver that we have is the ESPIC solver, which basically is a slightly approximated version of the PIC solver. Now this is basically used for the simulation of high ion, high plasma sources. And this is where you basically have most of your Monte Carlo collision models, and where you create ion thrusters and so on and so forth, ion sources. And the last one is basically used is the wake field analysis solver, which basically is used to see as to what the wake fields are, what's the transverse and the longitudinal wake field impedance is going to be, and what's the loss factor and what's the kick factor. So you can do all of these simulations with the wake field analysis. So what all can you design using CST? Well, CST is basically used extensively in the design of traveling wave tubes. And there's an extensive division in SAC ISRO, which uses CST for the design of TWTs, and of course in MTRDC Bangalore as well. So, and in addition to TWTs, you can basically design klystrons also in CST. So if you're interested, please visit me at booth number 18. I'll basically show you the model that we basically have. And in addition to the TWTs and the klystrons, you can perform also SEEs, secondary electron emission, which basically talks about the multipaction effect. I was very happy to see the director of the proton accelerator group in the morning talk about the different slides, and it made me feel very happy to see that there were 2 slides which said simulated with CST Microwave Studio. So we're very happy that it's basically being used. In addition, so we do have some additional tools called Spark 3D. So basically you can run a coupled simulation, you can set up the model in CST, and CST will automatically transfer the results to Spark 3D, where you can perform multipaction as well as corona discharge analysis as well. So Spark 3D is an add-on tool. And this is, of course, the accelerator community. We do have an inbuilt macro that designs accelerator cavities. And then as I was saying, you can design Linux in CST. You can initially perform an eigenmode analysis, and then you can see as to how well your eigenmode behavior is going to be. And after that, you can then create a complete PIC model to basically see whether you are getting the acceleration that you would want. I know it says in detail, but I'm not going to go through in detail. You can basically design TWTs in CST, and then you can also design klystrons as well. Now this is a complete model that has been set up in CST, where you can, this follows the seminal paper that Ulrich Becker has basically written. So you can design this complete thing in CST. It's not a part of the component library. The output cavity is, but the entire structure itself can be designed in CST. Moving on. You can, this is another example where you can set up a complex simulation where you can perform your eigenmode simulation, and then you can basically calculate what the Lorentz forces are, and then you can transfer the results to the stress solver to basically see whether you're basically seeing any shift in the frequency. That's number 1. Or else you can go the other route as well, where you can find out what is the thermal abilities and what is the thermal simulation and how much temperature rise, and does this rise in temperature give rise to any kind of a deformation. Now all of this can actually be put up as one simulation, and if needed, you can also put and use our thermal simulation solvers to see whether any kind of a cooling simulations can be performed by using our fluids and stuff. Okay, so that's the overall workflow that I have. Overall, what I would actually say is, if at all, if you're designing any kind of an EMAG structure, CST is your get-to-go tool, and then you can basically simulate complex problems and structures, and you'll be able to design a multi-physics kind of a simulation as well in CST. So that's all we have. We do have a couple of other simulation softwares that we have acquired called AMCAD, which basically helps you in designing RF circuit front ends, and also what is basically called WASPNet, which previously was called MIG, which is used for designing planar microwave components. So with that, thank you very much.
Thank you, Mr. Sai, to abide by the time. Now I invite a representative from Precise Vacuum and Mr. Sai for accepting our token of appreciation.
इससे नेक्स्ट होगा, इससे बैक होगा, इससे नेक्स्ट।
Good afternoon, all.
Yeah, Precise Vacuum System.
Yeah. So I'm Vishwas, and I will introduce you to the activities we do at Precise Vacuum. We are a 30-year-old company having state-of-art plant in Nasik. This company was founded by Mr. Vidale, Mr. Shinde. We are ISO 9001, 14001, and 45001 certified company. We are also certified by PGCIL for the bus duct. We work across 4 verticals: vacuum pumps and systems, cryogenics, GIS electrical products, and some custom projects. These are some solutions from our vacuum portfolio: double stage pumps, single stage pumps, multi-stage dry roots pump, piston pumps, oil diffusion pumps, customized systems, pumping stations, helium leak detection solutions. In cryogenics, we do cryogenic Diwar from 1.5 liters to 120 liters, open mouth containers up to 500 liters, silos up to 20 KL. And we do space simulation chambers in any configuration. Freeze dryers, we do custom fabricated chambers in SS, beam lines. These are some sputter chambers. These are aluminum chambers for MPCVD, microwave plasma chemical deposition. The next vertical is GIS electrical products, wherein we do the bus ducts of 145 kV, 245 kV, 400 kV, and 800 kV. We serve the major who's who of the power industry like Siemens, Husung, NHPS, ABP, Crompton. We do critical angular gas insulated bus ducts as well. These are CT tanks. These are aluminum CT tanks, case controls, and various components. This is the overview of our bus duct shop floor. We have dedicated radiography area, helium leak testing facilities. We have paint booth, shot blasting area. This is the dispatch area of the bus duct. Thank you for the opportunity given to present ourselves here.
Thank you. Thank you. Please accept a token of appreciation from the organizers. Over to organizer for some interesting announcements. Rinki.
With due permission of session chair, there's an important announcement regarding the exhibitors award. The details on this will be shared by Shri Preetam Singh Bagdwal. Sir.
Thank you, Rinki. InPAC 2025 has organized an exhibit also. That exhibition has in total 24 stalls from across the field, being the stalls has a representation of electrical background, electronics background, and someone from mechanical point of view also, and few exhibits from vacuum also. So this year we have decided to give them a best exhibit award. So we have decided to offer 2 best exhibit award. And in this regard, we have formed a committee, and the committee was led by Dr. K.K. Pan, and Other members was S. Raghavan, Deepak Sharma, and Avnish Ojha. The committee visited each and every stall. They had interaction with them. And on the basis of their assessment, we have been given 2 names in no particular order. Both the names, what we are offering the first for us, no particular order to them. So I would like to invite first Mahind Lad sir, Director PAG, ex-head division RFSD, and current head of the division RFSD is all Ramesh sir, who is happened to be the convener of exhibition committee also, to come on the dais and join the madam and hand over the prize to the respective winners. And thank you all the exhibitors for participating in InPAC 2025. You gave another dimension to this conference, and we expect you to be part of coming conferences and coming projects also. So first, I would like to take first name. So we had a company which has represented 4 companies in this conference, and 2 of them were front runner. So we would like to call Rudraksh Technology to come forward to receive its award for the best exhibit. Rudraksh Technology. The basis on which this award was given, as conveyed by the committee, was the aesthetic what you have in your stall, the presentation what you give, not on this stage, on your stall when you are meeting the committee and other members. And on the basis of that, we have decided another best exhibit award, and that goes to the RNS, Road and Swords. And I request RNS to come forward and receive his award. Thank you, Lord sir. Thank you, Ramesh sir. Thank you, ma'am. Thanks, everyone.
Like to mention that I congratulate Ramesh Kumar ji and all the team members to smoothly coordinating this exhibit, which is one of the different ball game together. So congrats to the members. Okay.
Thank you lots of for motivating everybody and inspiring them. Now coming back to our technical session, now invite Shri Rajiv Mehta ji from Inter-University Accelerator Center to give a talk on high current injector, present status and roadmap ahead. Shri Mehta Saab is a BSc and MSc in physics, and his area of research work is accelerator science and associated technology, design, fabrication and testing of accelerator components, including cavities and charged particle optics. His more than 50 publication he has. His achievements are member of Scientific Organizing Board of International Particle Accelerator Conference, expert member of Expression of Interest Committee for the project of Indigenous Magnetic Resonance Imaging of Ministry of Electronics and Information Technology. He is member of the Council of Governing Board and Financial Committee of IUSC, convener of Accelerator User Committee IUSC, and chairperson of Beam Time Scheduling Group IUSC. Sir, you have 15 minutes to discuss. Yeah, thank you.
Thanks to the organizers
on the behalf of IUAC and on my personal behalf. I would quickly go as we are running late. High current injector, present status and roadmap ahead. This will be on behalf of the complete group of HCI. And I must say that a difference between success and failure is a great team. Unfortunately, IUAC has a very great team. I'll start with a small this thing, and this has relevance to IUAC. This is one of the best books I have seen, a roadmap for accelerator under the guidance of Shri Purushottam Srivastava. And why I'm particularly mentioning this is one of the front cover, one of the accelerator is the high current injector that IUAC is envisaging for its user community. This is one of the most ambitious program IUAC has taken along with the free electron laser. Let me just, I'll take maybe a couple of slides only and go through the history. History is something which we should remember because that is what encourages us for the future development. And if you see, this is the team of Lawrence ready for acceleration, and I literally see that they are ready for acceleration. They're sitting. And at the same time, around 1960, Professor Meghna Shah and B.D. Nag Chaudhary sir also had a particle accelerator. And there is another one which is who's and who of DAE symposium, I mean the DAE Bhabha Atomic Research Center that Dr. Raja Ramanna, Dr. Homi Bhabha, everybody is there in 1962. This is something we need to archive and keep it safe in custody because these are the figures that will not see them off. And another one which is this note by Dr. Devetya, cyclotron has worked, it was dated 16/6/77. I'm sure it is there in archives of VCC. It's a very important document. Coming back to the present now. IUAC is a multidisciplinary experimental research facility. I'll just give brief idea about a high current injector, why it was envisaged. IUAC open 24/7, 365 days for the user facility. This is the only user facility outside DA MBA which serves to the user and completely for a user facility. Our all accelerator developments are governed by the user requirement. So we are open new window to young minds and our nation to strengthen the pool of scientists by building a bright future and scientific understanding. Of course, we operate and build. Our mission is mainly, I'll try to focus on this, participate in a national program and contribution to our nationwide user base. That's very important and critical for us. Priorities carry out the experiment and vision. Objective is to provide world-class accelerator system along with experimental facility to create a basic infrastructure, facilitate internationally competitive research. Anybody from university, NIT, IIT, any institute can come and join us and use our facility. Just to say that because our motto is knowledge, accelerator for knowledge. If you see, we have 700 research group associated with this, 160 university, 86 colleges, 107 other institute. We have produced almost 1200 PhDs and 400 postdoctor, and this is our footprint all over the country. We started with a modest 15 UD pelletron accelerator, which is still one of the workhorse. And as I said that we are user-driven facility. Once the user said that we need more energies, we ventured into the superconducting linear accelerator. This is the first, India's first niobium-based superconducting accelerator facility. And we have a complete in-house development facility starting from EBW, machining and everything. And then there are other facilities, standalone Rutherford backscattering, accelerator mass spectrometry. On this, I must say that under Ministry of Earth Sciences, we have been given a task to set up a national geochronology facility, which will be coming on our another area is in Noida. So this is there, and then we have an implanter and tabletop accelerators. Then this is our footprint complete. If you see in IUAC, we have multiple research facilities. All are governed by the starting from the pelletron, going to the superconducting linear, and this is the high current injector. Now, coming to user requirement, which created a need for the high current injector is this. If you see, typically we receive every year around 500 proposal from the user, sorry, 300 proposal from the user, and they submit this proposal to us. And if you see our footprint, in last 3 years, it has been completely all over India. It's complete. And this is our, IUAC also provide funds to the user for completing their PhDs and experiments. Now, if it's cost about, because UGC, we were formed under 12 CCC and under this thing, financial approval, we typically use 3.28 lakh rupees per 8 hours. That is our expenditure on a user. So this is an extremely large amount of money we spend on each user. From the user perspective, requirement, when it comes to the requirement, greater varieties of beam. Users said that they need greater variety, stable beams of abundant isotopes, heavier neutron-rich beam like 54 chromium, nickel, xenon, zinc. Then rare isotope beam species of higher intensities. Explore the rare channel of nuclear reaction and help in studying exotic phenomena in nuclear structure. So all these things were governed by the user, and from that, since Pelletron and LINAC cannot provide the high currents and other species, so we thought that we need to have some other injector, and hence high current injector came into the picture. Researcher need exotic beam, high current injector can solve this. And then pending shifts are too large in our center. We have a very huge database of users. So by having a high current injector, the typical nuclear experiment which lasts for over 5 days can complete in 2 or 3 days, and hence we can reduce the backlog. And the solution was to an injector to the LINAC. So we have a high current. This is just for my younger colleagues who are here. Most of you people know we have a ECR ion source followed by radio frequency quadrupole, a drift tube LINAC. This final energy is governed by the transient time factor of the LINAC, which is 8% to the velocity of the light. And we have a various component. I'm not going into detail. We can see that. But I typically come what we have achieved in another. High current the drift tube LINAC is there are 6 such tank what we have. And these are a typical structure what we have, and this particular design has an inbuilt bunching section inbuilt. So the beam when travels, it sees a bunching here and then further acceleration. So we don't have an additional buncher which is sitting outside. This is all installed in the beam line. As you can see, the experimental area. The problem that we have faced, if you see all this structure which I'm showing has a copper plating requirement. And this is what we saw when we gave it outside to a vendor. And they were not ready to do this. Fortunately, in one of the InPAC, I met Avinash Patambakar-ji, and they suggested why not RRCAT, and I am thankful to RRCAT and especially Ramshankar-ji to carry out this job for us. But unfortunately, they were busy. We could not do more work with them. And we went with this lab. This is a very important lab, and I think all accelerator lab will need copper plating sometime or another. So this is the lab, Central Electrochemical Research Institute, Sikri near Karaikudi. So that's the place where we got all the copper plating done for future projects. I'm quickly going through this. And this is one address this is basically we have to do everything in India. And this is the energy gain we obtained for the various drift tube LINAC, and you can see that we have achieved the design goal for almost up to all the accelerating section, starting with radio frequency quadrupole, DTL1 to DTL6, energy gain verified. By this year end, we are going to install one small chamber in the beam hall where 1.8 MeV per AMU beam can be used for astrophysics experiment. We had a small team meeting on this, and there are a lot of interest in this area. So we are going to set up this and do this. This is the typical beam what we have used in last 2 years. We have nitrogen, oxygen, neon, argon, krypton, xenon, copper, or lead, and these are the discrete energy what we can provide for nuclear astrophysics. Finally, this will be the energy entering into the LINAC. But on the other chamber, standalone chamber, these are the discrete energy that we can provide for astrophysics experiment. Now, we took up it was a calculated move that instead of going on a straightaway complete setup, we went in a phase-wise manner. In a first phase, we installed whatever was available with us. This is I've already presented in last InPAC, but I want to mention that because this is sake of the completeness. So we completed all this thing and entered the beam hall, our first experimental area, and that way all active accelerating components were installed and checked. So that was the one aim of that, and we used neon nitrogen 6+ beam. And typically we got around 280 nanoampere, which was 47 PNA was delivered at this point. This validated that whole section is complete, because after that it is simply a transporting beam to the LINAC entrance. Second was, whatever we purchased a complete set of elements, there are typically more than around 300 elements that have been installed. This is the biggest accelerator of IUAC, and once they were installed, we wanted to test each of them, and for that, the second phase, we tested the beam only from ECR source and the RFQ. All the details were switched off, and the beam was transferred up to this point. So we checked everything. We found all element, whether it's a power supply, magnets, and everything were successful. And we got 10 nanoampere, and when I'm saying 10 ampere, we didn't optimize. Idea was to check the functionality of each element that has been installed in the beam line. So after that, we immediately went with our first LINAC beam experiment, and here we use Neon 7 plus 2.85 MeV. This M by Q was this. I'll talk about this thing later if time permits, why we are restricting on 2.5. And we got this energy, and this was the final point before entering into the LINAC. So once the LINACs were getting ready with the liquid nitrogen and liquid helium, we checked it and we got 18 PNA of current at this point, and we were ready for beam acceleration through the LINAC. This is our first experiment when the beam was transported through LINAC, and that was our final gain, our target. 36 MeV Neon 7 plus beam was accelerated through the superconducting LINAC, but unfortunately out of 24 superconducting cavities, we could only transport from up to 12 only. Beyond that, there were a large number of peaks that were appearing, and I'll come to the reason for that and how we have solved that. And this is the beam what we have seen on the quads at the end of the LINAC, last cavity. And to verify the energy, we know that what was the energy gain from each of the cavities. And so what was finally we got 77.1 MeV, which was as designed also, considering the whatever energy gain the LINAC can give. So that verifies the first part of. But as I said that we could not complete it, that was because we had a very large delta E inherent from the system. First of all, our multi-harmonic buncher was not optimized, and I'll come to that point. And so we had to really take a very large delta T in the beginning to transport through the LINAC, and the acceptance of the LINAC didn't allow us to accelerate the beam completely. So you see, up to first 12 cavity, we were very reasonably good, but after that, we started getting other peaks because of the large energy spread. So to counter that, we have installed a double slit in the last bending magnet section, and here we will cut the beam and operate this achromat section in energy dispersive mode and cut the beam so that the beam delta E becomes as comparable what LINAC requires. So this is, and since we have a very large current and detector system cannot handle more than 10 PNA, the existing our detector system. So even by cutting this thing, we will still have a very large current to carry out any experiment. So we did that, and we were now hopeful. We are waiting. As soon as our LINAC is operational, we will accelerate the complete section again. So we are just waiting for the superconducting LINAC to being operational. Meanwhile, we also performed one experiment, because this is going to be a user facility. To ensure that user experiment needs a very large time and a stable beam, what we did when Neon 9 plus 36 MeV beam was given to a user from Professor Nageshwar Rao from Hyderabad University, and for 60 hours continuously very stable beam was provided for the experiment. Results are awaited. This is very recently done. So that proves the stability of the high current injector from the user perspective point of view, because IUAC is a user driven system. We don't have we do development, but based on the user requirement. And these are the beam that we provided to user, and this is the beam on the user target. This is around typically 5 millimeter diameter size beam. We could reduce further, but this is what the user requirement was. The difference beam we have produced in past, and recently we have also produced krypton beam, xenon and neon. So these are highly effective beam required by the user during the workshop. We were given that we should produce them and show that what kind of current. So if you see, we are getting very high current of these beam also. So this will be accelerating further. Major bottleneck, what we still have in our HCI is multi-harmonic buncher, RFQ and DTL number 6. Now, multi-harmonic buncher, if you see, this is basically there is a design flaw in this, and we need to correct it to make sure that it gives around 2 nanosecond bunch width at the entrance of the RFQ. Otherwise, the RFQ will blow up the delta E, and which will be like an avalanche when it goes to the DTLs. So this is one thing we are going to work on. We have a plan for that. RFQ, we have a severe issues with the power, and hence we are restricting ourselves to a lower A by Q rather than A by Q6, because by increasing the charge state, we are able to reduce the power required in the RFQ, and we are still. But since this is a constant velocity structure, design still gets validated even if it is a charge state is higher. Yeah, I'm going to. Then DTL6, we have a only we issue have with DTL6, and this is the surface related issue. The surface contaminations are there. We need to open it, clean it, and then we have to install it back. So we have a proper roadmap which we have devised for this system, which I'll just share with this. Complete the LINAC operation as soon as we get the LINAC ready for our acceleration. Then after the LINAC acceleration, we'll open DTL 5 and 6, clean them and install it back. We'll also install a chopper and deflecting system, which is ready now with us. And RFQ modification we are working because of the high power. Tomorrow there is a talk by one of my colleagues. He'll specifically talk about the RFQ also, what kind of issue we are having. There is a burning issue because of the high power in some points. So we have modified this. Hopefully this will solve this problem. And once this is solved, we will go back. If this is not solved, then we have to go for this step where we have to really work on the base place modification of RFQ. We are already working with SICRI to have another chamber which is copper plated. We are going to give them a completely new chamber with because right now the RFQ is having a frequency of 44 megahertz where required is 48.5. So to compensate that 4 megahertz, we need to put lot of tuners and other thing so that the frequency can be brought to 48.5 megahertz. So we will rework on this and we'll be ready. So, I mean, our complete goal is by end of 2026, optimize the system for A by QC and take a LINAC acceleration again. Plan of action, as I already mentioned, so I'm not going. This is 2 slides, ma'am. If time permits, I can just give 2 more slides. We have a very high performance computing system, which has been already informed by Professor Pandey in his talk. And this is one of the facility which was inaugurated by Honorable Prime Minister Shri Narendra Modi ji on 26 September. Already you can see there are large number of people within 4 or 5 months. We have a lot of users who are coming, and there is an online facility. People can enroll their system and use this facility for there. Typically right now we are using for material science analysis. This is the Prime Minister inaugurating our system. Then there is our MRI magnet. IUS is proud that we worked on a major system of with ministry and Samir to develop a 1.5 Tesla superconducting magnet. And this is at the Principal Scientific Advisor's office, and this is their comment, the Twitter handle. So it really makes IUSC feel proud that apart from our own accelerator development, we are also contributing to the social empowerment. Thank you.
Congratulations, sir, for making nation pride on accelerator technology. Yeah, thank you. Any question for using accelerator? How to get beam time? Okay, thank you. On behalf of organizer, it is my duty to honor you, sir.
Thank you.
Now, last presentation for this technical session, Shri Rajesh Kumar Sahuji, thing which we take alignment of big accelerator for granted. So he is going to talk about the challenges in precision survey and alignment of large accelerators. Shri Sahuji is a BE in mechanical engineering from GEC Jabalpur. His area of research work is large scale dimensional metrology for alignment of accelerator components. His achievements are, he is from 33rd batch of training school of BRC. He has successfully aligned SRS Indus 1 and 2 machines. He has supported two other DA projects in large scale measurements, streamlined Indus operation and operating training activities to present level, QIS for Indus RS facility, contribution in experimental metrology of ALI, CERN, and 100 measurements of sessions report on CERN. And he has publication in all national, international conference, journal, workshop. So you're welcome, sir. 15 to 18 minutes.
Thank you, madam. Maybe this is first presentation on survey and alignment in a general forum. Otherwise, earlier it was presented sometime as a alignment as a scheme was presented in review of Indus 2 project, and later on in international workshop on accelerator alignment in 1999. And so it is on behalf of our small alignment team, only 1 or 2 officers and few colleagues, which forms a small team. Since in the beginning up to 2011 or so, Mr. Vijay Prasad was also with us as in the alignment process of Indus 2. So for this matter, he is also part of this alignment team. So outline of my talk is just some introduction and how this large scale dimensional metrology is evolved, and then understanding its challenges, and what we did for Indus 1 to Indus 2, what was our journey, and how much we are ready for Indus 3. So large scale measurements, before calling it metrology, I will call it measurement. Large scale measurements, huge aircraft, large gas and steam turbine blades, and their assembly, large ship. They are large assemblies, and they need very high precision in their assembly. So our accelerator machine is also like a very large precision assembly. And during these measurements, for example, this rotor blade between this steam turbine, they are of the order of 25 to 30 meters and rotating in the stator, but on such a large dimension, only a fraction of millimeter, about 0.2 or 0.3 millimeter gap is there, and that kind of a stator rotor clearance is to be maintained because it is highly important for the efficiency. And in the same way, we can say that without a proper alignment, electron beam doesn't travel on its path. So then as the system goes bigger and bigger, our basic understanding that we can see in the next, our basic understanding that something is to be measured in the workshop and job is coming here, that becomes relatively impossible. And in place of that, we have to take the system around the machine, and then we call it that it is distributed measurement system. So by different laser tracker, by keeping a different station or together, or single station, single laser tracker, keeping it around it. This all big aircraft companies are using that. And in the same way, considering our experience in the Indus 2, a request from ECIL through BRC was there, that we have to there is some error correction is required on the 21-meter long stuffing ring, which is on 2 bearings, and we need some measurement. So I did some measurement on 1 or 2 days in ECIL and then trained them. In the same way, then in March 2016, this one colleague from ECIL and one BRC, they were also trained at RRCAT, and this was our contribution to another DAE project, that is mesh telescope. And another contribution from our team is CAP3, in which the two ends of the around 12 to 13-meter long coolant channel end faces, they are in 2 different vaults, and in single setting we cannot see both the ends, but the changes in the length is to be measured. So for that we completely a process qualification is done at RRCAT, and then we measured also at their CAP3 site. So when in place of measurement like this, in which 3 coordinates, 3 mutually perpendicular coordinate system, a coordinate system with 3 mutually perpendicular axes, and we are just measuring by touching the probe. There we get the coordinate directly x, y, z, but when we with an instrument we rotate around the machine, then the sensor readings are in the form of angle and distance, and they are indirectly related to the measurement. And in such cases, the challenges goes on increasing. So in our induction machine was around a 5 meter by 5 meter by 5 meter measurement volume. That was a small volume, and complete machine was visible in single setting. So in such single setting machine, it was possible to measure complete machine in a single coordinate system, but and instruments were only measuring the angle, and based on the some scale bar as a reference, it was measuring the determining the coordinates, and there was no coordinate transformation was required further and further, but this was not the case in INDUS 2. So this is general that while it is while making such measurements of very large object, when our measurement accuracy of the instrument itself is comparable or much poorer than the required accuracy, then you have to take best of the instrument and best procedure and analyze it for all the factors which are affecting it. And since it is a systematic study of our measurements, that's why it is called large scale dimensional measurements. So this is our INDUS 2. It was our measurement scheme in which multiple reference points were placed all around the ring, and there was a coordinate system, and with respect to this coordinate system, all points of this coordinates of this reference points were measured in the beginning, and it is good that our perception that alignment will come at the last, it is not correct. When the machine digging up the ground breaking is done for the machine, since that day till end, the beam is extracted and given to the beam line, and then again solving the problems of beamline person, scientist, who is not getting beam, why he is not getting beam, whether it is alignment problem at the machine side or in the beamline side. So from start to end, alignment team is involved. So some detail about this, we will go in the next slides. So any means in industry kind of thing, normally there is some primary measurement network like this, and at every this corner there will be multiple reference points, and reference points are in next photo we will see. And then every point is measured from multiple other points, and redundant data is taken, and by a least square adjustment, the best probable estimate is found out, and error ellipse is calculated, and that gives the idea what is the reliability of measurement and what is our confidence level. So you can see that all the magnets, this is a picture of around 2003 when vacuum system was not installed, and there are different references on the magnets, dipole, entry tangent and exit tangent, and this they are basically covered by the yellow cover to avoid dust. Otherwise, every reference point is like this. There will become some conical reference on which a Taylor-Hobson's ball of 3.5 inches capped, and center of this is our point of interest where the target is, where it is measured. So when we are measuring optically, the coordinates are measured for the center by only angle measurement, and when we put a corner cube reflector, then distance can be measured. So and such combination of distance and angle provides the finally software processing and finally determination of the coordinates. So various activities are going on here. This is the process of fiducialization of a dipole magnet, in which field mapping is going on that time in the magnet measurement lab, and based on that the exit tangent and entry tangent will be put in the form of this kind of combination, that is a physical reference, to provide a physical reference for a thing like magnetic axis which we cannot see. So various instruments, these are total stations, a theodolite with integrated electronic distance measurement. So in industry also, in industry we used total stations, and they are the manufacturer claimed that time that you used to claim that they are 0.5 plus minus 0.5 millimeter accurate, because they are just playing safe. But alignment head at ESRF, somebody did PhD in his lab, and he found out that these instruments are highly precise. So that if the systematic error part is removed, the residual errors are less than 0.1. And based on that, we also made a calibration facility of 30 meter, and distance were compared with the laser interferometer, and then a Fourier transformation for the fitting of all errors, and that error model was online correcting the measured distances, and the residual was of the order of 70 micron, 60 micron, like that, less than 0.1 millimeter. But we should understand that the alignment tolerance itself is 0.1 mm. So it doesn't allow any other error to be accommodated, or we should have sufficient knowledge about what error is coming from which for which parameter. So maximization of the performance of the best instrument, and to employ the most effective technique to the specific geometrics involved, and we have to always follow this rule for the accelerators. In industry also, this alignment tolerances are much tighter, but we can see that the best available instrument in the commercial market is laser trackers, and these are the accuracy claimed by the manufacturer. If we go by the general golden rule of measurement, we should not use the instrument for better than this accuracy, which is normally we see that the measuring instrument is 10 times, should be 10 times better than the accuracy you need. But that doesn't solve the problem of accelerators, because what accelerator physicist demands or what are the alignment tolerances, and that also already compromised. Those are already so tight that a thorough analysis of the measurement and its complete process is to be done. So these are the various errors, alignment tolerances by different machines, and we can see that what industry we are proposing is better than 50 micron over girder and girder to girder. These are the required tolerances. So we are targeting these kind of accuracies. So this and this 50 micron also is over a complete unit cell. So and continuously like a sliding window on any 30 meter or 10 to 50 meter, we should say exactly 10 to 50 meter, these tolerances should not cross this. And for the whole ring, after coming back, it should be closing, that the systematic error should not be in a single direction, such that at the end you are not escalating the error and not meeting at the starting point. So a lot of control is to be kept. So this is just for the information that how the instruments are developed over the time, and one can see that this total stations were, and around the same time we measured our INDUS 2, and laser trackers came here, because before that another form of laser tracker in the name of macometer, only 5 instruments were made. They were very costly, and only few big labs purchased 3 instruments, and then the production was closed. So this is the comparison of INDUS 2 and INDUS 3 in the size. So there are 8 unit cells of around 21.5 meter each for INDUS 2, whereas 30 meter each and 32 unit cells are there for INDUS 3. So what we see that the condition is same, that best you have to achieve. In INDUS 2 also the same condition was there. In INDUS 3 some instrumentation became better, but tolerances are still surpassing that. So so our motto remains the same. Of course, in this process there are some bridge designs come, that if some point is hidden, normally a offset in the perpendicular direction is taken, which is known in a particular direction by say 500 mm or 200 mm, but that doesn't solve problem always, because especially in the industry like size, where we have to take care of the earth curvature also, because the complete complete machine circumference is around 1 kilometer, so diameter becomes around 300 meter, and for that the earth curvature is not negligible. Another technology is photogrammetry, close range photogrammetry. Actual setup looks like this. This is one photo which I was measuring in CERN, and this technology can be a subset or supporting for the hidden points, or where multiple readings has to be taken, and something like this, in which multiple LEDs and our point of interest is inside, and then the instrument can see the a set of LEDs, and image processing will provide the coordinate here, calculating all x, y, z translation and rotation about that, not only a single offset. So in short, to close that we have to find out the uncertainty of complete measurement, and there are various factors affecting it. Skill of the operator, then vibration, temperature, dust. So vibration, in case of industry, it is very important because the stable beam is required of very small size, and the experiment station is around 100 meters, 30 to 100 meters away from the source. So any vibration at the source will get enlarged and will be unuseful if it is not controlled or taken care. Temperature, every single 1 degree centigrade is changes the wavelength of any electromagnetic wave by 1 ppm, or humidity, 30% humidity puts the same effect of 1 ppm, and our tolerances are also in that order. So nothing can be neglected. So in the same way, then there are different models how you are treating the measurements by statistically and to find out the uncertainty level, and object under measurement, that also, because it is also made of some metal, so its surface, then material, they also play a role, and all this contribute to the uncertainty of measurement. So a lot of studies to be done. We have planned.
Sahu ji, time ho gaya.
Okay. So we have planned this a subset of that, and presently, so quickly I will go to what I want to show then. So these things we planned in foundation phase, then design and development activities in our next phase. These are some instruments we want in foundation phase. But more than that, this is not visible here. I don't know. So we have added one system to evaluate the degradation of laser tracker with time. Then there are various methods, but they are only on the go and no go basis in the standards, but that doesn't solve our problem. We have to basically quantify how much is the error, and so there are different three studies are going on by my colleague Vikash, and thermal stabilization, how much it changes if the coordinates over time. So what is the effect on its distance measurement? What is the effect on its angle measurement, and horizontal angle, vertical angle, and so on. So one can see that this instrument is much better with respect to this instrument. So every instrument is different. One cannot believe on the what parameter accuracies are given by the supplier. So every instrument is to be utilized. So for a girder, this paper was presented here for 50 micron accuracy on a girder. So there is some analysis of the process is done, and so we have to still, yeah, and we are still just earth curvature effect is around for 300 meter. Earth curvature is not negligible. It is around 4 to 5 millimeter. So it means with dimension, as the size is increasing, though our technology progressed, it provided solutions also to some extent, but the size is giving us problems which are non-linear in nature. Means with size they are too much increasing. Like we will be taking care of earth curvature here, and that will put another problem, another responsibility on us. Thank you.
Thank you, sir. Thank you, sir. Excellent work. Any question? On behalf of our organizing committee, please accept the token of appreciation. Yeah.
Thank you.
Circular.
Yes, and all reference points are distributed over the ring, and around one can understand that for Indus 2, right from the putting first magnet in the ring to final alignment, it was 15 months. And for 15 months, we did not take tea at 10:30 because one cannot leave the measuring system unattended, and it has its own consequences. Otherwise, you will lose those 2 hours also. Yeah.
Thank you, ma'am. Thank you very much for conducting a very successful session. Now I invite Sri Manoj Gandhi sir to present a memento. To,
Please see the important announcement about the transport facility for today's evening.
phone sir,
नहीं किसी और ने, yes,